Hi there, and welcome to the Checkpoint Jumpstart training program on CloudGuard Workload Protection. My name is Levi, and I will be your trainer in this program. Before we get down to business, let's run through the program's outline. The purpose of this program is to give you an insight into the cybersecurity challenges involving the protection of workload in the cloud, and Checkpoint solutions for these challenges under the CloudGuard umbrella.
By the end of this program, you will be able to describe the cybersecurity challenges faced by workloads in the cloud, describe Checkpoint's solutions for protecting workloads, describe the steps required to deploy the various CloudGuard workload protection solutions, and perform light deployments of the various CloudGuard workload protection solutions. The program consists of the following sessions: this introduction session, which you are watching right now, a short introduction to workload protection. Then we'll have solution-specific sessions, starting with CloudGuard Container Security, CloudGuard Shift Left, CloudGuard Serverless Security, and CloudGuard AppSec. Finally, we'll summarize this program and suggest some further resources. For the sake of efficiency and in order for this training program to succeed, it is assumed that you're familiar with the following concepts: cloud computing and the workload concept, Kubernetes terminology including cluster, node, pod, and container, Docker container, serverless functions, Nginx web server and reverse proxy, and the CI/CD pipeline. So if you're unfamiliar with some of these concepts, please make sure to brush up on them before taking this program. It would also be beneficial if you are familiar with the AWS and Azure platforms, technologies, and concepts, as we'll be exhibiting some deployments using examples relevant to these platforms.
And that about wraps up this session. We wish you good luck in this program and hope you find it both useful and enjoyable. And I'll see you in the next session. Welcome to the short introductory session to workload protection. In this session, we'll take a high-level look at the threat landscape concerning cloud workloads, and we'll briefly lay out CloudGuard's advanced capabilities for protecting workloads.
By the end of this session, you will be able to describe the cloud workloads and application security threat landscape, and you'll be able to describe in general terms how CloudGuard protects workloads and applications. So, where do we begin? As we know, moving from an on-prem mindset and implementation to the cloud means a shift from a monolithic approach where services and applications are fully hosted on servers supplying all the resources needed to a dynamic, decentralized approach comprised of microservices which have the potential of being scattered across multiple platforms, environments, and resources. Infrastructure elements that were static in the corporate data center are now abstracted to software in the cloud, and their entire life cycle may only be a matter of minutes or seconds, what is known as ephemeral. On top of this abstraction, decentralization, and scattering of IT components, the management of various components becomes decentralized as well. Instead of just one IT department to manage, execute, and monitor, we have multiple cross-departmental teams who can deploy, manage, and modify resources, services, or applications. This evolution comes with a slew of security challenges that are unique to cloud deployments. The more decentralized a system is, the broader its attack surface. There are simply more components, assets, and mechanisms that may be exposed. Additionally, deploying multiple cloud accounts created by different teams for different applications means that there are simply many more targets of attack that might be compromised due to the human factor. All it takes sometimes is one misconfiguration of a resource or an account, and the road is paved for exploitation. Since cloud deployments may stretch over a vast array of platforms and environments, with multiple assets and multiple personnel responsible for various aspects of deployment and management, this may lead to deficiency in visibility and tracking. Invisible and unmanaged assets can create large gaps in security enforcement. Cloud assets are provisioned and decommissioned dynamically in large scale and in fast pace. Traditional security tools were not developed for the cloud and thus cannot enforce policies in such flexible environments. The faster than ever pace of the DevOps process around application deployment and server provisioning increases the risk of coding mistakes and exploit being shared automatically in this work culture. This rapid pace leaves little room for errors. In multi-cloud deployments, applications are deployed across multiple cloud providers. Vulnerabilities and mitigations differ between cloud providers. It becomes a challenge to create a consistent security policy across those deployments. Finally, cloud-delivered systems must be cloud compliant. That is, be in compliance with the industry standards, regulations, and best practices. Now that we've described cloud security challenges in general, let's focus on the specific challenges faced by cloud workloads, which naturally stem from the aforementioned challenges. First, for the sake of being on the same page, let's define. Workloads are the containers, functions, or machines that store the data and network resources which make an application work. In other words, they are the resources and processes required to execute an application, service, or other functionalities. Containers provide a consistent, isolated execution environment for applications. They are similar to virtual machines, yet they do not require a guest operating system. Instead, the application and its dependencies are packaged into a container based on an image, and then a standard runtime environment is used to execute the app. This allows the container to start up in just a few seconds because there's no operating system to boot and initialize. You only need the app to launch. The current dominant system for automating deployment, scaling, and management of containerized application is Kubernetes. It allows a company to get the same user experience regardless of the designated cloud provider. Every cloud provider has its own version of Kubernetes, for example, AKS, EKS, and GKE. Container environments elicit a range of cybersecurity issues. You must secure images, containers, hosts, runtimes, registries, and orchestration platforms. Container security is made more complex by the high quantity of containers most organizations have and the frequency with which they are updated. Each update is an opportunity for vulnerabilities to be introduced. Additionally, most images which containers are based on, even those that are custom-made, are built on third-party code and thus at risk of third-party vulnerabilities. Serverless functions, on the other hand, are single-purpose, event-driven functions that are triggered only in response to an event, such as receiving an HTTP request. The code executes in a fully managed environment where there is no need to provision any infrastructure or worry about managing any servers. This takes the abstraction of containers up a notch. Comprised of dozens or hundreds of functions, serverless applications are tiny microservices with their own policies, roles, API, audit trail, etc. This changes the attack surface. Instead of a small number of entry points with a lot of functionality hidden behind each one, there are now more entry points, each with a small part of the app behind it. Defending your application now requires thinking about each entry point. Additionally, most of these functions are provisioned with more permissions than they require. Overprivileged functions enlarge the attack surface as well as potentially increase the impact of an attack. The short duration of serverless functions means that serverless security threats may change shape. Attackers may construct a much shorter attack that just steals, for example, a few credit card numbers. Finally, the lightning speed nature of serverless functions execution requires adequately fast security processing. Any delay in execution due to protection and inspection will defeat the purpose of using this rapid mechanism. In the face of all these workload protection challenges, we have CloudGuard on our side. CloudGuard Workload Protection, which is part of the CloudGuard native security platform, provides a unified view of container assets across all cloud environments to ensure configurations are in compliance with known baselines such as CIS, Kubernetes Security Benchmarks, or NIST 800-190. In addition, security and compliance configurations can be built into CI/CD to automate container security during development. During runtime, CloudGuard protects the container assets using dynamic protection based on customized rules, behavioral analysis, as well as other threat intelligence modules, automating protection and remediation. CloudGuard's breakthrough code-centric platform automates security and visibility for cloud-native serverless applications from development to runtime, enabling organizations to securely innovate at cloud speed. By analyzing the serverless application code before and after deployment, organizations can achieve a continuous serverless security posture, automating application hardening, minimizing the attack surface, and simplifying governance. Utilizing machine-based analysis and deep learning algorithms, CloudGuard builds a model of normal application and function behavior to detect and block application layer attacks for enhanced serverless security. Up to this point, we've covered the security threats cloud workloads face and how CloudGuard can help protect against them. But what about the applications themselves? What about the APIs used to interact with cloud resources and services? How do we protect these elements? First, let's take a moment and talk about the threats we face in these areas. Web applications face a broad range of possible attacks described in the OWASP Top 10 standard. The decentralized nature of cloud implementations and the speed and scale of working in the cloud means apps are prime targets for various malign activities, from code injection to broken access control, coupled with a lack of sufficient logging and monitoring. These attacks can result in site defacing, information leakage, digital theft, and user session hijacking. In the realm of APIs, command injections and API key extraction can lead to exposure of sensitive data and the hijacking of resources. Furthermore, malicious bot attacks using automated web requests can be used to manipulate, defraud, or disrupt a website, application, API, and even end users. Traditionally, you would use a legacy web application firewall to defend against these kind of attacks. These WAFs are rule-based and use binary rules to match requests to attack signature databases. This creates enormous administrative overhead and blocks legitimate application users, or as we like to call it, false positives. Faced with these threats and the gap left by legacy WAFs, CloudGuard AppSec can stop OWASP Top 10 attacks, prevent bot attacks, and stop any malicious interaction with applications and APIs across any environment. CloudGuard AppSec is fully automated and leverages contextual AI analysis to provide precise threat prevention for modern web applications, lessening the need for ongoing administration and increasing applications security at scale. Gone are the days where rules had to be tuned manually with exceptions every time an update to the web application or API was necessary. From implementation through runtime, CloudGuard AppSec automatically analyzes every user, transaction, and URL to create a risk score to stop attacks without creating false positives. And there you have it. We've gone through the major security challenges we are faced when implementing cloud services and applications and the specific threats targeting cloud workloads, applications, and APIs. And we introduced CloudGuard's solutions to these complex, ever-evolving challenges. In our next session, we will start drilling down into CloudGuard's workload protection and see how we can perform a deployment. We will start with protecting containers. Thank you for taking this introductory session. I hope you enjoyed it, and I'll see you in our next one. Welcome to this session on CloudGuard Container Security. In this session, we'll take a deeper look at CloudGuard Container Security and how it is deployed. By the end of this session, you will be able to describe how CloudGuard runtime protection, image assurance, and admission control work to protect containers, and you'll be able to perform an initial deployment and configuration. As we know by now, due to the sheer complexity and decentralization of cloud deployments, containers can be vulnerable to exploitation. To help protect against malicious attacks targeting containers, Check Point offers its container security as part of its workload protection suite. This protection hardens cloud workloads by detecting overly permissive roles, vulnerabilities, and embedded threats. It automates runtime protection, providing multi-layer security, leveraging machine learning to profile and protect workloads. And it supplies governance and DevSecOps, enforcing granular security policies during CI/CD and production. CloudGuard monitors in real time the kernel system calls that workload containers perform. Runtime protection is a combination of two engines, signatures and profiles. The signature engine monitors the kernel system calls performed and compares them with known signatures that potentially indicate malicious behavior. For example, execution of processes associated with crypto mining software. The profile engine detects anomalies in behavior compared to a baseline profile, which is based by default on a learning period of 24 hours. Every time one of the containers of a given pod group performs an operation not observed during the profiling phase, a violation is detected and an alert is generated. Runtime protection includes the following resources. The Runtime Policy Agent. This agent is responsible for retrieval of user-defined configurations and policies from the CloudGuard backend. The Runtime Daemon. This is a Kubernetes daemon set which, as explained, runs the two runtime protection engines. The daemon monitors the kernel system calls. The last runtime protection resource is Custom Resource Definitions, also known as CRDs. These are runtime protection policies which define allow, deny, and exclusions. These CRD policies are present on any cluster our solution resides. So, once deployed, the flow would look like this. A node's runtime daemon requests information from the cluster's API server to determine which pods are running in the cluster and the processes that are running. These processes are basically system calls to the cluster's kernel. Meantime, the CRDs are constantly updated with valid signatures and profiles the Runtime Policy Agent retrieves from the CloudGuard backend. When a kernel system call is made by a protected asset within the cluster, its runtime daemon monitors the call and examines its validity against the CRD definitions. If there's a deviation from the policies defined in the CRDs, an alert is sent to the CloudGuard backend. When onboarding a Kubernetes cluster with runtime protection, CloudGuard automatically adds a default security policy and rule sets for the cluster environment. You do not need to perform any additional actions unless you would like to create specific exclusions. So we talked about runtime protection for containers, but what about the images they are based on? CloudGuard Image Assurance analyzes Kubernetes images in runtime to make sure they are free of known vulnerabilities and compromised repositories. The image assurance agents continuously check the cluster for all deployed images. If an agent identifies an unknown image, the agent scans and analyzes the image to find vulnerabilities, exploits, malware, viruses, trojans, credential leakage, and other malicious threats. Image assurance uses the following resources. The image scan engine, which is responsible for analyzing and scanning the image locally. This agent sends the backend the necessary information to complete the scan. And the image scan daemon, which is a Kubernetes daemon set that checks the local registry on every node to find the deployed images on the node. So, once deployed, the flow looks like this. Regardless of CloudGuard, for pod redundancy purposes, Kubernetes saves container images locally in the cluster for every pod it handles. In each of the cluster's nodes, CloudGuard maintains an image scan daemon, which scans the list of locally stored images by calling the cluster's internal container registry. This information is relayed to the image scan engine, which is then relayed to the backend. The backend then examines and validates the list of images. If it detects an unknown image, it reports this to the image scan engine. The engine then requests the image scan daemon to fetch the image in question from the registry. After its retrieval, the image scan engine unpacks the image, analyzes it locally, and sends its metadata to the backend. The detection verdict is then presented in the CloudGuard portal. You can view the findings in the CloudGuard native portal under Images, where you can drill down into the Posture Findings tab. You can also see the vulnerability findings for all clusters in the account by navigating to Image Assurance Vulnerabilities. When the process of onboarding a new Kubernetes cluster with image assurance is complete, or when image assurance on a Kubernetes environment is enabled, CloudGuard automatically adds a default policy and rule sets for the cluster environment to issue image assurance findings. You do not need to perform any additional actions. CloudGuard creates these findings when it scans the image for the first time. Then the CloudGuard portal checks it periodically for changes or newly discovered vulnerabilities. But what about the API calls to the Kubernetes cluster? Understandably, some calls may either be malicious in nature or come from an unauthorized source. CloudGuard's admission controller stops malicious or inadequate requests to the Kubernetes API server before they become persistent. Based on the controller's decision, the request can be immediately rejected and an error is returned to the end user. The CloudGuard admission controller utilizes a Kubernetes validating admission webhook to enforce the policies created by the users in the CloudGuard native portal or via CloudGuard APIs. The admission controller consists of the following resources: the policy agent, which is responsible for retrieving configuration and policies configured by the user from the CloudGuard backend. The enforcer agent, which establishes the admission webhook, receives the API calls and validates them based on the enforced policy. And finally, the CRDs, which consist in this case of detection and prevention rules for each supported Kubernetes object type, such as pods, jobs, roles, etc. Access to these CRDs, including read permissions such as get and list, should be restricted, as they contain information on the cluster security. So, once deployed, the flow looks like this. The policy agent retrieves user-defined admission criteria based on configurations and policies from the CloudGuard backend, and updates the CRDs accordingly. Once any API request to the Kubernetes cluster API server comes in, it is intercepted by the enforcer agent. The enforcer agent evaluates the API call, making sure it is not malicious, based on the CRD definitions. Depending on the settings, if the call is malicious, it can either be just detected and reported, or detected and blocked. So for instance, only DevOps has permission to connect via SSH to a pod protected by CloudGuard. So the API call will be permitted to pass by the enforcer agent to the API server. API calls from all other sources in this case will be dropped before the API call is completed. Unlike the previously discussed components, for admission controller to function, it requires proactively adding a policy rule set. Later on, when we get to this part of the deployment, we'll look at how we can add such a rule set. An additional component we can enable during the deployment process is threat intelligence. CloudGuard delivers advanced security intelligence, including cloud intrusion detection, network traffic visualization, and cloud security monitoring and analytics. It combines cloud inventory and configuration information with real-time data monitoring from a variety of sources from Amazon AWS, Microsoft Azure, and Google Cloud Native Log, packet capture, appliance, and alert tools. The outcome is rich contextualized information, enhanced and simplified visualization, deep event correlation, querying, intrusion alerts and notification of policy violation, enhancing security operations centers with relevant cloud security intelligence for faster and more efficient incident response. Finally, the last component that is enabled during deployment is CloudGuard Cloud Security Posture Management. This component is baked into the solution, so you need not enable it proactively. Posture management automates governance across multi-cloud assets and services, including visualization and assessment of security posture, misconfiguration detection, and enforcement of security best practices and compliance frameworks. Check out our dedicated program on CloudGuard Cloud Security Posture Management for a deeper dive. Now that we've covered the various components of CloudGuard workload protection that can be deployed to help protect containers, let's roll up our sleeves and start deploying. Deploying CloudGuard container security is rather straightforward. We will synchronize CloudGuard and the Kubernetes cluster by deploying a CloudGuard agent onto the cluster, which reports information back to CloudGuard. On top of that, we will have to configure the admission controller component from scratch to create default access rules. For the sake of this session, we're assuming you already have a Kubernetes cluster set up, as this is out of this program's scope. To begin, we log into the Infinity portal and navigate to the Assets section under CloudGuard. Here, we need to connect CloudGuard and the Kubernetes cluster we wish to protect. We start by adding a new Kubernetes cluster environment. If this is the first time we're adding an asset, we'll get this Get Started screen. Otherwise, we'll add a new environment into the existing list of environments. We fill in a meaningful, unique name which will be used to identify the Kubernetes cluster within CloudGuard. Next, we create a new service account which will generate the account API key ID and secret. These will be used to identify the API calls from CloudGuard's implanted agent in the cluster to CloudGuard. It is important to keep a record of these details for future reference. Note that you can also use an existing service account. In such a case, you'll be using the API key ID and secret on record. Next, we fill in the Kubernetes namespace as defined in our target cluster. We make sure to mark the desired features we'd like to make available. Now, we choose the relevant organizational unit to associate with a cloud account. Organizational units help us view and maintain onboarded accounts according to logical groupings, such as business units or geographical regions. Next, we open an SSH connection to the designated Kubernetes cluster and paste the Helm commands from the instructions summary in the SSH connection. These commands deploy the CloudGuard agent within the cluster. Once done executing, the status will be deployed. Clicking the Next button will verify that both systems are synchronized. This synchronization means CloudGuard accesses the cluster through the agent to obtain information about the assets. To finalize, we hit the Finish button. This completes the deployment. We now have our CloudGuard workload protection deployed and synced with our Kubernetes cluster. Let's look at what we have here. Under Protected Assets, we can view the onboarded account's assets. CloudGuard fetches information about these assets from the onboarded cloud platform and presents it in a console view. CloudGuard monitors the security posture of these assets. Drilling down into a workload asset, we can view its protected processes, define exclusions to the default runtime protection rules, and find any special security findings and events related to the asset. Conversely, we can access the protected components through workload protection. Here, we can view and drill down into all containers being protected across the board. Under Image Assurance, we can locate the images being protected, view any detected vulnerabilities, and examine and modify the default policy and rules. Here, we can view and drill down into all the pod groups runtime protection is applied to across the board. Under Admission Control, we need to create a first-time rule set, as the deployment does not create a default policy. This process consists of 3 steps: adding an admission control rule set, adding rules to the rule set, and adding an admission control policy that binds the rule set to the cluster. Let's add an admission control rule to prevent services from being publicly exposed. Naturally, your use cases can differ depending on your architecture and business needs. We start by adding a rule set and naming it. Now, we add a new rule into it. When we click inside the GSL box, the GSL editor opens up. CloudGuard GSL, which stands for Governance Specification Language, is a simple yet expressive syntax to define rules, which can be included in rule sets in the CloudGuard compliance engine. The use case option covers the most popular scenarios for the admission control rule set creation. In this case, we add this pre-built rule. You can see the GSL syntax change as we further configure the rule. Finally, we verify the rule against the relevant environment and save. Now, we need to bind the rule set to the relevant cluster. So, we head out to the policies and either associate it with an existing policy or with a new policy. In our case, we'll create a new policy. After defining which entities it applies to, we need to choose one or two actions to take when the rule or rules within the policy are violated. Either detection, where the policy does not block events on the cluster but sends an alert notification, or prevention, where the policy blocks an event that violates it on the cluster and sends an alert notification. It's best practice to first use detection with new policies. If needed, you can configure multiple policies on the same cluster with a different action configuration. Finally, we define one or more notifications to receive when the policy is violated. In case synchronization fails during the deployment, check that the agents are in a ready state by inputting the following commands to your Kubernetes cluster, where namespace is your Kubernetes namespace. And there you have it. We've gone through the CloudGuard components protecting containers, as well as the easy and straightforward process of deploying this solution onto a Kubernetes cluster. In our next session, we'll explore the shift-left concept of protecting workloads during the CI/CD pipeline process before they are deployed. Thank you for taking this lesson. I hope you enjoyed it, and I'll see you in the next one. Welcome to this session on CloudGuard Shift Left. In this session, we'll explore CloudGuard's Shift Left solution for shifting security to the left and how it is deployed. By the end of this session, you will be able to describe why CloudGuard's Shift Left is needed and how it works, and you'll be able to perform a basic deployment of CloudGuard Shift Left. Now that we've discussed deployment and configuration of the various container protection components, which relate to runtime, let's discuss the importance of shifting left and how CloudGuard Shift Left enables this. Shifting left refers to moving security sooner in the development process. Instead of only protecting assets in runtime, shifting your security to the left preempts misconfigurations and vulnerabilities in your asset during the CI/CD pipeline process before it is deployed. CloudGuard's solution for shifting left is called Shift Left, and it brings the CloudGuard security abilities to detect and prevent risks in cloud deployments while in the CI/CD pipeline. Shift Left scans infrastructure as code templates for risk, checks software for known vulnerabilities, and scans container images for security issues. It also provides a single interface for multiple CI/CD security steps. Instead of being forced to fix in production, developers are notified of issues immediately. Shift Left runs a pre-configured security policy rule set or rule sets to examine the destination of choice, be it an infrastructure as code template, such as a Terraform template, the software being developed, and/or container images. Shift Left can be executed either on demand or automatically as part of the pipeline execution. The end result of executing Shift Left is a stop-go action in the pipeline. The pipeline's execution moves to the next step upon a Shift Left OK. And if everything passes, the pipeline is completed. Otherwise, depending on the instructions, the execution will stop, and the relevant developer will be alerted about the failure and its cause. With this in mind, let's take a look at the process of deploying shift left. First, since the shift left arguments refer to rule set numbers within your CloudGuard native security policy, you need to make sure your relevant shift left policies are set up and make it clear to yourself which rule sets you would like to run against the examined destination. Now, you need to decide how you would like to execute shift left in your CI/CD pipeline examination. You can download the shift left CLI tool from the CloudGuard native portal and run the desired commands locally and on demand to get a feel for how the tool works, or you can automate its execution in your pipeline tool of choice. Let's first focus on the on-demand shift left scanning. If you're intending to run the shift left tool, browse to shift left in the CloudGuard native portal and walk through the wizard. It will prompt you to download the shift left executable. You can download an executable for Windows, Linux, or Mac, plus a containerized version is also available at the Docker Hub repository under checkpoint shift left. Then, you'll need to generate an API key and secret to be incorporated into the API calls connecting between the shift left CLI to the CloudGuard backend. This is followed by a set of commands to make this information available to the tool via environment variables. Once done, you can go ahead and fire away desirable shift left commands to examine the posture of your protected assets. So, how does such a shift left command look like? In general, commands first need to address the destination blade, either the code scan blade, the image scan blade, or the IAC assessment blade. This is followed by the argument and the desired parameters supporting the argument. So for instance, we can scan an image with the image scan blade pertaining to the following command and parameters. R stands for the rule set. Alpine.tar stands for the image name to be scanned. And E stands for the CloudGuard native shift left environment, followed by the environment ID. If it is detected that there's a deviation from the rule set, the tool will list the reason or reasons. So, a possible result of our image scan could look like this. For a comprehensive list of arguments and syntax, please refer to the documentation page, Shift Left, using the CLI tool. To better understand the output of running Shift Left, and for automation of various usage scenarios, check out the complete list of error codes that might appear during the execution of Shift Left. This can be found on the documentation page, Shift Left Error Codes. Incorporating Shift Left automatically into the pipeline process would be the desired path of DevOps or DevSecOps in a real-world setup. This method requires a one-time setup on the desired automation platform. In the following example, our repository is hosted on GitHub, and the pipeline automation is performed via GitHub Actions by executing main YML. In this case, we're running a containerized version of the Shift Left tool, which resides on Docker Hub. Upon any change to a repository asset, a full set of Shift Left inspections is initiated on all three blades. Note that you will also need to incorporate the API key and secret into the YML configuration file by using repository secrets. And there you have it. Implementing Shift Left protection is pretty straightforward and flexible, and ensures you can preempt configurational errors or deployment of malicious code or images into your production, way before runtime protection is employed. In our next session, we'll explore the other part of the CloudGuard workload protection solution, serverless functions. Thank you for taking this session. I hope you enjoyed it, and I'll see you in the next one. Welcome to the session on CloudGuard Serverless Security. In this session, we'll take a deeper look at CloudGuard Serverless Security and how it is deployed. By the end of the session, you will be able to describe how CloudGuard Serverless Security works to protect serverless functions, and you'll be able to perform an initial deployment and configuration. As we know by now, serverless functions are single-purpose, event-driven programmatic functions hosted on managed cloud provider platforms. This allows for greater scalability and flexibility when performing various event-driven activities in the cloud, for instance, interacting with chatbots. Even though serverless functions run without a managed server, they still execute code. This means that vulnerable code can still be susceptible to OWASP Top 10 attacks. To help protect against malicious attacks targeting serverless functions, Check Point offers its serverless security solution as part of its workload protection suite. This solution analyzes your serverless application code before and after deployment, continuously scanning your serverless infrastructure code and runtime environment. It builds a model of normal application and function behavior by utilizing machine-based analysis and deep learning algorithms, including the automatic creation of an allow list of actions. It detects, alerts, and stops application layer attacks, such as the serverless OWASP Top 10 and other anomalous activities, with CloudGuard's function self-protection, also known as FSP. In this session, we'll be discussing the deployment of the solution onto an AWS account. So, how exactly does CloudGuard Serverless Security protect your AWS Lambda functions? I'm glad you asked. Protection happens on several levels, which are combined to make up the allow list policy. This includes static code analysis, runtime behavioral profiling, and user-defined rules and exclusions. Let's break it down before we roll up our sleeves and start deploying. Upon the onboarding of CloudGuard Serverless Security, static code analysis analyzes the serverless functions code and function configuration of the AWS account. It detects configuration risks and automatically generates least privilege function permissions. It outlines recommended steps for remediation, including recommended least permissive IAM privileges in JSON format. The security admin can just copy and paste this directly into the relevant IAM role policy. Whenever a change is detected in a function's code or in its function configurations, static code analysis kicks in to analyze, detect, and offer remediating actions where necessary. Function self-protection is a lightweight Lambda layer that sits on top of the target Lambda functions to profile their usage and ultimately block malicious attempts automatically. Once FSP is deployed, the solution enters its learning period, where it examines invocations of the protected functions. It analyzes the function's behavior to define a profile of what would be defined as a normal behavior. Together with the static code analysis, an allow list is generated automatically and is stored in a dedicated S3 bucket. Enforcing the allow list can either generate alerts in case of a deviation from the allow list, or conversely, proactively and automatically block any function invocations in runtime that deviate from the allow list while reporting it to CloudGuard's backend. When an invocation of the target function occurs, it first goes through the FSP layer, analyzed against the allow list, and only if it is approved will it pass onwards down the execution path. Otherwise, it is stopped at the FSP function. Finally, to complete the picture of how an allow list policy defines what is and what isn't legitimate use of the protected serverless functions, users can define specific rules and exclusions to rules in order to ensure that certain behaviors aren't blocked. For instance, If the function needs to access a text file which was not mapped during static code analysis or during runtime behavioral profiling, an exclusion can be added to the policy. Now that we understand the mechanism behind CloudGuard serverless security, let's roll up our sleeves and start deploying. In our use case, since we're deploying to AWS, we'll be talking about an AWS-oriented deployment. The overall process consists of the following steps: onboarding a designated AWS environment into CloudGuard native, enabling serverless security, enabling runtime protection, and creating exclusions and rules. First, we need to onboard an AWS environment into CloudGuard native. CloudGuard native has two operation modes for managing AWS accounts, either read-only or full protection. Read-only allows you to monitor and examine AWS accounts within CloudGuard. Full protection, on the other hand, has a more proactive level of enforcing access and tamper protection on your AWS assets, managing security groups, and controlling direct access to your cloud assets. There are a few methods to perform onboarding, from a step-by-step process using CloudGuard and the AWS console, to automating the process using batch scripts, Terraforms, and REST API calls. In our case, we'll focus on onboarding from the CloudGuard portal. To begin, we navigate to Environments and add a new AWS environment. Now we need to select an operation mode. In our case, we'll use Full Protection. The next steps involve following the CloudGuard wizard, which instructs you how to prepare an IAM policy in the designated AWS account, granting appropriate permissions to CloudGuard to access the AWS account for information about resources. Additionally, it details how to create an IAM role in the AWS account to be used by CloudGuard to access the cloud account using the IAM permissions defined in the previous step. Let's assume we've performed these easy and straightforward steps listed in the wizard, and we've arrived to this summary screen. Based on the number of entities in the AWS environment, the process may take a few minutes to complete. This completes the onboarding process. Once fully onboarded, you can view your AWS environment and its status. Now that things are onboarded, let's enable serverless protection. To enable, we navigate to Environments and choose Enable Serverless Protection. Now we create a cross-account role. After acknowledging, we create a stack. After the stack is created, the additional permissions are granted to CloudGuard, and CloudGuard completes the process of enabling protection. When this is complete, as indicated in the CloudGuard wizard, you can see the serverless functions in the protected asset list for the account in the Protected Assets page. You can now examine the static code results and the posture findings generated from the scan. Now it's time to enable the runtime function self-protection to allow the comprehensive protection that is expected from CloudGuard. To enable, we navigate to the Serverless Functions page. We select the desired function from the list. Now we switch Auto Protect on. The profiling will commence and will complete the allow list. Since we'd like to block malicious actions that are not in the allow list, we toggle on Block on Detect once Auto Protect is done applying itself. Finally, let's define an exclusion which will manually add access in the allow list to an allowed asset, in this case, text files under the logs directory. First, we select our target function and navigate to its Rules and Exclusions tab. Then we create a new exclusion and select its target, in our case, a file. Now we enter the exclusions pattern, which is a string or a set of strings that matches against actions. If an action matches a pattern, it is added to the allow list and excluded from further inspection. In our case, since we're matching text files under the temp logs directory, We use this pattern. Finally, we select the scope this exclusion applies to, a specific function, a group of functions, or the entire set of functions in the environment. And there you have it. We've gone through how CloudGuard can protect your serverless functions, constantly analyzing and profiling the behavior of the function components, providing built-in function self-protection. And we've examined an implementation of CloudGuard serverless security in AWS. If you'd like to enhance your knowledge on implementing this solution on other platforms, such as Azure, please refer to the product documentation. Thank you for taking this session. I hope you found it useful, and I'll see you in the next one. Welcome to the session on CloudGuard AppSec. In this session, we'll take a deeper look at CloudGuard AppSec and how it is deployed. By the end of this session, you will be able to describe how CloudGuard AppSec works to protect cloud-based web applications and APIs, and you'll be able to perform an initial deployment and configuration for both application security and API protection. Web applications are programs that are accessible to users via a web browser. Organizations can use APIs that allow programmatic access to their web applications or underlying services supporting applications. As organizations shift to the cloud, they also shift the services required to build and access such applications. As we've discussed earlier in this program, assets in the cloud, such as applications and APIs, have an increased attack surface. This, together with the sheer speed which they are developed, deployed, and updated, can lead to increased compromises and vulnerabilities. Traditional rule-based web application firewalls, also known as WAFs, are simply insufficient in protecting the increasingly complex cloud-based web applications. At the core of this incompatibility is the notion that any solution requiring manual tuning of application security will never match the pace of development and deployment of applications in the cloud. This is because traditional WAFs are based on static rules, whereas the process of development and deployment of cloud-based web applications is more dynamic than ever. Adding to this dynamic is the fact that cloud-based web applications interact with potentially numerous third-party services outside of the perimeter. In effect, there are now hundreds of perimeters to secure. Finally, there's a major issue of privilege escalation in the cloud, which is not properly addressed by WAFs. Attackers that infiltrate an application will look for API keys to other applications or resources. Due to poorly configured role-based permissions, remote code execution can be much more harmful in the cloud. Here's a quick example of a vulnerable cloud-based web application which displays power meter readings. A hacker performs a SQL injection directly to the web application from the browser to zero his electricity bill regardless of his consumption. Later, he figures out that he can actually make the system work for him and pay him for consumption instead of the other way around. Using a local application he developed, he attacks an API used by the web application, reversing the charge. These kinds of attacks are relatively easy to commit for hackers who face weak protection in the form of traditional cloud-based WAFs. The better alternative to rule-based binary WAFs is CloudGuard AppSec. CloudGuard AppSec enables automated deployment that requires no rule tuning. It relies on the concept of application self-protection powered by a contextual AI engine. CloudGuard AppSec can stop application layer attacks, including OWASP Top 10, with little to no manual tuning or false positives. It can stop unauthorized API access and abuse without breaking applications and frustrating users. It can identify and stop malicious bots before they can negatively impact the customer's experience. And it can catch any HTTP-based CVEs and known vulnerabilities. AppSec relies on several mechanisms to provide its top-of-the-line protection: contextual score-based decision engine, continuous learning, Open API schema validation, bot identification, and IPS protection. Let's face it, no customer trying to access a website would be happy with being blocked due to a false positive on the website's end. This is critical to any business or service delivered via a web application. AppSec uses contextual analysis, which combines the risk analysis of multiple engines to determine if the transaction with a target application is legitimate or not. Those engines include a transaction risk engine, which breaks the transaction into small elements called attack indicators, which are then examined by a dedicated machine learning algorithm to make the decision to block or allow. Additionally, AppSec uses a user behavior risk engine, which analyzes all of the requests made from a specific user, looking into malicious intent in prior user requests. You can take this one step further by creating an allow list of trusted users, which accelerates the application learning. Furthermore, the crowd behavior risk engine maps a site based on how all users interact with it. If a critical mass of users uses a website a certain way, the probability of a request being a specific attack is lower. Finally, the content risk engine learns what content is typical for a specific field in a specific application, providing a deeper analysis of the content itself and the patterns that are expected in each field. The final score reached by the decision engine is either to allow the transaction through to the application or to block it. This while dramatically minimizing false positive decisions. Before the engines kick into action, the system begins in learn detect mode. In only a short period of time, it completes its learning and the user can choose to switch it to prevent mode. Behind the scenes, the system gathers raw data on the transaction sources, their HTTP methods, the type of HTTP requests, and their headers. This information is all parsed and fed into the aforementioned engines for analysis. When the system completes its learning, the user can choose to switch it to prevent mode. This process of gathering data, parsing it, and feeding it to the engines is performed on a continuous basis. A user can assist the learning process and shorten the learning curve by responding to tuning suggestions. For example, this user assistance is called supervised learning. AppSec narrows the scope of API attacks by allowing API schema validation. Users can upload their schema, which describes the API functionality of the server. AppSec then makes sure to enforce this schema by ensuring that no one can infiltrate applications via API fields and values that are not explicitly allowed in the schema. The use of bots for automated attacks against login pages is a regular practice among threat actors. CloudGuard AppSec utilizes client-side behavioral analysis to distinguish between human behavior and bot behavior. Once a client connects to a server, it performs a GET operation. It receives the page from the server, including a JavaScript developed by Checkpoint that is injected to the browser of the client. The script collects behavioral information from the client. When the client performs a POST operation to the server, it will include the decision of the script, which defines if the request originated from a bot or from a human. Finally, the IPS protection offered by CloudGuard AppSec is complementary to the protections already discussed. AppSec IPS protection, which is based on Checkpoint's award-winning Gateway IPS protection, catches any known vulnerabilities, preventing known malicious CVEs by looking for network signatures in HTTP requests. Now that we know what CloudGuard AppSec can do, let's focus on its possible architectures and deployment considerations. There are currently 3 available types of deployment, which can accommodate various implementation scenarios. It can be deployed either via the CloudGuard AppSec Gateway as an embedded nano agent on top of any Linux machine running an Nginx web server or an Nginx reverse proxy, or as a nano agent Docker container. Let's elaborate. When implementing AppSec via the CloudGuard AppSec Gateway, we have a CloudGuard AppSec Gateway virtual machine deployed in front of the web server to be protected. It runs on a Checkpoint Gaia operating system as a secure OS with an Nginx reverse proxy and an AppSec Nano agent, which is the core of the solution. In this deployment scenario, NGINX is managed from the Infinity portal by the user. AppSec can also be deployed as an embedded Nano agent on top of any Linux machine running an NGINX web server or an NGINX reverse proxy. The Nano agent attaches to the NGINX as a standard plugin and provides CloudGuard's AppSec features. This type of deployment can take shape in two ways: either as an NGINX web server where both protected web app and the Nano agent reside on the web server, or as an NGINX reverse proxy where the Nano agent resides on NGINX. In this case, the NGINX reverse proxy is set up in front of the protected web app. Alternatively, AppSec can be deployed as a Nano agent Docker container, either on top of an NGINX Ingress controller within a Kubernetes Ingress pod, or on top of an NGINX reverse proxy Docker container. These solutions are also deployed in front of the web application to be protected. For the sake of simplicity, we'll focus this session on deploying AppSec as an embedded Nano agent on top of a Linux machine running an NGINX reverse proxy. Before we go over the deployment process, let's break down the elements that enable the AppSec solution. First, we have the what. What are we protecting? This is referred to as assets. An asset maps to URLs of websites. Then we have the how. How is this protection being applied? This is based on the selected deployment profile, which we'll elaborate on in a minute. The deployment profile includes a built-in security policy which is applied on the protected assets and defines the expected behavior for a set of AppSec security engines. Finally, we have the by whom. Who is in charge of enforcing the policy? The answer is AppSec's Nano agents. These Nano agents are services which implement security monitoring and enforcement based on the defined policy and the assets they're attached to. Now, let's define the high-level deployment process of our chosen scenario, providing application security and API protection using an embedded Nano agent on top of a Linux machine running an NGINX reverse proxy. First, we define the AppSec policy. Then we deploy the Nano agent. And finally, we can create exceptions and additional definitions on the Infinity portal's end to accommodate any special requirements that go beyond the default settings. Let's break it down. Defining the AppSec policy includes defining the assets we wish to protect and the type of agent deployment we wish to implement. Policy practices will be automatically populated with Check Point's best practice defaults at the end of this process. This policy will be enforced by the Nano agents. In our use case, since we would also like to protect web APIs on top of applications, we will need to upload an API schema to enforce the API calls being sent to the application. Next, we deploy the Nano agent. In this step, we install a Nano egg on the target Linux NGINX machine. The Nano egg is a binary that creates trust between the protected asset and the Infinity platform in the cloud. The Nano egg then deploys the relevant Nano agent services based on the policy and the environment on which it is installed. Finally, we can create exceptions and additional definitions in the Infinity portal to accommodate any special requirements that go beyond the default settings. All right, it's time to deploy. It is assumed that you already have a Check Point Infinity portal account set up at portal.checkpoint.com and that you have an NGINX reverse proxy set up as the target Linux machine, as this is beyond the scope of this session. Let's first start with the solution's front end. We log into the Infinity portal and open CloudGuard Application Security. Next, let's add an asset of type Web Application. For ease of use, we can start this from the Getting Started screen. After our Web Application asset is set up, we will do the same for Web API protection. In the wizard, we define our target for protection. We name it, define its zone if it is part of a group of assets, define whether it's in the stage of staging or production, and finally in this step, we add the front-facing URL for the web application. Now we choose the type of practice to apply to our target. This represents the type of policy to enforce. In order to train the engines to detect legitimate traffic versus malicious traffic, it's best practice to keep it on Learn Detect until learning has progressed sufficiently to recommend the move to prevention. The amount of time for this process varies by the number of requests sent and whether trusted users have been defined, but more on this later on in this session. As discussed earlier in this session, part of the learning process involves profiling user behavior. For that to happen, AppSec needs to distinguish between users. One way of doing this is by their differing IP addresses. To ensure their original IPs are forwarded to AppSec, instead of any IP address of an intermediary machine along the way, such as a proxy, we choose this option. We can also help the engine by identifying ahead of time source IPs that are unlikely to be malicious. This helps accelerate AppSec's learning phase. Now we define a deployment profile. We can either choose a profile we've previously created or create a new one. Since in this case it is a first-time configuration, we'll opt for creating a new nanoagent profile to be deployed according to our selected implementation. That is, a nanoagent within an Nginx reverse proxy set up as the target Linux machine. In the wizard summary step, we can publish the application security policy and enforce it. Publish saves changes to the database, and enforce means the policy changes are ready to be picked up by its target, similar to install policy on a gateway. Our web application asset to be protected is now set up in the front end. Now, we proceed to deploy the nanoagent. First, we navigate to our profile in question. This will be our source for establishing the trust between the nanoegg installed on the target asset and the Infinity platform. Now, we open an SSH connection with a target machine. Once established, we can copy the commands from our profile in the front end to establish the connection with the Infinity Portal backend. This will be preceded by the fetching of the nanoegg, its installation, and its automatic download and installation of the nanoagent components from the backend, while also fetching the policy. This is all done while using the system-generated reusable token. At the end of the process, a success message should appear in the command line window. To check that the agent is up and running, we run the command cpnano-s. A message will also appear in the portal indicating that the agent has connected successfully. This completes the nanoagent deployment, which means application security for our target asset is active. Now it's time to set up API protection. As mentioned, AppSec provides open API schema validation, ensuring that no one can infiltrate applications via APIs and fields that are not explicitly allowed in the schema. We start by adding an asset of type Web API. We make our way through the wizard in a similar fashion to what we previously did for the web application security. We can use the previously created agent profile or create a new one. In our case, let's use the existing one. Once done, it's time to upload the Open API schema. Under the Threat Prevention tab within our asset, we hit the Upload button and select our schema. Finally, we publish and enforce. Now, let's briefly explore various nooks and crannies of the system where we can find some interesting insights. Naturally, navigating to the various sections here will provide us with information on the various entities we've set up. Under Agents, we can view the list of nanoagents that are configured to work with our deployments. As we can see, the status of this agent is connected. Beyond that, we can access the AppSec Monitor, which provides us with rich data concerning incidents handled by AppSec, including attack sources, the timeline of attacks, and the assets that have been attacked. Events displays a list of incidents. In case you'd like to customize your AppSec policy, you have various ways to do so. For instance, adding an exception to the policy which blocks requests from a certain source IP. Based on parameters defined here, when there is a match, the agent will operate according to what it's instructed to do here, overriding any AppSec engine-defined criteria. You can further narrow down or broaden the scope of exceptions by adding behaviors. In terms of best practices, we've already mentioned the learning period, which is the period during which the AppSec engines gather and analyze data to build adequate profiles. After this period is over, the system provides us with a recommendation to switch to prevention. Following that recommendation, we can go ahead to the Assets Threat Prevention tab and switch the mode to Prevent. For additional best practices, please refer to the AppSec Best Practices section in the Infinity Next Administration Guide. And there you have it. We've gone through how CloudGuard AppSec can protect your cloud web applications and APIs, utilizing sophisticated AI-based engines which learn to detect normal versus anomalous behavior, constantly analyzing and profiling the behavior of incoming traffic to the protected assets, providing in essence an application self-protection, which requires no manual tuning. We've detailed a deployment scenario of an embedded nano agent within an Nginx reverse proxy running on a Linux machine. We also mentioned various other forms of deployment depending on the environments you operate in and your protection needs. If you'd like to enhance your knowledge on implementing the solution, please refer to the Infinity Next Administration Guide. Thank you for taking this session. I hope you enjoyed it, and I'll see you in the next one.
Welcome to this program summary session. In this session, we'll briefly summarize what we've seen and learned in this program, as well as provide some references to resources to further enhance your knowledge.
In this program, we presented the major threats and vulnerabilities that are amplified when protecting workloads and web applications in the cloud. We went through some common solutions addressing these security challenges and established that in many cases they are insufficient. We then presented Check Point's dedicated solutions for protecting cloud workloads and web applications that fall under the CloudGuard umbrella. We discussed the major advantages of protecting cloud assets via CloudGuard Workload Protection and CloudGuard AppSec, and how they provide robust protection using advanced technologies such as machine learning and AI to provide the top-of-the-line protection while demanding little maintenance and tuning. We learned how CloudGuard Shift Left can help us complement runtime security by shifting security to the left and into the CI/CD pipeline to preempt any vulnerabilities and misconfigurations during the development process in the cloud. And finally, we walked through some basic deployment scenarios involving CloudGuard's container, serverless, shift left, and application security solutions. To further enhance your knowledge, please refer to the respective solution documentation. Additionally, if you're not already a member of the rich and dynamic community of Checkmates, where you can find the latest tips, tricks, and deep dives, you should definitely check it out.
And with that, our program has come to its end. I hope you found it both useful and enjoyable. Thank you for participating, and good luck.
Hello and welcome to Quantum Spark Jumpstart Introduction. This is one of my favorite products, Quantum Spark, and this series is a Jumpstart program, meaning you have this wonderful product at your hands and you want to know how to get started with this product, how to efficiently protect your organization with this solution. Well, you've come to the right place, because by the end of this training, you'll be able to deploy Quantum Spark within your organization and start to efficiently protect your organization. We'll also perform some administrative tasks within Quantum Spark, for example, VPN, management options, meaning how do you want to manage your device, locally from the box, from a different box, or maybe from the cloud, how to set up wireless network, how to get updates, how to configure and modify your security policy, how to run upgrades, troubleshooting, and of course, monitoring. So we're going to have a lot of fun together. So Quantum Spark is an appliance suitable for the small and medium business. Because if you have a bigger organization, you might go with one of our bigger appliances. It depends, for example, on the throughput and the blades you want to enable. So Quantum Spark is right here. And if we will zoom in on the small to medium businesses appliances, we can see these beautiful appliances. For example, the 1535, which can support up to 440 megabit per second and supports Wi-Fi 6, and up to the 1595, which can support 900 megabit per second, Wi-Fi 6, and a 5G network. Amazing. Quantum Spark, what a solution. I really like the definition of Spark. It's an enterprise-grade security for small to medium-sized businesses. All-inclusive security, next-generation threat prevention, application control and URL filtering, IPS, antivirus, anti-bot, anti-spam, sandblast, threat emulation, which you might know as sandboxing. It provides the same level of security as a quantum gateway. It's integrated with Wi-Fi 6, which is new and exciting, XDSL, and cellular traffic with the latest 5G network. It is easy to deploy and manage, and it's a real all-in-one solution. You have on-the-go real-time security alerts and remediation using the Watchtower mobile app, which will have a great video on it. You get simple and insightful reporting. And look at this beautiful throughput, 2.8 gigabits per second firewall, 900 megabits per second of threat prevention, and perhaps the crown jewel, Quantum SD-WAN support, so you get optimal app performance. So during the demos, I'm going to use this topology. This is my home network, so I have my home router at the end. It's an ISP router, it's a dumb router, so every traffic it gets, it just forwards it back to its destination. During the demos, I'm going to use a real live topology. It's going to be connected to my home router at home. It's a dumb ISP router, meaning no firewall rules or special configuration, just your out-of-the-box ISP router. The network it's managing is 192.168.1.0/24. It's a Class C network. On this network, I have my own PC, which I'm going to use to manage it all. That's going to be my admin machine. I have a PBX server, which will allow me to conduct voice over IP calls within my network. I have a VoIP phone on my network as well. I have an Active Directory server running Windows Server. So I'm going to use it to create users and then integrate it with my Quantum Spark, which is right here. I have a Quantum Spark device, and it also hosts its own private and protected network behind it with one PC. The structure of the course is going to be very simple. I'm going to start with a brief introduction like this one. This one is some sort of introduction as well, but it's going to be an introduction per the topic we'll discuss, followed by a demonstration, so you'll know exactly how to get started with your appliance. So it's going to be cool, and most importantly, it's going to be real, because I have a real device. I'm going to install it. No smoke and mirrors. You're going to get the real appliance out of the box and installed to give you the best security, because you deserve the best security. So without any further ado, or actually you may pause the video, because you can pause the video, but anyway, let's get started. Installation. By the end of this training, you'll be able to install the operating system as a VNF and run the first time wizard. If you want to play with Quantum Spark, you can either use it as an appliance, a physical device that's right in front of you and you can actually hear it and touch it and smell it, if that's what you like, or you can use it as a VNF, meaning as a virtual machine. The operating system is going to be Gaia embedded. It's slightly different than the regular Gaia you all know and love. If you're using an appliance, then the operating system is pre-installed, meaning you plug it in, the operating system is already running. But if you're using a VNF, you'll need to install the Gaia embedded yourself, which is actually really easy, so you don't need to worry about it. First time wizard is something you'll need to do on both appliance and VNF. This is the product installation, so you'll select if you want to manage this device directly or maybe from a dedicated management server. You'll set up the credentials and access to the device. You'll enable the blades you want to have. Networking settings, for example, if you want to get an IP using a DHCP, or maybe you're going to add it statically, and so on. Set up zero touch, or actually that's the time to use zero touch if you've configured that. And also, if you have internet connection, you're going to obtain the license automatically. If not, you can do it offline or just set it up later as well. So all of these settings will be configured during the first time wizard. During the demo, we'll do two things. One, we'll install the VNF. If you want to use the VNF, you need to either have the ISO or maybe the OVF file if you're using VM Workstation, and some sort of virtualization software. In this case, I'm going to use VMware Workstation. For the first time wizard, you'll need to be familiar with the network topology you're using, so you'll know where to plug it in, which IP address to use, and so on. You'll need a browser, and you will need an Ethernet cable. So this is my topology. I'm going to connect my admin machine directly to the LAN 1 network, so I can go ahead and get an IP address and start managing the device. And actually in this demo, I'm going to connect my appliance using a SIM card to the internet using the cellular data package and not directly to my home router, just for this demo. To install Quantum Spark as a VNF, I'm going to SK 168204. And down here, I can see the available downloads, so either as OVF files or as ISO. And I've already downloaded this file. I'm going to download it again. So you get a TGZ file, I've extracted it. And now from VMware Workstation, in my case, I'm going to open a virtual machine. I'm going to browse to the location of the OVF file that I've extracted. Give it a name. Location is fine. Import. I'm going to edit the virtual machine settings. By default, I have two network interfaces. I'm going to modify them and place them on a different VMnet. And I'm going to add a third adapter. Now, I still don't know which interface is which, meaning I don't know if this is the WAN adapter, if this is the DMZ adapter, I don't know. So I'll turn it on and then we'll know together. Press OK. And power on. In this specific VNF, I was using an OVF, so the operating system was already installed. And now I can just log in with admin. Default password is admin again. And now I have access to Clish and I can go ahead and do whatever it is that I want. I can change the adapter, IP address, I can change the host name, whatever it is I want to do. Now, I do want to know the interface's assignment. So I'm going to set up expert password. I'm going to enter expert mode and I'm going to display the MAC addresses just so I can know which interface is which. Okay, so now I can see DMZ, LAN 1, and WAN, and I can see the MAC addresses. So what I'm going to do now, I'm going to access the virtual machine settings. And I can see the MAC address of CC is network adapter 1. So network adapter 1 is DMZ. So I'm going to place it on VMnet 3. Second adapter is D6. D6 is the LAN 1, so I'm going to assign it to, I don't know, VMnet 1. And the last one, E0, that's the WAN adapter. So in my case, I'm going to modify this to NET. And that's it. I've successfully installed a VNF. To run the first time wizard, I need browser access to the appliance. So I'm going to take my admin machine, connect an Ethernet cable to the port. Now in this case, the appliance is running as a DHCP server, so I'm going to obtain an IP address automatically, and I'll know the address of the device is something something something.1, and if not, I'll show you how to check it. And then you'll need to open up a browser session, https:// the IP address of the appliance, which you'll need to figure out. But it's not going to use the regular port for HTTPS, it's going to use port 4434. Okay, so let's see it. So here I have all of my network adapters. This is the adapter that's currently connected to the appliance. So I'm going to the status, details. So the IP address that I'm getting is 192.168.1.224. My default gateway is 1.1. So that's the IP of my Quantum Spark. I'm going to open up a browser, type in the IP address 192.168.1.1:4434 and press enter. So the connection is not private because the appliance is presenting me with a certificate that is self-signed, so I'm not aware of that certificate. I'm going to go ahead and approve. And this is the first time wizard. Now, currently I don't have zero touch, so I'm not going to be able to use that. I'm going to set up next the administrator name and password. So I'm going to stay with admin, but I will change the password. I don't want password complexity, so I'm going to leave that unchecked. Help us improve. Yeah, sure, why not? Press next. Date and time. It's okay. I'm not using a network time protocol, so I'm going to leave that off. Press next. My appliance name, I'm going to change it. I don't have a domain. I'm going to manage my device locally, and we'll elaborate on it on a later video. But basically it means I'm going to manage the device and policy by using the local web application. Unlike if you're going to use central management, it means you have a dedicated management server to manage this box. But I'm going to stay with local management. How would you like to obtain internet access? In this case, my internet access is not over a DHCP or an Ethernet cable. It's actually using cellular. So I have my SIM card in. I'm going to press connect. And of course, if you want, you can always configure internet connection later. I'm connected. Here's my IP address. Press next. Now it asks me, how do I want to configure the LAN network? So I'm going to configure the LAN network to be actually .2, like so. The subnet mask is fine. The DHCP is being calculated automatically. I don't have an exclusion range. Press next. Now this setting right here is very interesting. How would you like those 8 ports to behave? Meaning, if I enable this, those 8 ports are acting as a switch, meaning they're all connected to the same LAN network. However, if I'll uncheck it, I'm currently only configuring port 1. So if I'll have another computer connected to port 2, that's going to be an entirely different network. So you can go ahead and modify this now or later. In my case, I'm going to set it up as a single network. Press next. In this window, it asks me if I want to set up the wireless network. Currently, I don't want that. I'll configure the wireless network later. How do you want the administrator to access the device? I'm going to allow the administrator to access the device from any connection and from any IP address. Of course, if you want better security, you can go ahead and modify it, but in this lab, I'm going to leave it as following. It's going to register my appliance. I do have internet connectivity, so this should work, and I have obtained my license. Which blades I want on, I'll use all of them. And that's it. Here's a summary. I'm going to go ahead and approve it. I'm done. I have my appliance running and ready. Web UI Overview. By the end of this training, you'll be able to log in to the Web UI and describe the functionality of each tab. The Web UI is a web application, so you'll need a browser if you want to use it properly. And basically it means that you're going to use a PC to connect over HTTPS to your Quantum Spark. And notice that by default, we don't use the classic port for HTTPS, but port 4434, just because it's more secure this way. From this Web UI, you'll be able to manage the device itself and configure the security policy. So unlike the classic architecture where you use the Gaia Web UI only to manage Gaia as an operating system, when you're using Quantum Spark, you're using the Web UI to do both device configuration and security policy. These are the main tabs from within the Web UI. So you have in home mainly overviews, device. This is mainly device configuration like IP addresses, network addresses, upgrades, and so on. Things related to the access policy, the threat prevention policy, VPN connections, if it's site to site or from a client or from an application, user and objects, and finally logs and monitoring. If you're ever feeling lost, from the home page under overview you have the sitemap. In the sitemap you have all the different links simply laid out, so you can easily find whatever it is you want to do. And of course you can always just go to the previous page and search for the option you want. But some people like this display, so it's here as well if you prefer it. For this demonstration, you will need connectivity to your Quantum Spark, and you'll need to know the credentials of the appliance so you'll be able to log in and do your stuff. Here's my appliance, so I'm currently at the home page. So here under system, I see the system information, my version, the device name, the MAC address, my uptime. Network, I can see that I do have the internet connected. I'm currently connected over cellular. This is my IP address. Wireless networks are turned off. In this case, I have dual channels. The Watchtower mobile app, currently I still haven't set it up, but I can set it up from here. Network activity here below. Notifications. So for example, earlier today, I've set up a test. So I see the malicious file was indeed blocked. Security dashboard. I can see the different blades. I can see that they're enabled, and I can go ahead and modify them from here. Security management. So we'll talk about this in a different lesson, but currently my device is locally managed, meaning I'm managing everything straight from this box, from the Web UI, but I can go ahead and change central, and then it means I'll manage this box from a security management server. Here you can configure a cloud service provider that can handle your security policy and supply a variety of services. Yeah, I just read it from here. But in other words, for example, if you're using Spark management, you can set it up from here. And we'll do this in a later video. License. So you can see the services that I'm using, my MAC address, my registration key. Currently was activated automatically. So for example, a few months ago, I had to modify my license. So after I've modified my license, I've just clicked reactivate, and it pulled information in again, and it got the update that I have a different license. Or of course, you can do it offline as well. This is the sitemap that we've discussed earlier. The monitoring tab, so I can see the notifications, the active devices that are currently connected to my device, monitoring information. Okay, so I can see all of the different applications that were being used. So this is quite nice. I can see checkpoint IPsec. It's because my computer is connected over a VPN, so I have that traffic. Different reports. This is a really nice report that you can generate. Tools, we'll talk about this in a later video, but this is troubleshooting tools to get insights or to run diagnostic tools. And support information. Moving on to device. So as we mentioned, this is where you manage the device from. So you have network settings, like for example, if you want to set up the wireless network, set up the local network. And we've discussed this in a previous video where you can go ahead and configure how the device will behave. Will it act as one big switch or as separate LANs? So you can customize it from here as well. System operations, you can go ahead and run upgrades, set up administrators, the administrator access, and you have lots of information here. Advanced routing, this is actually really cool. Certificates, high availability settings, and so on. Access policy, everything related to your security policy, but we'll discuss this in a later video. Threat prevention, everything related to threat prevention. For example, IPS, antivirus, anti-bot, threat emulation, they're all enabled and up to date, which is important. And I can see the policy that's being used. VPN. I currently don't have any VPN sites, but in the future, we'll set it up straight from here. Users and objects. So in a later video, we'll connect our Quantum Spark to Active Directory. So we'll be able to pull information about the organization from Active Directory. And finally, logs and monitor, which gives you great insights about what's going on within your organization.
Thank you for watching, and I'll see you in the next video.
Policy out-of-the-box state. By the end of this training, you'll be able to describe the out-of-the-box state of Quantum Spark and review current policies. So right after First-Time Wizard, you are protected. Out of the box, you've completed First-Time Wizard, you're already protected. Because if you'll take a look at the policy, you'll see that by default, you have the standard policy. Now, unlike the classic firewall architecture when you're using Quantum Firewall or Quantum Gateway, there, the default policy is any drop. But this is an SMB device. It's Quantum Spark. So it's ready to protect you. Okay? So the default policy is to allow traffic to the internet on all services, allow traffic between internal networks and trusted wireless networks, block incoming traffic, and as for application control, it's going to block security risk categories. So right out of the box, you'll be able to go to the internet, you'll be able to access other internal networks in your organization, but any random incoming traffic, and we're not talking about replies to your traffic, this is just someone trying to access your internal network, that's going to be dropped. Let's have a look. So if you want to have a look yourself, make sure you have connectivity to Quantum Spark and that you have the right credentials for the appliance. So here I am on my appliance. You can see it's the Quantum Spark 1590 appliance. And here under Firewall Policy, I can see indeed everything we saw on the slide. And if I'll go to Policy, I can see the actual policy in a well-known and lovable format and a rule base. So I can see outgoing access. I have any source to internet destination, and if the application or service is undesired applications, and I can double tap, and I can see which are those unwanted or undesired applications. I can see that it will be blocked with a log. Next, I have the any to the internet on any service except with no log. And then I'm going to have the incoming. If it's someone from within the LAN networks to any destination on any service, yes, they can do whatever they want. Anything else, that's the classic cleanup rule. So these rules are auto-generated. It's similar to the auto-generated rules you have with NAT when you use classic quantum. Okay, so it's good as is, but if you want, you can always go ahead and add a new rule and customize it to look however you want your security policy to behave. You can go ahead and modify and add additional rules.
Thank you for watching, and I'll see you in the next video.
Policy customization. By the end of this training, you'll be able to modify firewall and application control policy and create a manual rule. The basics of a policy is any traffic can be categorized into its own source, destination, and service. So for example, I can say any traffic coming from any destination can be my DMZ, for example. Service can be FTP. So whenever traffic comes in and we can match it to a rule with these categories, we have an action. The action can be drop or accept. As we saw in a previous video, you already have default rules to protect your organization. However, in this video, we'll see how to customize it and add more rules to your policy. In order to demonstrate this, you'll need access to your Quantum Spark, you'll need to have the right credentials, and you'll need to know what's the organization's network and security needs. Do you want to block that website? Do you want to allow that website? And so on. Here I am from Access Policy. I'm going to enable block file sharing applications. And let's press Apply. I'm now connected to a new client, which is protected by a Quantum Spark, meaning all of my traffic here goes through Quantum Spark. Let's try access Dropbox. The site can't be reached. Now let's try to access WeTransfer. Blocked as well. So currently, this rule that I've enabled blocks Dropbox as well, because it's a file sharing application. I'm going to Policy. Let's refresh this page. So now if I'll go to Undesired Applications, I have file sharing applications as well. Now, I want to override it. So yes, I want to block file sharing application, but Dropbox is a website that I do want to use. I do want to allow that website. So I'll need to override this. I'm going to create a manual rule on top. Source, let's have it specific from our LAN networks. Destination is internet. An application, let's search for Dropbox. Accept, keep a log, no need to modify any of that, press apply. Okay, now let's go back to the Windows client machine. Refresh. And now it works, because now I've added a manual rule to allow that specific traffic. In my case, it was Dropbox, but you can go ahead and add whatever traffic you want to allow within your organization. Thank you for watching. Policy Smart Excel. By the end of this training, you'll be able to enable Smart Excel and customize Smart Excel. Have a look at this list. We have Apple, Checkpoint services, Google services, Microsoft updates, media streaming services, Amazon, Disney Plus, and Netflix. Now, can you think of what ties them all together? They're all at low risk because we're talking about traffic from Apple, from streaming services, from Google, from Microsoft. So they are currently low risk. Smart Excel is a beautiful feature that we have that will bypass these low risk services and will give you better performance. So in other words, it means you can bypass the network inspection for these specific objects. Services such as those corporate services, media streaming services, and so on. Assets, so devices such as computer, audio player, or alarm can be bypassed. This improves connectivity and optimizes the load on the Quantum Spark Security Gateway. To go ahead and utilize this tool yourself, make sure you have connectivity to Quantum Spark, make sure you have the right credentials, and the organization's network and security needs. Because I assume your organization, for example, uses web conferencing applications. So in that case, you would like to have that service bypassed. However, in some organizations, streaming is forbidden from within the corporate network. So you don't want to bypass, you just want to block that, right? To enable Smart Excel, simply go to Access Policy, Smart Excel, and currently it's on. You can just tap it, set it to off, or turn it on again. If you want to customize Smart Excel, you can click the All Services selected and select exactly what services you want to accelerate or not. For example, I can go ahead and remove TikTok or Skype or WebEx or Zoom and whatever you like. So very easy to turn it on, very easy to customize it. And if you want to see the assets, this is here under Policy Bypass. You can just turn it on. And then again, it can bypass specific assets within your network, like alarm clocks, audio players, and so on.
Thank you for watching, and I'll see you in the next video.
Voice over IP, or VoIP, is a key element in an organization of any size. No need for the classic PSTN infrastructure. All you need is TCP IP. And since in between the networks we have a security gateway, we will need to allow this traffic in the policy. In earlier version of Quantum Spark, you had to manually add the rules and create a network object for the source and the destination. And it was a long and painful procedure. Although we have a very detailed SK about it, it was just very detailed. Very detailed. Worry not, my friends. In version R80.20, we have released a new VoIP wizard, which will guide you through creating the right rules based on your topology. Simple and easy to use. First, let's review our topology. We have our Quantum Spark connected to the WAN network, in this case, the 192.168.1.0, which is my physical address at home, and the Quantum Spark WAN adapter is connected to this network. We have the 192.168.100.0 network. It's a wired network protected by Quantum Spark. And since it's the 21st century, we have a wireless network as well, secured by our appliance. We have phones on all three networks. The PBX server is in the WAN network. As you know, Quantum Spark offers out-of-the-box security. So if we'll check the current policy, it will only have these auto-generated rules, and incoming traffic to the Quantum Spark device will be dropped. Here I have a soft phone app, and I'm initiating a call to a client which is behind the Quantum Spark box. And as you can see and hear, the call could not be completed.
The person at extension 300 is unavailable. Please leave your message after the tone. When done, hang up or press the pound key.
Let's select VoIP from the menu on the left. Turn it on. In my case, the SIP server is off-premise, as it's on our WAN. I will create a new object to represent the IP of the PBX server. Next, I will configure the devices which are on-premise. I will create network objects for every network I have and add them to the list. That's it! You can see the cool topology that was generated on the right, illustrating our topology. It's much nicer than the one I created manually before. I call dibs! If you scroll down, you will see the properties of SIP services and the ports they use. Make sure your clients are configured to use port 5060 as the source port as well. Now, let's see if it all works. I have my soft phone app on the left, and let's try to make a call. Looks like we have an incoming call from George. We did it.
Thank you for watching, and I'll see you in the next video.
Management options, local management. By the end of this training, you'll be able to configure Quantum Spark as a locally managed device. When you want to manage your Quantum Spark appliance, there are three main options. Locally managed, when you use the same single web applications to manage both the security policy and the device configuration. Second option is centrally managed. This is, you might say, the classic method in Checkpoint, where you have a security management server on site or on cloud, which manages all the gateways within the organization. So then you'll use Smart Console to manage your security policy and the web UI to manage the device itself. The third option is the Spark management, which you'll use if you are using a much larger scale. So you have dozens or hundreds of Quantum Spark gateways and you want to manage them all. So it's a beautiful feature. However, in this video, we'll show you how to set up the local managed Quantum Spark. The local managed device, you only need the web UI. So it's a single pane to do everything, manage the device and the security policy. So if you have a single device, this is a great option for you. And here I have a VNF, and I'm going to run through the first time wizard to show you how you can select the locally managed option. Hitting next. For password, I'm just going to go ahead and type something. Time zone is okay. I'm just going to use the auto-generated name here. And here we go. Local management. And I can go ahead and use that option to locally manage my device. So I'm just going to go ahead and press next. And by the end of First Time Wizard, my device will be locally managed. So it's going to look like this, where you have one web application to manage both the device and the security policy.
Thank you for watching, and I'll see you in the next video.
Management options, central management. By the end of this training, you'll be able to configure Quantum Spark as a centrally managed device. In a previous video, we've discussed the three options to manage your Quantum Spark. It can either be locally managed, which means you'll use the local web application to manage your device. You can either use the central managed option, which we'll use right now, which means you'll use a dedicated management server to manage your appliance, or through Spark management. In this specific video, we'll walk you through using centrally managed device. If you're using the central managed device, it means the web UI is only going to be useful for OS configuration, managing IP addresses and stuff like that. But the security policy aspect, that will be configured through Smart Console. Why would you use this? Because it's scalable. You have multiple gateways, multiple locations, you want to manage it from a single place. That's why you'll use centrally managed device. So what I'm going to do right now is I'm going to set up a management server which will manage this box right here. Since my device is after First Time Wizard and I don't want to go ahead and reset it, I'll need to adjust it from the web UI. So I'm going to Home, Security Management, select Central, and hit Apply. And the first thing you can see is how everything here changed. You no longer see everything related to the security policy because you will now do that from Smart Console. So just like any security gateway, you now need to go ahead and set up a SIG password. So I'm going to set up. Now I don't have security management service, but this is something you can definitely do. In my case, I have a classic open server security management server. Press next. I'll connect to the management server later. Press finish. Now I have SIG ready. Now I'll need to go to Smart Console, set up a new gateway, classic, give it a name, the IP address, under hardware, I'm going to select my appliance, communication, set up the password, okay, trust established, press OK. I have the proper topology, press OK. Let me go ahead and install the policy. And that's it, succeeded. So I now have a security management server managing a classic open server security gateway and a 1590 appliance, which is my very own Quantum Spark device. Thank you for watching. Management options, Spark management. By the end of this training, you'll be able to connect Quantum Spark to Quantum Management Portal. As we discussed in previous videos, there are three ways to manage your Quantum Spark. The first option is the locally managed, where you use the single web application to manage both the security policy and the device itself. Next, we have the centrally managed option where you need a dedicated security management server. Can be open server, can be on cloud, can be on an appliance, but it's more scalable. And if you want it to be even more scalable, you would use the Spark management option. So Quantum Spark management is great because it's a single console to manage thousands of customers. It's part of Check Point's Infinity Portal cloud management solution, provides unified management, monitoring, and analysis, granular role-based administration, and as you can see, provide extensive logging, reporting, simplified group-based security provisioning using plans. So the idea is you set up a plan, you modify the plan with the security blades, the firewall policies, and so on, and you assign a gateway to a plan. As easy as that. So I've connected to the Infinity Portal using my account, and as you can see at the moment, I have 0 gateways and a single plan. If I click on the plans, I have the initial plan. You can see the blades that are enabled. I'm going to go ahead and modify it. Going to security software blades, firewall access policy, and just a few minutes ago I've added a manual rule to allow WeTransfer, and I've saved that already. Now I'm going to gateways, and I'm going to add a gateway. So this is going to be a small office appliance. The name is going to be Spark 1. Registration key, I'll use that. Finish. Okay, so now I have prepared everything I need for the gateway. Now I'll need to go to the gateway itself and introduce myself to Quantum Spark Management. I'm now copying the activation key. Now I'm going to Home, Cloud Services, Configure, and it's just a single string. You just paste it, press apply. Let's hit details. I can see the status if I want to. And we'll just wait for a few minutes. I'm now connected. I can do details to get that information. Let me show you a cool thing. In a previous video, I have manually added a rule to allow Dropbox on the appliance. From the Quantum Spark Management, I've modified the plan to allow WeTransfer. If I'll go to Access Policy, here we go. I can see the Dropbox rule and the WeTransfer rule. And you can see that this rule takes preference as well. So that's really cool. And we have now successfully added Quantum Spark to be managed via Quantum Spark Management. Thank you for watching. User Management Active Directory. By the end of this training, you'll be able to add a new Active Directory domain to Quantum Spark. User management is essential for when you want to use either user awareness, meaning you don't want to see just an IP address, but you want to know, hey, that's Bob. And for when you want to use VPN, for example, it's very common to set up users so I can authenticate by my username when I'm connected remotely. You can create those users locally on the appliance, or you can sync and get them through Active Directory. So in the next demo, I'm going to connect my Active Directory server with my Spark appliance. let's see how easy that is. If you would like to run this demo yourself, you'll need to have the information about your domain controller, the IP address, and credentials. From the Infinity portal, I'm going to Users and Objects, Active Directory Queries, Configure, my domain name. I've added my domain name, my IP address, username, and password, and if I'll hit Discover, it worked. So it managed to pull the distinguished name from the domain. Hit Apply. And for example, if I'll go to VPN, Remote Access User, I can go to Add, Active Directory Group, and I can see the group I've created on my Active Directory domain server. I can just add them. So in this case, for VPN, any user that's part of this group will be able to set up, in this case, a VPN tunnel.
Thank you for watching, and I'll see you in the next video. Threat Prevention Out-of-the-Box State. By the end of this training, you'll be able to evaluate the out-of-the-box state of the device. Once you have completed the first-time wizard, all of the threat prevention blades are enabled. Updates are pending, so after you've ran the first-time wizard and you have established internet connectivity, you'll be able to get the latest updates. SSL inspection is currently disabled, but the device is using HTTPS categorization instead. I have now switched over to my Quantum Spark VNF appliance, meaning this is not my real physical appliance, it's a virtual one, because I wanted a fresh install without any of the updates. So if I'll go to Threat Prevention, I can see that in terms of the blades, IPS, antivirus, antibot, and Threat Prevention are enabled, and I have updates pending. So all of the updates are scheduled automatically. I can click on one of those. I can see the schedule updates. This IPS is up to date. I can go to antivirus. If I'll go to schedule updates, here I can see that IPS, antivirus, antibot, and application control are all scheduled to have a daily task to run the update at 1 a.m. But if I want to, I can always go and click Update Now and update the device right now. Policy, by default we're using the recommended policy, logging everything that happens, protection activation, so vulnerabilities that are at high confidence will be prevented, medium confidence will be prevented, low confidence will be detected. I can go and set up exceptions if I want to. Here I can see the infected device within my network, a list of the IPS protections, modify the engine settings, modify anti-spam, exceptions, and also the SSL status, which currently is disabled. I mean, it's not disabled, but it's not using classic SSL traffic inspection. It's using HTTPS categorization. Thank you for watching, and I'll see you in the next video. Threat Prevention SSL Inspection. By the end of this training, you'll be able to enable SSL inspection and enable inspection by asset type. The SSL traffic inspection inspect traffic that is encrypted by the Secure Socket Layer protocol. All hosts behind the gateway must install the Gateway CA certificate. The blades that are supported are application control and URL filtering, IPS, antivirus, antibot, and threat emulation. However, by default, SSL traffic inspection is not being used, and we're using HTTPS categorization instead, which is filtering specified HTTPS URLs and applications without activating SSL traffic inspection based on the URL in the certificate file. You can easily switch from HTTPS categorization into SSL traffic inspection, but as you'll see in the demonstration, if you want to enable traffic inspection, there are a few things you need to do. First, you need to disable SmartXL, and you also need to deploy the certificate within your clients. When enabling SSL inspection, you can select a bypass policy, meaning certain services or certain networks won't be inspected and the traffic will be bypassed. For example, you can bypass based on the network, if it's a trusted network or an untrusted network. For example, one of your wireless networks. So you can say that any traffic coming from a trusted network would be bypassed. Or to bypass based on a category. So if the user will browse to a financial website, traffic won't be inspected and it will be bypassed. I've switched to my 1590 appliance. I'll go to Access Policy, SSL Inspection. Now you can see that currently I'm using HTTPS categorization. If I would like to switch to SSL traffic inspection, I can see this warning. SSL inspection is not supported when SmartXL services is on. So we'll need to press OK, go to SmartXL, and disable it. Once you disable SmartXL, you can go back to Policy and enable SSL traffic inspection. Now, I really like how informative this Quantum Spark is. I really like this comment here. To deploy SSL inspection, download CA certificate and install it on the hosts. You can click on download, and here's the certificate, which you can later go ahead and install it. And if you click more info, you can see that to enable outbound HTTPS traffic inspection, follow these steps, and you can see these specific steps showing you how to do that. Press close, and let's talk about this setting here to inspect based on the asset, meaning do I want to inspect desktops, laptops, or maybe select specific assets. And for example, IP phones and whatever it is that you like from this list. So you can select to enable SSL traffic inspection, which categories you want to bypass, which sources you want to bypass, and also if you want to bypass or inspect based on the asset that's being used. And if you want, more information is available in SK 12.12.14. Thank you for watching, and I'll see you in the next video. Networking configure interfaces. By the end of this training, you'll be able to configure network interfaces on your Quantum Spark. Once you have this beautiful device, you would probably want to configure your local network. So the first thing you'll do is to configure DHCP. The SMB can support the DHCP protocol, meaning it will assign IP addresses to any device with an interface configured to obtain a dynamic IP address. By default, your subnet would be 192.168.1.0, and of course you can go ahead and modify it to match your actual needs. You can configure each port to act as part of the same network, meaning same LAN, or you can split it into separate networks. So either this will act as a switch or as different networks. On some of the devices, you can customize a specific port to act as a DMZ port or just another port on your network. The Quantum Spark can also support VLAN as well, so you can configure a VLAN interface if that's what you want to use within your organization. Back on my appliance, from the device internet, I can see the external interfaces. In this case, I have two. One was connected directly to WAN, and the other one is connected over cellular using a SIM card. I can see one of them is connected and active, the other one is disconnected. If I'll go to local network, I can see that I have a LAN 1 switch. My local subnet is 192.168.2.1. Subnet mask is 24. And here's my MAC address. And out of those 8 ports, I have one port that is being used. You can see the status right here. And at the moment, all of these ports are part of the same network, which means if I'll take a printer or a TV or just another computer and plug it into this port, it will be part of this same network. Now, if I want to, I can go to Edit. I can select which ports will be assigned to this network. I can check them in and out. I can configure the interface configuration if I wanted to act as an unassigned network or as a separate network. I can configure the local IP address, the DHCP settings. I have additional DHCP settings, for example, which DNS address to assign all of my DHCP clients, which default gateway I want to provide them, the lease of the DHCP. So 4 hours here, but you can go ahead and modify it and customize other settings as well. I can see that at the moment the DMZ is a separate network that I have here. I can go ahead and add a VLAN interface if I want to, a virtual access point, a VPN tunnel, and other configurations as well. I also have the wireless network here. In this case I have two. It's pretty small, but it's the 5 GHz and the 2.4 GHz, but we'll discuss this in a separate video. If I'll go to my Windows client machine, I have all of these network interfaces right here. If I'll go to this one, this is the interface that I'm using to connect to the actual device. I'll go to Details, and I can see my MAC address. I mean, this is the MAC address of my laptop, but look at this line. Who is my default gateway? 2.1. 2.1, that's my actual appliance. So here I can actually see who's my default gateway. In this case, the SMB Quantum Spark device. Thank you for watching, and I'll see you in the next video. Networking, enable wireless network. By the end of this training, you'll be able to enable the wireless network and monitor other access points. On the appliance, I went to device and wireless, and I can see that I have the 2 radio bands available. The 5 GHz is configured but disabled. The 2.4 is not configured. So let's start with that. Configure, select the name. I've configured the network name, protected network 2.4, so people would know that this network is, well, it's going to be slower. The security type, my authentication is using a password, and the password is going to be whatever it is that you want. Press apply. If I'll go to edit settings, I can see the name again. I can change it if I want to. I can see the security type, the encryption type, the password. Now from this page, if you want, you can generate a new password, which is going to be much harder to guess. Here from the wireless network tab, I can see the DHCP settings, the subnet that will be used, access policy, allow access from this network to local networks, or you can disable it, other DHCP settings, and advanced. Press apply. In this case, I've modified the password. I'll enable the 5 GHz radio, and since I'm enabling these networks, my Watchtower application keeps popping with notifications because now there's a new network available, so it tells me about everything that's going on, so it's interesting. I can go to password protected. I can modify only the password if I want to. Press cancel. I can go to edit settings, see those settings again, same settings, of course. If I'll click here, this settings on top, this is the actual radio settings. So if I'll click on that, I can see the frequencies that will be being used, the transmitter power that will be used. I can run a schedule when this network will be available. So for example, it can only run during business hours if you want to. Now that I have enabled the wireless networks, if I'll go to local networks, I can see those networks right here. I can see the subnet that is being used. I can see that they're up. And if I'll go to logs and monitoring, under wireless active devices, I'll see nothing. So let me go ahead and add the device. So I've connected my personal computer to the wireless network. So I'll go and hit refresh. And look, there's a new device on the network. Daniel's Air. The network that it's connected to, the channel that's being used, the frequency, the signal strength, and everything. It detects that this is Apple. Next, I can go to access points. Now, unlike the previous display that we saw, the previous display was show me all of the devices that are currently connected to my network. This shows you all of the access points surrounding you. So you can see your neighbors, you can see other cafes, other businesses that are surrounding you. This is good if you want to see, for example, if there's any noise. Maybe there's another network close to you, and maybe they're using the same channel. So usually it's automatic, the channel selection, but still, this is great data. And if you're familiar with wireless networks, this is a page you want to see just to better understand the wireless networks surrounding you. So this is a great page, but if you want to get an information, you need to make sure that your wireless networks are enabled. And at a glance, I can see that here I'm using channel 11 and here I'm using channel 40. Right at a glance, so this is really nice. And you can also see that 16 adjacent access points use the same channel. That's why the 5 GHz is usually much better. Thank you for watching, and I'll see you in the next video. Networking enables cellular. By the end of this training, you'll be able to enable the cellular connection on your appliance. Enabling the cellular connection is really easy, but when you think about it, everything is easy when you want to configure your Quantum Spark. Based on the model you're using, it can support 1 or 2 SIM cards, so you can use several connections. In this case, I only have 1 SIM card, so let me show you how easy it is to configure it. We'll go to Device, Internet, Configure Internet. The interface that I'm using is not WAN, it's actually the cellular connection. Give it a name, press Apply. And here we go. I have an active connection. I can see that SIM1 is connected to Cellcom and I have a 4G connection. 0% failures, the latency. I can do connection monitoring and see connections going to Google, Cloudflare, and OpenDNS. I can monitor the cellular modem itself. It's nice, I can see the temperature. And you have lots of useful information right here. Press close. And now that I have internet connection, I can show you another cool thing, which is to fetch the license. So I can do activate license. And because I have internet connectivity, I'll be able to get my activation file from the user center because I have internet connection and my appliance is registered. New license was obtained. Press OK. And now I have a license as well. Thank you for watching, and I'll see you in the next video. Reach My Device configuration. By the end of this training, you'll be able to configure Reach My Device. Reach My Device service allows you to remotely connect to the appliance from the internet so that you can use the web UI or CLI when necessary. This is done by tunneling the administrative UI or CLI connections through a checkpoint cloud service. Such configuration is very useful in instances where the appliance is behind NAT device or firewall and cannot be reached directly. In addition, the feature makes it easier to access an appliance with a dynamically assigned IP address. When the security gateway enables the Reach My Device service, an outgoing tunnel to the checkpoint cloud service is established with the appliance IP address. The gateway registers the application server, receives ports and the SSH server hostname, and then opens the SSH tunnel on the SSH server on the specific ports received. If I'll talk about my own home appliance, I don't have a public IP address. I have a dynamic IP address that I got from the ISP. And if I want to reach the device from anywhere around the world, I'll need to enable Reach My Device. The service is free and it's so useful. Let me show you how to use it. From the appliance, we'll go to Device Access. At the moment, I am not registered to use the service. I'll need to do Register. I'll need to select some sort of a unique name. For now, let's use this one. This is a random name, so it's going to be available. And let's just use this one for now. You can see that there is an option to register with an existing hostname. I'll do that later. For now, I'm going to use this one. If you change the hostname, all Watchtower mobile app users must pair the mobile devices again. We'll talk about that later. For now, let's hit apply. And I'm connected. This is my hostname. You can see those unique URLs that I'll have. A validation token. So now I can go and click this. And here's a cool thing. Regardless of the network I'll be connected to, this link, this specific link, will take me to my own appliance. So I'll be able to manage it from wherever I am around the world, as long as I'm connected to the internet, of course. Thank you for watching, and I'll see you in the next video. Reach My Device reuse name. By the end of this training, you'll be able to reuse Reach My Device hostname. In a previous module, we've discussed Reach My Device, and we've discussed that once you enable it, you're given a unique hostname by default, and that hostname needs to remain unique, and you can use it to access your device from wherever it is that you want. But what if I'm going to reset this box, and I would like to use the same hostname again? If I would try that, I'll get an error message saying that hostname is already in use, so you can't just take it from someone else. So if you want to reuse your hostname, you need to have two things: the hostname you want to reuse and this validation token. So if tomorrow I would like to set up a new device with the same link, I'll need to type this as it was, because otherwise it's going to be a new name, and then paste this validation token. And if you'll do that, you'll be able to reuse your name. Let me show you. So I've changed the name to test name. I'll go to edit settings and I'll paste my previous name. I'm going to paste my token here, press apply. And now I've successfully configured Reach My Device to use my previous hostname. By adding the validation token, which I have saved aside because I was prepared, I can now reuse the same link that I've used before to manage my device. Thank you for watching, and I'll see you in the next video. Mobile Configure Watchtower. By the end of this training, you'll be able to configure Watchtower. Watchtower is a checkpoint mobile application which you can install on your mobile devices and monitor your security appliance. It gives you a network security snapshot. You can see security alerts, on-the-spot threat mitigations, policy configuration, customized push notifications. You can prioritize event notifications, and simple management of multiple gateways. Let's see how to configure it. From the main overview page, I'm going to pair your mobile device. The administrator I'm going to use is admin. I'm going to generate a QR code. On the left here, you can see my actual mobile device. So if you want to add a new device, you'll just hit the plus. Scan this QR code. And here I can see lots of cool information about my device. I can see that I'm connected to the internet. If I had a VPN, I could have seen some VPN traffic. If I'll go to statistics, these are statistics from the last hour, and I can see how much traffic was being used. And you can also see the security updates. In this case, I'm up to date with everything. Wireless network. Let's see if I'll see my actual network that I'm using. So I'm currently connected to this network right here. Status is up. Here's the IP address. And I can see that there are 2 protected devices. Now if I'll go back to the Web UI portal, I can see these 2 wireless devices that are connected. One is my mobile device and the other one is the actual laptop that I'm using. And if I'll go to paired mobile devices, I can see that the admin is connected from an Apple iPhone device, and that's the device I've used to connect to the Watchtower application. Really cool, really useful. Go ahead and install it. Thank you for watching, and I'll see you in the next video. Updates, manual and automatic. By the end of this training, you'll be able to update the device and run a manual update. Let's see how easy it is to upgrade the operating system on your Quantum Spark. Straight away, I can see a notification that a new firmware is available. But let's say I don't know about this page. So we simply go to Device, System Operations, and I can see that a new firmware version is available. I'm going to click Upgrade Now. So a few moments later, the upgrade is complete. So now if I'll go to Device and System Operations, I can see that I have the latest version. Now what I've done here was an automatic upgrade, but sometimes you'll want to do a manual upgrade. In that case, you'll go to Manual Upgrade. Next. Select the image you would like to use. Press Open. Upload. Upload finished. Press Next. Next again. And now I'm installing the new image manually. And I can see that the upgrade is complete, and please wait while the appliance reboots. Please do not pull out the power cable. Appliance will be up in about 207 seconds. And when it's done, I'll have a new version of my appliance. And 207 seconds later, the Spark appliance have rebooted, and now I can log in. And done. Thank you for watching, and I'll see you in the next video. VPN site-to-site. By the end of this training, you'll be able to configure site-to-site VPN. VPN, virtual private networks. There are two main flavors of VPN. One is remote access, where you allow endpoint devices such as mobile devices and laptops to connect securely to your remote gateway. And the other one is site-to-site, where you have two gateways, maybe on two branch offices, and you want to establish a secure connection between those two. So in my network, I'm going to have two Quantum Spark boxes on my so-called WAN network, and I'm going to establish a VPN connection between those two sites. It's all done using the web UI. It's graphic, it's very simple. Let's have a look. I'm under VPN sites and I'm going to set up new. Setting up VPN requires you to set up both sites. I've already set up the remote site, so once I set up this, VPN would be running. Here, I'll need to set up the IP address of the remote site. The pre-shared secret we've agreed on. As for the encryption domain, I'm going to use the routing table. Now, if you want, you can modify the encryption or other advanced options, but for now, I'm going to stay with the defaults and hit apply. And as I mentioned, since I've already set up the other site, you can see that the tunnel test finished successfully. If I'll go to VPN tunnels, I can see there's an active tunnel. And if I'll go to my Watchtower app, click VPN, and I can see that there's currently one VPN site active. Thank you for watching, and I'll see you in the next video. VPN remote access. By the end of this training, you'll be able to configure remote access VPN. VPN stands for Virtual Private Network. It has two main flavors. One is remote access, when you allow remote users using laptops, mobile devices to connect securely to your remote gateway. And site-to-site, which allows two remote gateways to communicate with each other securely, setting up a virtual private network. In this video, we'll discuss the remote access. I really like this menu from the web UI because it summarizes all of those different VPN flavors we offer. Each setting has a simple checkbox and the instructions telling you how to set it up, with even links to applications, and everything you need is right here from this menu. So we'll jump to the web UI and show you how to do it yourself. So what we're going to do is we have the Quantum Spark on our artificial WAN network, and I have a few mobile devices on this WAN network, and I'm going to connect over VPN to my Quantum Spark. From VPN Blade Control, I'm going to enable Windows VPN client, set up the pre-shared key. In this case, it's going to be VPN 123. And if you'll click how to connect, you have all the information you need right here. Same goes for mobile client, Checkpoint VPN clients, or an SSL VPN if that's what you're fancy. Same goes for Checkpoint VPN clients, mobile client, SSL VPN. Just enable it, follow the instructions, and you're good to go. One more thing I'll need to do is to set up a user. So I'm going to Remote Access Users, Add. I'll set up the username, password. I can set up email, phone number, and other comments as well. Press Apply. As you can see, I have mobile client enabled, which enable VPN remote access mobile clients to connect via Checkpoint mobile VPN client. On the right, I have my mobile phone, so I'm going to my business applications, Capsule Connect. I have the username, SimpleRick, my password, and you can clearly see that I'm connected. And if I'll go and see the connected remote users, I can see SimpleRick is indeed connected. This is another laptop that I have, and I've set up SimpleRick to set up a VPN connection. I've added the gateway's IP address, my username. And now all I need to do is to enable VPN. And you can see I'm connected. And here's my remote connection. And back on the Watchtower app, I can go to Internet, VPN. I can still see the site-to-site VPN tunnel. And if I'll go to Users, I can see SimpleRick is connected from 2 different IP addresses. From the Logs and Monitoring tab, I can go to VPN tunnels. Here's the site-to-site VPN tunnel that I have. And to see the remote VPN users, I'll need to go to VPN Connected Remote Users. And by the way, to add the user, if I were to have Active Directory enabled, I could have just used the Active Directory users as the remote VPN users as well.
Thank you for watching, and I'll see you in the next video. Monitoring. By the end of this training, you'll be able to use the Monitoring tab to monitor the network environment. Here I am in my 1519 appliance, and we'll just go over all of these settings right here. First, we have the security logs. So any security incidents you'll have regarding the policy will be shown here. You can run queries, refresh, clear the logs, and other cool stuff. We have system logs. If you were to have any external log servers, you'll be able to configure them right here. Notifications. So personally, I get these notifications on my Watchtower app, so it's really cool. Active devices. These are all the devices that are currently connected to my Quantum Spark. Wireless active devices. I have 2 right here. Paired mobile devices. So if I were to have any users who are using Watchtower, I would have seen them right here. In my case, I've reset my appliance, but if you saw the Watchtower video, you saw the device was there. Infected device, currently I don't have any, I'm good. VPN tunnels, if you were to have any VPN tunnels, you would see information about the tunnel right here. Connections, I can see connections going through my device. Access points, if you have the wireless networks enabled, you can go ahead and scan networks in your area. If we'll go to monitoring itself, here we can see information about the current connections. We have a breakdown of the different applications that were being used. I can go and switch to categories instead, and I can see instant messaging, general search engine, and so on. I'll go back to applications. We can change to sites, users. In this case, I don't have user awareness, so it's just 100% same thing. This is nice. You can see traffic over time, reports. I can go to demo here as well. And here just have a little bit more information, so it just looks nicer. I'll go back. And if I'll click here, it can also take me to do some troubleshooting, meaning to show me monitoring about the actual CPU, memory, and disk usage. I can hit refresh, and I can start seeing those live graphs about the memory usage and CPU usage, and also disk here below as well. Click on reports. You get nice reports about the traffic that was being used. Really nice. Can be useful as well. You can print it straight from here. Really, really nice. Thank you for watching, and I'll see you in the next video. Troubleshooting Tools Overview.
By the end of this training, you'll be able to use the diagnostic tools to collect valuable data and generate reports. Back on my 1519 appliance, I'm at the Device Tools tab, and from here we have lots of small tools which can be useful for troubleshooting. For example, monitoring the system resources. I can hit refresh, and then I have CPU usage, memory usage, and disk usage live, really useful. Show the routing table. Now, of course, you can also just open up a command line and do that yourself, but it's nice to have it in a graphical method right here. Router configuration, for example, for OSPF, which at the moment I have nothing. I only have the area enabled, but later on, if you'll have OSPF enabled, you'll be able to see that information here. The test cloud services ports, which will verify that the appliance could connect to cloud services. You have a graphic TCP dump tool, where you set up like a host, a port, and then you'll see it here. DSL statistics. At the moment, I don't have any. I'm not connected over DSL. Monitor the cellular modem. So I can see 4G, LTE, signal strength. I'm using SIM1. SIM2 is not available. Temperature and other cool stuff. This will generate a CP info file, which you can later send to your technical support or someone to help you figure out if something doesn't work. So just click on that, it will generate the report, and later you'll be able to send it over to whoever it is you're working with. You can also generate Dr. Spark. Dr. Spark is a cool utility that generates lots of useful traffic regarding Spark and help you troubleshoot if something doesn't work. And there's also the Dr. Spark load as well, a performance test in this case, useful tools. You can send a ping straight from here. So yes, you can open up a CLI window and run a ping, or you can just do it from here. And in this case, the ping works. And a DNS lookup as well. You can also download a USB-C driver for your appliance, so you can go ahead and have a console connection to your appliance. In this case, the Dr. Spark performance report is ready. I can click download, and it will download this report. Same for CP info file. And now I have these files ready. Thank you for watching, and I'll see you in the next video. Troubleshooting backups. By the end of this training, you'll be able to create a backup file and restore a backup file. From the Device tab, if I'll go to System Operations, there are a few very useful utilities you can use here. First one is to just reboot the appliance, restore to factory default settings, but the firmware will remain as is. Factory defaults revert to the factory default image and settings. In this case, my factory firmware version is R80 2015. Firmware upgrade, so you can do check now to get an online upgrade from the Checkpoint servers, or you can do it manually. We've done this before. Revert to the previous image. In this case, this is my previous version, and set up a backup. So I can create a backup file. I can encrypt it if I want to. And tomorrow, if something didn't work, I want to revert, I've messed something up, I can always just do restore. Browse to that file and restore if needed. Thank you for watching, and I'll see you in the next video. Networking dynamic routing. By the end of this training, you'll be able to enable OSPF on an interface. When you talk about dynamic routing, there's so much to discuss. It's a very efficient way to build your routing table in a dynamic and automatic manner. So you need to enable the dynamic routing protocol, configure it, and watch the magic happens. When you think about dynamic routing, OSPF and BGP are two common, very useful dynamic routing protocols that come to mind.
In this demo, I'll show you how to configure OSPF on your Quantum Spark. For the purpose of this demo, I've already set up a checkpoint security gateway running OSPF. And what we'll do here is I'll set up the Quantum Spark to establish neighbor relationship with that router. Going to OSPF, add an interface. So I'll be using LAN 1, area 0. I'm going to keep the intervals as default, 10 and 40. This is not going to be a passive interface. Press apply. And now, if I'll go to the routing table, and here it is. Look at this beautiful route. If you want to reach 10.1.1.0/24, your next hop is this address. And this is an OSPF protocol. It's a dynamic route. And all I had to do was to just configure OSPF. And the cool thing was, I've configured OSPF on the Quantum Spark using a graphical interface, which is such a relief, actually. That's really cool. I really love this feature. I hope you'll take the time to do it yourself.
Thank you for watching, and I'll see you in the next video.
Welcome to the most comprehensive yet straightforward online resource about Linux NetFilter and IP tables firewalls. Nowadays, Linux powers the internet servers, and IP tables is the built-in and de facto way used to secure them. This is the only course you need in order to master all IP tables key concepts from scratch. At the end of the course, you'll know how to create custom IP tables firewalls for your Linux infrastructure and how to troubleshoot and monitor existing ones. Now let's be honest, there are hundreds of free tutorials out there. Why should you choose this course? Because I will not only teach you some IP tables commands or how to copy and paste confusing out-of-the-box configurations, but I will teach you how to deeply understand the way a firewall works and how to optimize such a security solution. I've spent thousands of hours studying Linux and security, and I honestly say that I've read them all, and it will be my pleasure to share this knowledge with you in a structured and easy to digest manner. We'll dive deeper into every IP tables option, match or target, and we'll see a lot of examples, many of them ready to be used in your environment. You'll see how to filter huge collections of addresses and networks, or even entire countries, using IPsec. By enrolling in this course, you get the skills to get ahead. This course is really different, and I'll give you only two main reasons why you should take this course. For each IP tables key concept, you'll get not only a video tutorial, but a bunch of real-world examples, quizzes, challenges with solutions, and slides with main points. This course is taught by me. Hi there, I'm Andrei. I have almost 20 years experience in networking and programming, and I'm not just a random guy that teaches Linux and IP tables. I have more than 10 years experience with in-person networking and programming trainings. Over the years, thousands of students have been enrolled in my courses. I know how to build a curricula, and I know exactly what really matters. This course is for a wide audience, including sysadmins, network engineers, DevOps engineers, ethical hackers, pen testers, and anyone who is involved with Linux and security. And don't forget, you'll have lifetime access to the course, and you can return and look for a specific IP tables option, match or example anytime you want. And one more thing, I'll update the course constantly with new content, quizzes, and challenges. Now, if you don't like the course, you are covered by a 30-day money-back guarantee, full refund, no questions asked. When you are ready to start your journey into Linux and NetFilter IP tables firewalls, check the free preview lectures to see if the course is right for you, and then click the enroll button. See you in the course. Hello and welcome. In this course, we'll talk about Linux firewalls. A firewall is a network security system that monitors and controls incoming and outgoing network traffic based on predetermined security rules. A firewall typically establishes a barrier between a trusted internal network and untrusted external network, such as the internet. Firewalls are an important tool that can be configured to protect your servers and infrastructure. The firewall solution for Linux is called NetFilter. NetFilter is a software firewall, a packet filtering framework inside the Linux kernel. It enables packet filtering, network and port address translation, port forwarding, and packet alteration, which is the process of intentionally altering data in IP packet headers before or after the routing process. NetFilter is the professional and mostly used solution for building firewalls in Linux operating systems. The netfilter framework is controlled by the iptables command. iptables is a tool that belongs to the user space used to configure netfilter. It is said that netfilter belongs to the kernel space and iptables belongs to the user space. Most of the time, netfilter and iptables are often combined into a single expression, netfilter iptables. In this course, we won't make a very clear distinction between iptables and netfilter and simply refer to the entire thing as iptables. Then you should know that every Linux distribution uses netfilter and iptables, and there is nothing extra, no extra software that should be installed. iptables is already there. You should also know that only root can configure the netfilter framework or use the iptables command. This was a very short introduction to netfilter and iptables, and in the next lectures we'll dive deep into almost every iptables option available. In this lecture, we'll take a look at iptables, chains, and tables, which are extremely important netfilter concepts. In order to be proficient in building custom firewalls, you have to deeply understand these concepts. Every data packet is inspected by firewall rules within the Linux kernel. Firewall rules determine what traffic your firewall allows and what is blocked. Each rule has a matching component and an action component. When packets arrive from the network, the netfilter framework of the Linux kernel recognizes and groups packets into data streams or flows. Netfilter analyzes both packet headers and packet contents in order to track connections and to perform SPI or stateful packet inspection. Each packet from the stream is processed by the firewall with some performance optimization. The iptables firewall uses tables to organize its rules. Within each iptables table, rules are further organized within separate chains. Rules are placed within a specific chain of a specific table. This is important, and I'll say it again. A rule is connected to a chain and to a table. Within a chain, a packet starts at the top of the chain and is matched or evaluated rule by rule. When a match is found, the target of the rule is executed. The target is the action that is triggered when a packet meets the matching criteria of a rule. Examples of targets are drop or accept. If the target is a terminating one, like for example drop, no other rule will evaluate the packet. If the packet reaches the end of the chain without a match, the default policy for that chain is applied. There are two policies, drop and accept, and the last one being also the default one. We'll talk more about policies in subsequent chapters. Let's move on and see what chains are available in netfilter. There are 5 built-in chains. One of the most used chains for packet filtering is called input. This is used for filtering, so dropping or accepting incoming packets. Our Linux host is the destination of the packet. Each packet that was destined to our Linux host is evaluated against the rules of input chain. No exception here, no packet is allowed to skip this evaluation. I'd like to show you a very simple example. Please don't focus on iptables syntax, but only on the concepts of chains, tables, rules, and targets. From this Windows machine, I'm gonna continuously ping the Linux machine. Ping -t and the IP address of the Linux machine. And on the Linux machine, I'm gonna add a new IP tables rule to filter table of input chain that drops all ICMP traffic and that includes ping as well. I'm becoming root. And I'm writing the rule IP tables -t filter -a input -p ICMP -j drop. Ping is still working. And we notice how ping has suddenly stopped because the NetFilter firewall is blocking incoming ICMP, so including ping packets. Ping doesn't work anymore. By the way, you should always write table names in lowercase letters and chain names in uppercase letters. Targets like drop in our example are always written in uppercase letters. Another important chain is output. This is used to filter outgoing packets. Our Linux host is the source of the packet. Let's see an example. I want to drop all packets generated by the Linux host that are going to the IP address of netfilter.org. First, let's check that the connection is working. And we see that the site is loading. Now, I'm adding a firewall rule to filter table and output chain. IP tables -t filter, this is the name of the table, -a output, the name of the chain, -d netfilter.org, and -j drop. This is the target or the action. Let's check again the connection to the website. I'm refreshing the website. We notice the web page is not loading anymore. Of course, that's because the firewall is dropping generated packets that are going to netfilter.org. One remark here. NetFilter uses in fact the IP address of netfilter.org, not the domain name, even though I've written the domain. Behind the scenes, it makes a DNS query and requests the IP of netfilter.org and then drops all the packets destined to that IP. Now, in your tasks, if you are using another domain, especially a big one like google.com or facebook.com, it's possible that even though you've executed the right IP tables command, the connection to that site is still working. The reason for this is that behind those big domains, there are tens of IP addresses and you've blocked only one or a few of them. When you make the next DNS request, it's possible that the server will give you a new IP that was not blocked in the first place. As a conclusion, you can deny access to the websites this way only if that domain has one or only a few IP attached. Another chain is forward and is used for filtering routed packets. In this case, our Linux machine is a router and connects at least two networks like the internet and the local area network. And the last two chains are pre-routing, used for DNet, aka port forwarding, and post-routing, used for SNet or simply net or masquerade. These are more advanced concepts and we'll see examples in their dedicated sections. Okay, these are the 5 IP tables built-in chains. They are always available, you cannot remove or rename them. You just use them as they are. You can also create other chains named user-defined or custom chains. This is an advanced topic and we'll dive deeper into user-defined chains and we'll see many more examples in another section. Welcome back. Let's take a look at the tables that iptables provides. The logic for filtering IP packets is organized in a collection of tables, each with a specific purpose. Each packet is inspected by the NetFilter firewall and matched in order top to bottom against the rules that are placed within a specific chain of a specific table. There are 4 built-in tables available, and each table has a very specific purpose. The filter table is one of the most widely used tables in iptables. It's the default table and is where all the actions typically associated with a firewall take place. There is where the decision of accepting or dropping each packet is taken. Being the default table means that when we add or remove a firewall rule, if we don't specify the table's name, it will automatically consider the filter table. Let's see an example. I want to create an iptables rule that accepts TCP traffic to port 22 only if it comes from a specific IP address. This is the Windows machine and this is the Linux machine. Let's check port 22 on Linux from Windows. Let's see if it's open or closed. Telnet, the IP address of Linux, and port 22. Sorry, port 22. And it's open. There is an SSH server that is running. Now I'll write the iptables rules. iptables -a input -p TCP, it's TCP traffic, -d port 22, traffic is going to port 22, so the SSH server, -s, and I'll take a random IP address, -j, accept. If a TCP packet comes from this random IP address to port 22, it's accepted. Okay, let's think for a moment what happens if the packet comes from a different source IP address. And the answer is that it depends on how the policy of the input chain is set. It could be either accept or drop. The default policy always applies at the end of a chain only, and it determines what happens to the packets that are not matched against any rule of the chain. Are they accepted or dropped? In this case, we don't know what is the policy, and we neither want to enter into further details about chain policy, so we add a second rule that drops any packet to port 22 from any source address. So iptables -a input -p TCP -d port 22 -j drop. What do these two rules do? Each incoming packet will be inspected in order, and this is the key here, by the first rule, and if it doesn't match against it, it will be inspected by the second one. So if a packet is coming from 5.3.6.6, it will be accepted, and the second rule will not evaluate the packet anymore. But if it's coming from another IP address, like say the IP address of Windows, the second rule will inspect it, and if it comes to port 22, it will be dropped no matter of its source IP address. In these rules, you notice I didn't specify the table to which the rules are added. In this case, it's the filter table. Let's check the same port again. And we notice that the port is now filtered. That's because the Windows machine doesn't have that specific IP address, and only traffic from that IP is permitted. Also note that IP tables filter table has the following built-in chains: input, output, and forward. Another table is net, and it's specialized in SNet that comes from source network address translation and DNet that comes from destination address translation. As packets enter the network stack, rules in this table will determine whether and how to modify the packet's source or destination addresses in order to impact the way the packet is further processed. IP tables net table has the following built-in chains: pre-routing for DNet or port forwarding, post-routing for SNet or masquerade, and output if we want to configure net in a different way for locally generated packets. The Mangle table is specialized in packet alteration. For instance, we can modify fields in the IP header, like say type of service or time to leave, by adding rules to the Mangle table. The Mangle table has the following built-in chains: pre-routing, input, forward, output, and post-routing. In fact, it can be used with all IP tables built-in chains. And the last table is RA. The IP tables firewall is stateful, meaning that packets are evaluated in regards to their relation to previous packets. IP tables views packets as part of an ongoing connection or session instead of as a stream of discrete, unrelated packets. The RA table is used to set a mark on packets that should not be handled by the connection tracking system, or simply said, we don't want some packets to be classified by accepting them directly. Like for example the traffic from our own loopback interface. This is done for performance improvement. We'll have a special section on RA table later in the course. To write efficient firewall rules, you must deeply understand how a packet traverses the net filter tables and chains. And there are 3 lectures where I explain in depth these concepts. Until that point in the course, to ensure a smooth start in understanding IP tables, let's recap in a nutshell the most used scenarios. Incoming traffic is filtered on the input chain of the filter table. Outgoing traffic is filtered on the output chain of the filter table, and routed traffic is filtered on the forward chain of the filter table in both directions. Then, source network address translation, SNet or masquerade, is performed on the net table of the post-routing chain, and port forwarding or destination network address translation is performed on the net filter of the pre-routing chain. Now, if we want to modify values from the packet's headers, like time to leave or type of service, we add rules to the Mangle table of the output, pre-routing or post-routing chains. And if we want the packet to skip the connection tracking system, we add rules that match that packet to the RA table. Okay, that's how a packet traverses the net filter tables and chains in a nutshell. Thank you. In this lecture, we'll talk about the IP tables command. IP tables is the user space component used to configure netfilter, the kernel framework that does the actual filtering. It's said that IP tables belongs to user space and netfilter belongs to kernel space. So we can interact with netfilter using the IP tables command. There are also some graphical frontends for netfilter that allow us to create rules. However, they lack the flexibility of using a command line, and Linux professionals rely heavily on the IP tables command, which has many options. It is also important to know that IP tables can be run only by root. Let's move on and see what is the general syntax of IP tables. After the IP tables command comes the table name. The table name indicates the netfilter table on which the command operates. By default, it's the filter table. Command or option indicates the operation we perform on a chain of that table. Either long or short options are allowed. For example, we append a rule to the end of the chain, we insert a rule on a specific position, we flush all the rules of a specific chain and table, or we simply print out all the rules of a chain. Each rule has a matching and an action component. The matching part of a rule specifies the criteria that a packet must meet in order for the associated action or target to be executed. A match is something that specifies a special condition within the packet that must be true or false, and a single rule can contain several matches, and the entire rule condition is true if all the matches are true. For example, we may want to match packets that come from a specific host or network and are going to some ports on our system. If any of these matches fails, for example, the source address isn't correct, but everything else is true, the whole rule fails and the next rule is tested on the packet. But if all matches are true, the target specified by the rule is applied. Then comes -j and the target. The target specifies what action is taken on packets matching the criteria of the rule. Examples of targets are drop, accept, log, or masquerade. We'll dive deeper into targets in a dedicated section. Enough talking, let's go to a terminal and write some real IP tables rules. Before starting writing rules, don't forget that only root can run the IP tables command. You need root access in order to configure netfilter or run the IP tables command. If you try to run the IP tables command as a non-root user, you'll get a permission denied error. I've executed the IP tables command as a non-root user, and I've got a permission denied error. It says very clear that I must be root. And I'm becoming root by running sudo su. Now I'm root. Let's run the same command as root. Okay, there is no error. By the way, the command lists the filter table, which is the default for input, output, and forward chains. If you want to see the rules from other tables, you should specify the table using -t option like this, IP tables -tnet -l. It has displayed the chains of the net table. Okay. In the next example, I want to add a rule to filter table and input chain that drops incoming ping packets. First, I'm checking that ping is working. Ping and the IP address of Linux 1. This is another Linux host and its host name is Linux 2. So ping and the IP address of the other Linux operating system. X10 at the end. Ping is working. And now the rule. IP tables. I'm adding the rule to the filter table, filter. -a, I am appending the rule to the input chain. And the matches. The protocol is ICMP, --ICMP type. I'm matching on the ICMP type. Echo. There are more messages in the ICMP protocol and I am dropping only echo or echo request packets. -J, drop. Ping is still working, and I'm hitting enter. Okay, it wants echo request, not echo. Perfect. And we notice how ping stopped. Let's list the contents of the firewall. IP tables -L or IP tables -VNL. I want to see more information. And there are 30 packets matched by the rule. The same rule could be applied without -T filter option. The filter table is the default. It's the same. Let's try another rule. I want to deny access from this Linux host to a specific website, let's say www.ubuntu.com. Let's think about this requirement and split the rule in more parts. What table are we using? And the answer is filter, because we are filtering traffic. We are not doing net or something else. So IP tables -T filter. What IP tables command or option are we gonna specify? And the answer is -A from append. We are gonna append a new rule to the table. What chain will be used to match the packets? This is outgoing traffic and it always means output. And now come the matches. What matches are required for this kind of traffic? So this is TCP traffic -P from protocol TCP -D port 80. The traffic is going to port 80. And -D, the destination IP address, www.ubuntu.com. And what target or action we perform on the matched packets. And of course, it's drop. -J, drop. J means to jump to the specific target or do the following action when the packet matches against this rule. Targets are always written in uppercase letters. Before hitting enter, I want to check that the web page is loading. And the page is loading. We notice here that it uses HTTPS and that means port 443. So I'm hitting enter and I'm adding another rule that drops packets to port 443. So in fact, these two rules will block traffic to port 80 or port 443. Let's reload the page. And we notice that the page is not loading anymore. If we list the firewall using -L option and VN, okay, we see the IP tables rules and a lot of matched packets on the output chain. All these IP addresses are of www.ubuntu.com and have been obtained from the DNS server. And we see a lot of matched or dropped packets. Hello and welcome back. In this lesson, we'll talk about IP tables options, flags or switches. These options specify the desired action to perform and only one of them can be specified on the command line unless otherwise stated. Also note that all of these options are written in uppercase letters. Let's see what options are available. -A means append the rule to the end of the selected chain. Let's look at an example. I'll append a rule to the output chain that drops incoming traffic to port 25. So SMTP traffic. IP tables. It's not necessary to specify the table. It's by default the filter table. So I don't write -t filter. I could write if I want. -a, the name of the chain input, minus PTCP, it's TCP traffic, minus D port 25. The packets are going to port 25, -j drop. Before hitting the enter key, I want to test that port 25 is open. From another Linux machine, I'll scan that port. And I'm gonna use nmap. Nmap -p the port 25 and the IP address of the Linux machine that I'm scanning. By the way, you could simply install nmap by writing apt-get install nmap. And we notice that port 25 is open. And I'm adding the IP tables rule. I'm scanning the port again. And the port is filtered. This IP tables rule has dropped the packets to port 25. Let's add another rule that blocks incoming traffic to port 80. IP tables -a input -p TCP -d port 80 -j drop. And I'm also installing a web server to test it right. It's very easy to install a web server on Ubuntu. I'm installing the Apache web server. From the other Linux operating system, I'm gonna scan port 80. The port is filtered, and if I list the firewall, I'll see a lot of matched and dropped packets. Each rule has dropped 2 packets. Another important option is -i. -i inserts one or more rules in the selected chain on a specific position or on top or position 1 if no position is given. Let's look at an example. I want to drop incoming traffic to port UDP 69, which is TFTP, Trivial File Transfer Protocol. Instead of -a, I'll use -i. The chain is input -p, the protocol is UDP, and the destination port is 69. -j drop. Now I'm listing the firewall. We see that the last rule has been added on top of the input chain. Now that rule is the first rule in the chain, and this is very important because rules are traversed in order. If I want to add a rule on a specific position, for example a rule on the second position, I can simply specify the position after the name of the chain. Like this. I'll insert this rule on position 3, on the third position. And the rule is on the third position. Let's suppose I've changed my mind and I want to accept all traffic to port 80. Remember that I've already added a rule that drops traffic to port 80. I'm running the same IP tables command, just that instead -a, I'll use -i. Okay, this is the rule. I'm using -i. And instead of drop, I'm using accept. Instead of appending the rule to the end of the chain, the rule will be added on top of the chain on first position. We see the rule on first position on input chain. Pause the video for 30 seconds and think about what will happen. Will the traffic to port 80 be dropped or accepted? Let's test it using the browser from another machine. I'm writing the IP address of Linux 1. And we see that the port is open. We could connect to port 80 and the page loaded successfully. When I've added the rule using -i, the rule became the first rule in the chain, and rules are traversed in order, top to bottom. When a packet is arriving to port 80, the first rule matches the packet and accepts it. Accept is a terminating target, and that means that the packet is accepted and no other rule will check the packet. So in fact here, the rule that drops incoming packets to port 80 will never be evaluated. That's why the packets were accepted, and this is an example of why the order of the rules is so important. Another option is -l. -l lists all rules in the selected chain and the specified table. If no chain is given, all chains are listed. For example, iptables -l lists all rules in the filter table and all its chains, input, output, and forward. It's common to use -l option together with n from numeric and v from verbose like this. We'll talk more about -l in another lecture where we'll dive deeper into listing the Linux firewall. -f means flush the selected chain or all the chains in the table if none is given. This is equivalent to deleting all the rules one by one. For example, if I want to flush the input chain, I can simply execute iptables -f input. Now, when I'm listing the chains, I can see that there is no rules on the input chain. They have been flushed. If I don't specify the chain, it will flush all chains from that table, and by default, it's the filter table. It has flushed all the chains of filter table. Now, I'm flushing all the chains of the net table. We'll discuss more about -f in a subsequent chapter. -z means zero the packet and byte counters in all the chains or only in the given chain. Let me show you an example. I'll add a rule to the output chain that accepts SSH outgoing traffic or traffic to a remote SSH server, this Linux being the SSH client. iptables -a output -p TCP -d port 22. The packets are going to port 22 -j accept. And I'm connecting to a remote SSH server just to have some matched packets. Okay, I am pressing Ctrl+C. I don't want to connect to that server. I just wanted some matched packets. When I list the firewall, we see that there are 9 matched packets, or 1925 bytes. iptables -z will reset packet and byte counters. We see that the number of packets and bytes matched by the rule have been reset. -n creates a new user-defined chain by the given name. We can create user-defined chains simply by writing iptables -n and the name of the new user-defined or custom chain. iptables -n, my chain. When running iptables -vnl, we see all the chains, including the custom chain I've just created. Now to delete that chain, I use -x option, iptables -x, my chain. I don't go deeper into user-defined chains at this moment. We'll have an entire section on this later in the course. And finally, -p sets the default policy for the built-in chains input, output, and forward. The default policy specifies what happens to packets that are not matched by any rule and can be either accept or drop. The default policy is set to accept. We can change the default policy using iptables -p, the name of the chain, and then input or drop. For example, I'm setting the drop policy for the forward chain. iptables -p, the name of the chain forward, and the policy drop. This means that each packet that is not accepted by a rule will be dropped. We'll have a dedicated lecture on policies. And the last option we take a look at in this lecture is -d. It deletes one or more rules from the selected chain. We don't use this option too much because we often write all the rules in a script and then run the script. If we want to delete or modify a rule, we simply modify the script and run it again. But if you want to use the -d option to delete an iptables rule, you just have to specify the line number you want to delete like this. There are rules loaded into memory, and I'll list the filter table to see the rules. Let's delete this rule, which is the second rule of the output chain. So I write iptables -d output and 2, where 2 means the second line. And now when I list the filter table of input, output, and forward chains, we notice that the rule has been deleted. Okay, these are the most important iptables commands, options, or flags. Thank you. Until this point in the course, we've written all the iptables rules directly at console and they were loaded into RAM. If we have a firewall with many rules, it's much easier to write all these rules in a script, make that script executable, and then run it. But if we just want a simple rule that drops the traffic from a specific IP address or allows a specific service to communicate with the outside world, we can simply write that rule at the Linux terminal. Let's see some live examples. If I want to write an iptables rule at the Linux terminal, I simply write the rule as root. iptables -a input -p icmp -j drop. That's all. The rule drops all incoming ICMP traffic to this Linux machine. It's important to note that iptables rules written at the terminal are not saved after the system is restarted. If you reboot the system, you will lose all the rules. And you say, okay, but do I have to write all the rules each time the computer starts? Of course you don't. If you want your iptables rules to persist after the system restarts, you write them in a shell script make that script executable, and configure the script to be run automatically at boot time. Let's go to work and see how we create a script with iptables rules and then run the script. Remember that a script is just a text file that contains shell commands. I'm gonna create the script using my preferred text editor, which is VI. In your case, if you haven't used VI before, try a simple editor like Nano, Pico, or even Notepad. VI is a very good and efficient editor, but it's not the easiest one to use in Linux. The name of the script will be firewall1.sh. The first line of the script will look like this: a hash sign, an exclamation mark, and the path to bash. This is called shebang, and it tells the shell what program to interpret the script with when executing it. In this example, the script is to be interpreted and run by the bash shell. If you write another script, let's say a Python script, you write here the path to the Python interpreter. The most common option is using bash. And inside the file, I'll simply write some iptables rules. For example, I'll write a rule that drops all incoming SSH traffic, so traffic to port 22, and two another rules that drop outgoing traffic to port 80 and 443, so HTTP and HTTPS traffic. And the first rule, iptables -a input -ptcp -d port 22 -j drop. It drops incoming traffic to port 22. And two rules that drop outgoing HTTP and HTTPS traffic. iptables -a output x outgoing traffic -ptcp -d port 80 -j drop, and another rule for HTTPS. iptables -a output -ptcp -d port 443 -j drop. Okay, here x output. I'm saving the script, make it executable, and then run it. And we see the rules. The rule that drops incoming SSH traffic and the rules that drop outgoing HTTP and HTTPS traffic. One important thing to know is that if I run the script using its name like firewall1.sh, so without a dot, which is the current working directory, and a /, I get an error, command not found. This happens because the current working directory doesn't belong to the Linux path, so the shell doesn't look for the script inside the current directory. It's looking for commands only in these directories. Here is where the shell is looking for commands. So you have either to add the current working directory to path or run the script using ./ and the name of the script. In fact, it says take the script from the current working directory, which is dot, and run it. Now suppose we want to change something in our script. For example, I don't want to block outgoing HTTPS traffic anymore. The logical thing to do is to open the script, replace that line, save the script, and run it again. In this example, I've executed the script again. If we list the firewall iptables -vnl, we see that there are more rules that we have expected. There are only 3 rules in the script, but more rules in the RAM memory. In fact, each rule seems doubled. To make this point clearer, I'll execute the script again. Now, there are even more rules in the RAM memory. Something is wrong. What could it be? Each time I've executed the script, the rules from the script, so those 3 rules, have been appended to the IP table's chains. I ran the script 3 times, so I have 9 rules. And this is not what we want as a result. When I run the firewall script, I expect that only those rules from the script are loaded. How do we do it? A good practice is to add at the beginning of the script IP tables -f. This will flush all the chains of the filter table and start with a new fresh firewall. I am opening the file, and at the beginning I am adding IP tables -f. This will flush all the chains. I'm saving the file and running it again. And we notice that only the rules from the script have been loaded. All other rules have been flushed. An important remark is that if you have rules also on other chains and tables, like say rules for doing net, you should also flush those tables and chains. Let's see what it's all about. I'm adding a rule that will perform as net. It will translate the private IP addresses from network 10.0.0.0/8 to the public IP of this Linux machine. In this case, it's a router. IP tables -tnet, it's mandatory to specify the table, -a post routing, -s, the IP addresses that will be translated, it's an entire network, -o, the outgoing interface, -j, snet, and to source, and I'll write a random IP address. I suppose this is the public IP. Don't focus on net, we'll have an entire section on this. I'm saving the script and then run it. And I'll run it many times. When I am listing the net filter, we see there are many rules. There are 4 rules, not 1 like in my script. It appended the rule to post routing chain and not filter each time I've executed the script. This issue will be solved by also flushing the net table at the beginning of the firewall script. Here, at the beginning, I write IP tables -tnet -f. I'm saving the script and running it again. I can run it as many times as I want. There will be a single net rule, the rule from the script. IP tables -tnet -vnl. And there is only one rule. Okay, that's all, thank you. In this lecture, I want to emphasize the difference between IP tables options -a append and -i insert. Should we use -a or -i in our IP tables rules? Most of the time, we write the IP tables rules in a shell script and run that script. Let's take an example. We create a script that drops incoming SSH traffic from any IP address except one. By the way, this is a very common scenario. I'm creating a new script called drop_ssh.sh. The first line will be the shebang. It tells that the script is executed by bash by default. At the beginning of the script, I'll flush the firewall. We've discussed about this in the last lecture. And the rules. iptables -t filter. Filter is not mandatory, it's the default table. -a input. It's incoming traffic, so I am using the input chain. -ptcp, --d port 22. The traffic is coming to port 22. And the source IP address I am permitting. And it's the IP address of the other Linux machine I have. And -j accept. This rule will accept SSH traffic from this source IP address. And another rule that drops all other SSH traffic. iptables. I don't write -t filter anymore. -a input. -ptcp. --d port 22. And -j drop. I'm saving the file and then make it executable. And I'm executing the script. Perfect. Let's test it. First, I'm trying to connect to this Linux machine from the IP address that was permitted. SSH, the user that is authenticating, student, and the IP address of the server. And it's working. Perfect. Now, let's try to connect to the SSH server from another IP. For example, from Windows using PuTTY. And it's not working. Let's list the firewall. We see there are 3 dropped packets by this rule and 40 packets accepted by the first rule. Perfect, it's working fine. Now back to our firewall script, we'll try something different. What would happen if instead of -a, which means append or add rules to the end of the chain, I'd use -i, which means insert or add rules on top of the chain. I'm replacing -a with -i everywhere. I'm saving the script and then run it. Let's try to connect again using SSH from the IP address that was permitted. So from Linux 2. I'm executing the same command. And surprise, it's not working anymore, but it should be working. Let's analyze what had happened. The bash shell has executed the script line by line. On this line, it has flushed the filter table of input, output, and forward chains, and on this line, it has added this rule to input chain. This is the first rule of the chain. And then it inserted this rule, so the last rule of the script, on top of the input chain. Insert means insert the rule on top. So in fact, this is the first rule of the chain and this is the second rule. Let's list the firewall to check it. We notice that the rule that drops the packets is the first and the rule that accepts the packets is the second. That's because I've used -i instead of -a. In the RAM memory, the rules are not in the order in which they were written in the script. What happened when a packet from the permitted host has arrived to the firewall? Which rule has matched the packet? And of course, it's the first rule, the rule that is dropping all traffic to port 22. The packet's headers satisfy the matching criteria of the rule. It's TCP traffic to port 22, so it's dropped. So in fact, the second rule, the one that accepts traffic to port 22 from that specific IP address, will never, but never match any packet. All the traffic has been already dropped by the first rule just before it. This is an example showing that order matters. Let's come to a conclusion. When writing rules inside a shell script, you usually use -a, so append to the end of the chain, and not -i, which means insert the rule on top of the chain. If you use -a, the order of the rules in RAM memory will be exactly the order in which the rules have been written in the script. So inside the script, we usually use -a, not -i. But when do we use -i? We use the -i option when we already have a firewall with a lot of rules and we want to drop or accept a specific IP or port by writing the IP tables rule at console, so without changing the firewall script. Bear in mind that there is always the possibility to already have a rule which accepts the traffic. For example, let's say there is a rule that accepts web traffic from any IP address and I want to drop a specific IP address. Then I must add the rule that drops the traffic before the rule that accepts the traffic, and I do that using -i option. For example, at this moment, all SSH traffic is dropped, and I want to add a rule that accepts traffic from this IP address, from the IP address of Linux 2. I'm adding the rule using -i. IP tables, -i input, -s the IP address, -j drop. Sorry, I want to accept traffic, not drop it. This rule will be the first in the chain and will accept traffic from 192.168.0.20, even though there are other rules that could drop the traffic. Those rules are anyway after the rule I've just written. And you see that SSH is working. In this lecture, we'll take a look at how to obtain information about the IP tables firewall. Listing the firewall means showing the tables and chains contents, and that means listing rules, the default policy, and traffic statistics. There are two main options, -s and -l. Let's take a look at some examples. IP tables -l. -l is often used with -n to avoid long reverse DNS lookups. Using -n option, IP addresses and port numbers will be printed out in numeric format. We see 22 and not SSH. Then -v, which comes from verbose, shows interface names, packet and byte counters. It shows how many packets and bytes have been matched by each rule. By the way, it's very common to write IP tables minus V and L. V and N are written in lowercase letters and L in an uppercase letter. In all these examples, I've listed only the filter table, which is the default. If we want to list other tables, we should specify the table's name using -t option like this: IP tables minus tnet minus V and L. And it printed out all the chains of net table. Or IP tables minus T mangle minus V and L. It printed out the mangle table and the raw table. There are only two chains, pre-routing and output. Okay, that's how we list the firewall. Thank you. Welcome back. This lecture will be about policy. Traffic filtering is done in the filter table of the input chain for incoming traffic, of the output chain for outgoing traffic, and of the forward chain for routed traffic. Rules are added to chains and tables and traversed in order from top to bottom by the packets. Each packet is then checked against each rule in turn, starting at the top. If it matches the rule, then an action is taken, such as accepting or dropping the packet. Once a rule has been matched and an action taken, the packet is processed according to the target of that rule and isn't processed by further rules in the chain. Now, if a packet passes down through all the rules in the chain and reaches the bottom without being matched against any rule, then the default policy for that chain is applied. The default action is referred to as the default policy and may be set to either accept or drop. The concept of default policies raises two possibilities that we must consider before deciding how we are going to organize the firewall. So when organizing our firewall, we should have the following options in mind. We can set the default policy to drop all packets and then add rules to specifically allow packets that may be from trusted IP addresses or for certain ports on which we have services running like FTP, web, email, and so on. Or the second possibility, we can set the default policy to accept all packets and then add rules to specifically block or drop packets that may be from specific IP addresses or ranges or for certain ports on which we have private services. Generally, the first option is used at least for the input chain and is considered more secure. By default, policy is set to accept any packet that hasn't been dropped by any rule. Policy can be changed for chains that have the filter table and they are input, output, and forward. We cannot change the policy for pre-routing or post-routing chains. Let's take a look at some examples. We can check the policy by listing the firewall IP tables minus VNL. This is the default firewall for a Linux operating system. We see the default policy is accept for input, output, and forward chains. Note that there is no rule in the chains, so all traffic is permitted. Now, I'll continuously ping this Linux and also check the SSH connection. Ping and the IP address of Linux 1. Ping is working. And now SSH. SSH is working too. Both incoming ping and SSH are working. Now if I set the policy to drop on input chain, all the traffic will be dropped. There is no rule that accepts traffic, so all traffic is dropped. IP tables minus P, an uppercase P, input drop. This is how we set the policy. We see that the policy is dropped, and it has already dropped for packets. Ping has stopped. It doesn't work anymore. Setting the drop policy on input chain without any rule that accepts traffic is like I've logically disconnected the host from the network. Now I'll add a rule that allows incoming SSH traffic. The input chain is incoming traffic, the protocol is TCP, the destination port 22, minus J, the target, is accept. Let's try to connect using SSH again. And it's working. We notice how SSH client can connect to the server again. The SSH traffic is permitted by this rule. But what about ping? Ping is still not working. Ping packets are dropped by the policy. There are 15 packets dropped. Now there are 19 packets, 22 packets, and so on. Ping is continuously sending packets to Linux One. If I want to permit incoming ICMP ping packets, I should add a rule that accepts that traffic. Also note that policy is always at the end of the chain. It's not possible to add rules that match against packets after the policy. At the end of this lecture, I'd like to tell you something important. Take care when changing the policy on remote servers. There is always the possibility to block yourself from accessing the server anymore. First, be sure that you've added a rule that allows your own traffic, and only then change the default policy. Keep this in mind. If you want to completely flush all IP tables rules and reset to an open firewall state, you should set the accept policy on all chains, flush all netfilter tables, and delete all IP tables user-defined chains if there is any. This is useful to use at the beginning of any firewall script in order to flush everything and build it from the ground up. I'm creating a script named delete firewall.sh. The first step is to set the accept policy on all the chains of the filter table. They are input, output, and forward. Forward chain is used only for routed packets, and that means that the Linux machine has also the function of a router. IP tables minus P input accept, IP tables minus P output accept, and IP tables minus P forward accept. The second step is to flush all tables that have rules. IP tables minus T filter minus F, IP tables minus T net minus F, IP tables minus T mangle minus F, and IP tables minus T ra, the last table, minus F. If the table has no rule, nothing happens. And lastly, delete user-defined chains, if any. This is optionally and needed only if there are user-defined chains. We'll talk about user-defined chains in another lecture. IP tables minus X. If you are using IPsec to drop large collections of IP addresses like entire countries, you should also flush and destroy the secs. There will be a dedicated section about IPsec later in the course. Okay, that's all. I am saving the script. Then I make it executable and run it. The IP tables firewall has been cleared out and all traffic is permitted. By the way, this is also the default state of a Linux operating system. In this lecture, we'll talk about saving IP tables rules from memory to a file on disk and load them back into the RAM memory at system boot time. Firewall rules created using the IP tables command are stored only in the RAM memory. If the system is restarted before saving the IP tables rule set, all rules will be lost. If you want your firewall rules to persist after a system restart, make sure to save them first. There are two commands that are used to dump IP tables rules from the RAM memory to a file and respectively to load rules from a file into memory. These two commands are IP tables save and IP tables restore. The first command dumps rules to standard output or to a file, and the second one loads rules from a file into memory. Let's see how they work. I'm executing a script that contains some IP tables rules. At this moment, there are some IP tables rules loaded into memory. I'm listing the firewall. And there are some rules loaded into memory. And I'm running iptables -save. Iptables -save is dumping the iptables rules to standard output, which is the terminal. Using output redirection, I can redirect and save them to a file like this. iptables -save, the output redirection, which is the greater than sign, and a file. Let's say my firewall. The output has been redirected to my firewall, and the file has been created. I am listing the file. And we see the output of the command. At a later moment, I can load the saved rules into memory by running iptables -restore and the name of the file, like this. iptables -restore and the file, my firewall. The rules have been loaded from file into memory. Good. Let's see how to restore the iptables rules after system restart. The solution is based on the Linux distribution we are using. Let's see how it's done on Ubuntu and Debian-based distributions. There is a package, a program, named iptables persistent. This program is not installed by default in Ubuntu, but it belongs to the standard repositories and I can easily install it. I'm gonna install iptables persistent. I'm already root, so it's not necessary to prefix commands with sudo, and I'll simply run apt update && apt install iptables -persistent. During the installation, you will be asked if you would like to save the current iptables rules, the rules from the RAM memory, and set them to be automatically loaded at system boot time. Select yes if you are happy with your current configuration and you have tested your ability to create independent SSH connections to this Linux machine. In my case, I'll select No. And the same for IPv6 rules. Once the installation is complete, you'll have a new service called iptables persistent that is configured to run at boot time. This service will load your iptables rules into memory and apply them when the Linux machine will start. iptables persistent will automatically load the rules from /etc/iptables/rules.v4 for IPv4 or rules.v6 for IPv6. The next step is to save the iptables rules using iptables save command to /etc/iptables/rules.v4. Let's do it. There are some rules in the memory, and I'm running iptables -save. As we've already seen, iptables save is dumping the iptables rules to standard output, which is the terminal. And using the output redirection, I'll save them to /etc/iptables rules.v4. This file will be loaded automatically into memory by iptables persistent at boot time. Let's test it. I will reboot the system. The system is rebooting, and I'll pause the video until the system is up and running. Okay, it's ready. I'm opening a terminal and checking if the iptables rules have been loaded into memory. First, I'm becoming root. And then I'm running iptables -v-nl. And the rules are there. They have been loaded by iptables persistent. Now if you want to update the persistent rules with new rules, you simply add new rules and redirect the output of iptables save to the same file. Let's see an example. Suppose we add another rule that's dropping incoming packets from a given network. iptables -i input -s 11.0.0.0/16 -j drop. I've used -i from insert and not -a from append to be sure that packets will be dropped. This will be the first rule on the input chain and will drop the packets. If I run iptables -save, okay, we see that the new rule is there. And now the redirection. iptables -save, the output redirection, etc iptables rules.v4. Now rules.v4 contains also my new iptables rule. And all rules from the file will be loaded at system boot time. Okay, that's how we configure iptables rules to be automatically loaded into the RAM memory at system boot time on Debian or Ubuntu-based distributions. Let's move on and take a look at a specific way for Red Hat or CentOS. To save netfilter rules, type the following command as root: service iptables save. This executes the iptables init script, which is different from the iptables command, and runs the iptables save program that writes the current iptables configuration to /etc/sysconfig/iptables. The existing iptables file, if there is any, will be saved as iptables.save. Next time the system boots, the iptables init script reapplies or restores the rules saved in /etc/sysconfig/iptables by running iptables-restore command. Okay, that's how you save and restore the iptables firewall rules on Red Hat or CentOS. That's all. Now you have the knowledge to save and restore iptables rules at boot time. Thank you. In this section, we'll start a series of lectures about iptables basic matches, which are also the most used ones. As I've already told you, each iptables rule has a matching component and an action component. iptables rules can be constructed to match traffic by protocol type, destination or source address, destination or source network, destination or source port, input or output interface, header fields, or connection state, among other criteria, and these can be combined to create very complex rules. In this lecture, we'll take a look at how to filter traffic based on source or destination IP or network address. We can match packets by source IP address or by source network address using -s or -- source match option. Address can be either a single IP address like 192.168.0.1, a network IP address with a /mask specification like 10.0.0.0/8, or a domain name like www.linux.com. Please note that specifying any name will be resolved with a DNS query, and this is not always a good idea. Let's take a look at some examples. I want to drop all incoming traffic from Linux 2, which has the IP address of 192.168.0.20, okay, from this Linux machine to Linux 1, to the firewall. And I write iptables -a input. I am using the input chain because it's incoming traffic, -s, this means the source IP address, and the IP address of Linux 2, of the other machine, 192.168.0.20, -j, and the action, drop. Before hitting enter, I'll ping Linux 1 from Linux 2. Ping is working, and I am hitting the enter key. And ping stopped. If I list the firewall, I see that there are 8 matched and dropped packets. If we want to drop by destination IP address, we use -d or -- destination instead of -s when writing the iptables rule. In the next example, I'll write a rule that drops outgoing traffic to an entire network like 8.0.0.0/8 to this network. At this moment, I can communicate with that network. It's working. And iptables -a output, it's outgoing traffic, so I am using the output chain, -d, and the destination network address, 8.0.0.0/8. -j, drop. Now, ping is not working. And if I list the firewall, I'll see a lot of matched packets. There are 2 dropped packets. So this rule drops any packets destined to an IP address that starts with 8 or its first byte is 8. Perfect. Let's continue on and see another example. I want to completely deny access from this Linux machine to a website like, say, www.ubuntu.com. For this task, there are more possibilities. The first one is to find the IP address or the IP addresses, if there are more, of www.ubuntu.com and then drop all the packets that are going to those addresses. You can find the IP address of a website using either NSLookup or dig. NSLookup www.ubuntu.com. And we see the IP addresses of www.ubuntu.com. And dig www.ubuntu.com. These are the IP addresses of that website. Keep in mind that NSLookup works both on Windows and Linux, but dig is a Linux-only command and has more options available. We notice that there are 6 IP addresses for this domain. If we want to deny access to the website, we must write 6 IP tables rules, and each rule will drop one IP address. I'll write just an IP tables rule as an example. IP tables minus A output, this is outgoing traffic, minus D, and I'll take an IP address from this list. Let's say the first one. Minus J drop. Of course, at this moment, the access to the website is not denied because there are still 5 IP addresses that are permitted. The second possibility is to use the domain name in the IP tables rule. It will automatically query the system DNS server for the IP addresses and add a rule for each IP address. IP tables minus A output minus D www.ubuntu.com minus J drop. And IP tables minus V N L. I am listing the firewall. And we notice that there are 6 rules, one rule for each IP address, that drop the outgoing traffic to those IPs. If I open up a browser window and try to connect to www.ubuntu.com, it won't work. The website is not loading. Notice that when dropping traffic based on source or destination IP address and you use a domain name instead of an IP address, at the end, IP tables still uses IP addresses and not the domain name. I've used a domain name, but IP tables uses IP addresses. This requires access to a DNS server, and that means other IP tables rules that allow DNS traffic. Pay attention, especially when using the drop policy. It may be the case when you cannot permit or deny traffic to or from an IP address because you have specified the domain name, but the DNS traffic that resolves the domain name is not permitted. Also note that it's not a good idea to accept or drop traffic to a very big website like google.com or facebook.com this way. Domains like google.com have tens or hundreds of IP addresses, and the DNS response will contain only a few of them. You should use an application firewall like Squid instead of IP tables. At the end of this lecture, I just want to tell you that if you see the address 0/0, it means any IP address with any network mask. For example, I accept all outgoing HTTPS traffic and I write IP tables minus A output minus PTCP minus D port 443, this is HTTPS traffic, minus D, and now the destination IP address. And I write 0/0. It means any IP address with any mask. Minus J accept. Okay, that's all about matching by source or destination IP address. Thank you. In this lecture, I'm gonna talk about filtering packets using an IP range. When creating your IP tables firewall, it's important to keep it as simple as possible. It's always preferable to use a single rule that does the job of other 10 rules. If we want to accept or drop packets from the IP address in the range of 10.0.0.0.10 to 10.0.0.29, we have to write 30 different IP tables rules, and this is not scalable at all. The -S and -D IP tables matches are used to match traffic from a single IP or network address. It's not possible to specify a range of IP addresses. Fortunately, there is another match that allows matching traffic sourced from or destined to a range of IP addresses. That match is -M IP range. And there are two different options. -SRC- range used to match by source IP address in the specified range, and -DST- range, which is used to match by destination IP address in the specified range. This is an example that's dropping incoming TCP packets to port 25, which is SMTP, if the source IP address is in range of 10.0.0.10 and 10.0.0.19. The first IP tables rule is dropping incoming SMTP packets to port 25 if the source IP address is 10.0.0.10. The second rule is dropping traffic if the source IP address is 10.0.0.11, and so on. I'm sure you can imagine that it's not scalable at all. If you want to drop 100 IP addresses, you have to write 100 IP tables rules. Now, instead of writing 10 rules, I could simply write a single rule using -M IP range match option. Let's see how it's done. All these 10 rules can be replaced by a single rule like this. IP tables -A input -P TCP -D port 25 and -M IP range -SRC range. I'm matching by source IP address and the range 10.0.0.10, the first IP address, a minus sign, and the last IP address 10.0.0.19 and -J drop. Now I can comment out these 10 IP tables rules and the final result will be the same. I'm commenting out the rules. I'm saving the script and then run it. IP tables -VNL. I am listing the firewall. And we see the rule. It's always easier to understand and manage a firewall with fewer rules. Another match that we can use is -M ADDR type, which comes from address type. We can match packets based on the type of the address. There are many address types, but the most important and used ones are unicast, multicast, and broadcast. You can see all the types by executing iptables -m ADDR type --help. These are the types. And I'll show you an example. I'm dropping all outgoing multicast packets or outgoing packets that have the destination IP address of type multicast. I suppose I don't want to advertise or join to any multicast group. iptables -a output -m ADDR type -DST -type multicast -j drop. Hello everybody and welcome back. In this lecture, I'm gonna show you how to filter traffic by TCP or UDP ports. This is a very common task when developing a firewall. You can match by a single port using the match option --d port, which comes from destination port, or --s port, which comes from source port. It's mandatory to specify TCP or UDP protocol using -p match option, otherwise you'll get an error. Keep in mind that there are ports in the packet header only if the protocol is TCP or UDP. Other protocols, like for example ICMP, do not use ports at all. In this example, we are dropping incoming SSH packets. It's incoming traffic because the chain is input, the protocol is TCP, and the destination port is the standard SSH port. We assume that there is an SSH server that is listening on port 22. If we want to match by multiple ports, we can write more iptables rules, one rule for each port, or we can use another option which is -m multiport. There are two other options, -s ports to match by source ports and -d ports to match by destination ports. After that match option are coming the ports separated by commas. Let's take a look at this example. We are accepting outgoing traffic, it's the output chain, to port 80 or 443. This means traffic destined to HTTP or HTTPS servers. Perfect. Let's go to a terminal and see some live examples. From Linux 2, I want to see what ports are open on Linux 1. In order to check what ports are open, I'll use nmap, which is by the way a great port scanner. nmap and the IP address of the other Linux machine, 192.168.0.10. After a few seconds, nmap will show us what ports are open on Linux 1. As you can see, there are 4 ports open. 22 for SSH, 25 for SMTP, 80 for HTTP, and 443 for HTTPS. I've flashed all the rules, so at this moment it's an open firewall and all traffic is accepted. This is the state where I'm starting from in each example I'll show you. There is no rule and the default policy is set to accept. And I want to drop incoming traffic to port 25. iptables -a input, it's incoming traffic -p TCP, -d port 25, -j drop. And I am listing the firewall again. We can see the rule here, and there are no packets matched. I'm scanning Linux 1 again from Linux 2 using nmap. I'm executing the same command again. And we notice that port 25 is now filtered. By the way, do you know what is the difference between a filtered and a closed port? A filtered port is in fact an open port, but there is a firewall that's dropping traffic to that open port, and we are receiving no traffic back when sending a packet to that port. In this case, port 25 is open on Linux 1, so there is a process that's listening on that port, but it appears filtered to Linux 2 because packets are dropped. On the other hand, a closed port is a port on which no application is listening. If we send a packet to a closed port, we receive a packet back indicating that the port is closed. That's a TCP packet with the reset flag set. For example, port 55 is closed. So as a conclusion, a filtered port is an open port that doesn't respond back because a firewall is dropping the packets, and a closed port is a port where no application is listening and it responds back with a TCP reset packet indicating that it's closed. Now on Linux 1, if I list the firewall, I'll see some matched packets. There are 2 matched packets. Let's try other examples. I want to block all incoming traffic to port 80. Let's check if port 80 is open, closed, or filtered. And it's open. I'm gonna create a new firewall rule that will block all incoming traffic to port 80. In fact, it's the same rule, just that instead of port 25, I have port 80. I'm listing the firewall. There is no matched packet, and if I scan it again, we see that the port is filtered and there are matched packets. There are 3 matched packets. Let's move on and see another example, which is a very common and useful one. We suppose there is a Linux server and a management station, and we want to allow only the management station to connect to the Linux server using SSH. Or, in other words, we allow a single source IP address to connect to Linux 1 using SSH. In this example, it will be the IP address of the Windows recording machine. All other source IP addresses will be denied. Let's check what is the IP address of this Windows machine. I'm running ipconfig, and we see that the IP address is 192.168.0.112. Okay. For this task, I'm gonna create a bash script, write the rules inside the script, and then execute the script. It's easier to manage the firewall this way. The first line of my script is the shebang and indicates that this script will be run by the bash shell by default. First, I flush the filter table of all chains because maybe I'll run the script many times and I don't want the rules to be appended each time I run the script. iptables -f. We've already discussed about this in a previous lecture. And the first iptables rule will permit SSH traffic from that specific IP address. iptables -a input -p TCP -d port 22 -s and the IP address of my Windows machine. -j accept. This rule is accepting the traffic that is coming from the Windows machine. Now you can imagine that we still need something that will drop SSH traffic that is coming from other source IP addresses. There are two possibilities. If the default policy for the input chain is set to drop, it means that the traffic that is not matched by any rule will be dropped by the policy. In this case, we don't need to write another IP tables rule. But if the policy is set to accept, then we mandatorily need a second rule that drops all incoming SSH traffic that was not accepted till that point. In this example, I said nothing about the policy, so I'll write that second rule. IP tables -a input -p TCP -d port 22 -j drop. I don't specify the source IP address, and that means any IP address. If you want to specify an IP address, you can simply write -s 0/0. It's the same. Perfect. That should be enough. Let's save the script and make it executable. Before running the script, I want to check that port 22 is open. So I'm scanning it using nmap from Linux 2. It's open. Now I'm running the script. Let's scan the port again. And the port is filtered. The firewall is dropping the packets that are not coming from the allowed IP address. Linux 2 doesn't have the permitted IP address. If we list the firewall, we see there are dropped packets. From Windows, I am opening PuTTY and trying to connect to Linux 1. I'm writing the IP address of Linux 1. And open. And we see that the port is open. Packets are permitted through the firewall. There are 18 packets accepted by the first rule. In the last example of this lecture, I'll show you how to match by multiple ports in a single IP tables rule using -m multiport match option. I'll try to block the access to port 80 and 443. I'll write the IP tables rules inside the same script. IP tables -a input -ptcp -m multiport -d ports 80, 443 -j drop. Take care that there is an S at the end. So D ports, not D port. And I'm saving the script. Before running it, I'll check the state of those two ports. Port 80 and 443. And they are open. I'm running the script and then scanning the ports again. Okay, the host is not responding at all and nmap thinks that it's not up. I'll add -p, an uppercase P, and 0 to avoid probing the server using pings. Now it says that the ports are filtered, exactly what we've expected. There are 8 matched packets by the rule. In the last lecture, we've seen how to match traffic by TCP or UDP ports. But how can we match the traffic of the protocols that don't use ports? The only protocols that use ports are TCP and UDP, and there are a lot of other protocols out there that don't have the concept of port. Some examples are ICMP, GRE, or routing protocols like OSPF or EIGRP. We can see a list of protocols in /etc protocols. These are the protocols I'm talking about. Excepting TCP and UDP, they are not using ports. There is one major thing about protocols which should be cleared up. Network communication happens on many layers, and each layer has its own set of protocols. The scope of IP tables is limited to the transport layer and below, so we are talking in fact about layer 3 and layer 4 protocols. Be careful not to confuse protocols and service names. Popular services like SSH, HTTP, SMTP, etc. have been assigned to specific ports. So to match by layer 4 protocol, use the -p option followed by the protocol name. For example, I'll allow only TCP and UDP traffic both on input and output chains. All other traffic like OSPF, GRE, or ICMP will be denied by the policy. I am creating a new script called only tcp/udp.sh. As usual, I'm flashing the firewall at the beginning of the script. I'm starting from ground up. Then I'm setting the drop policy on input and output chains. It's always a good idea to allow loopback interface traffic. We'll talk about the traffic of the loopback interface in the next lecture. -I and the name of the loopback interface, -J accept. -O, the outgoing interface, the same LO, -J accept. These two rules accept the loopback interface traffic. And the rules that are accepting TCP and UDP traffic on input and output chains. IP tables -A input, -PTCP, -J accept. IP tables -A output, -PTCP, -J accept. And the same for UDP. This firewall script is accepting only TCP and UDP traffic. All other kind of traffic will be dropped by the policy. I am saving the script, make it executable, and then run it. TCP and UDP are working, for example, dig www.google.com. I am testing the DNS protocol, that means UDP, it's working, but ping, which means ICMP, will not work. Operation not permitted. Packets are dropped by the policy. There are 6 dropped packets, and we can also see 6 messages. Welcome back. In this lecture, we'll take a look at how to match packets based on the interface they are coming to or the interface the packets are going through, are leaving our station. If we want to match packets based on the interface via which they were received, we use the -i option and then the name of the incoming interface. In this example, I allow any incoming packets that are received on the wireless interface named WLAN 0. This option -i is available only for packets entering the input, forward and pre-routing chains. To match traffic by outgoing interface, use -o option and then the name of the outgoing interface. In this example, I allow any outgoing packets leaving our station through the interface named ENP8S0. Also note that this option is available only for packets entering the forward, output and post-routing chains. Also note that if the interface name ends in a plus sign like this, then any interface which begins with this name will match. Also keep in mind that it's always good practice to permit traffic on the loopback interface, which is called LO. By the way, the loopback interface is a special virtual network interface that your computer uses to communicate with itself. It is used mainly for diagnostics and troubleshooting and to connect to servers running on the local machine. Let's take a look at an example. I want to allow incoming and outgoing traffic through the loopback interface. IP tables -a input, -i LO, -j accept. And IP tables -a output, -o LO, -j accept. You can always add these two rules at the beginning of your firewall script. We'll see later that we can create more complex rules using these matches. For example, we can load balance traffic based on the outgoing interface. Imagine we have a Linux router with two internet connections and say SSH, HTTP and HTTPS traffic leaves the router on the first interface, which is in fact the first internet connection, and email traffic leaves the router via the second interface or the second internet connection. We'll dive deeper into this in the NAT section. At this point, we've seen many examples on how to match packets based on certain conditions. However, in some cases, you may need to negate these matches. IP tables provides the negation operator, which is an exclamation mark, for this purpose. A very common use case scenario is to allow traffic to a specific service only from a given IP address. Let's say we have a web application that uses the HTTPS port that can be used only from a specific IP address or network. And the IP tables rule that does this is IP tables -a input, not -s, and the IP address of the allowed host. For example, the IP address of Windows. -p TCP -d port 443 -j drop. This will drop all TCP traffic that's coming to port 443 except that from 192.168.0.112. Or, in other words, if the source IP address is not this IP, drop the packet. Let's test it. I'll check the HTTPS port from Windows. and I'm using telnet to scan the port. Telnet, the IP address of Linux 1, and the port. And we'll see that the port is open. Now, let's scan the port from Linux 2. I'll use the same telnet command. Telnet and the IP address of Linux 1. And the port. Sorry, the command is telnet. And it's not connecting. The port is filtered. Only the IP address of the Windows machine is allowed to communicate with this port. Negations are very useful sometimes. Nowadays, most of the network traffic uses TCP. Web, email, FTP, telnet, SSH, and so on. All these protocols use TCP as the layer 4 protocol. It's common to match traffic based on TCP flags. For example, each new connection is established by packets with SYN flag set. To match packets that have the SYN flag set, there is the --SYN option. It matches when only SYN flag is set. Another possibility is to use --TCP- flags match option, which has two arguments. The first argument is called mask and represents the flags which we should examine, written as a comma-separated list. The second argument, called comp, is a comma-separated list of flags which must be set. To match by TCP flags, you should know which are these flags. SYN comes from synchronize and is used for TCP three-way handshake or connection initialization. The first packet of any TCP connection has this flag set. ACK comes from acknowledgement, and every TCP packet has it set excepting the first one, which has only the SYN flag set. FIN or FIN comes from finalize and is used for closing the connection. RST comes from reset and is another possibility to close the connection. Then there are URG from urgent and PSH from push. These last two flags are not used too often. And all, which means all TCP flags are set, and none, which means that no TCP flag is set. Let's see some examples. I want to block incoming TCP connections to port 22. To do that, I could block only the first TCP packet, the packet that initializes the connection, and that packet has the SYN flag set. I'm scanning port 22 on Linux 1 from Linux 2 to see if it's open. Nmap -p22 and the IP address of Linux 1. And it's open. Back on Linux 1, I'll add an IP tables rule that drops incoming TCP packets to port 22 if they have the SYN flag set. IP tables -a input -ptcp -d port 22 -SYN -j drop. Back on the other Linux machine, I'm scanning port 22 again. And it's filtered. The firewall is dropping TCP packets with SYN flag set. If we list the firewall, we see that there are dropped packets. There are two dropped packets. Let's try another example. I want to permit incoming SSH connections only from a specific IP address. Maybe there's a management station or a location from which SSH is allowed. In this example, the permitted IP address will be the address of Windows. How can I do that? First, I'll clear the firewall. I want to start from ground up. Now there is no rule and the policy is set to accept. For this task, I'll use an IP tables rule similar to the last one. Actually, I'll add another match with a negation. This is the last rule. And I'll add this option, NOT, -s, and the allowed IP address, the IP address of Windows. This part means match the packet if the source IP address is not this one. We can describe the entire rule like this. If incoming packets are of type TCP with the SYN flag set and the destination port is 22, drop them if the source IP address is not 192.168.0.112. Or in other words, only this IP address is allowed to establish a new SSH connection. I'll scan port 22 from this Linux machine. And it's filtered. And the same from Windows. This is the allowed IP address. I'm using Telnet. Telnet and the IP address of Linux 1. And port 22. And the port is open. Of course, you can also test it using PuTTY. We notice that the port is open. Hello and welcome back. In this lecture, we'll dive into stateful firewalls. NetFilter has a module called Contract that permits us to inspect and restrict network connections using a method called connection tracking. Connection tracking refers to the ability of maintaining state information about a connection in memory tables. Firewalls that do this are known as stateful and are much more secure than their stateless or packet-based counterpart. The decision to drop or to accept a packet is not taken anymore based on the values in the packet headers like source or destination IP addresses or ports, but on the relation the packet has with other packets. For a packet, there are the following states defined. A new packet is the first packet of any connection. It's in fact the packet requesting a new connection, such as a TCP packet with the SYN flag set or the first ICMP echo request packet. Packets in the established state are those that are already part of an existing connection. All packets of the connection starting with the second packet and until the last one are in the established state. Related packets are those that are requesting a new connection but are already part of an existing connection, such as FTP data transfer or an ICMP error. In general, it's good practice to accept these packets. An invalid packet is not part of any connection in the connection tracking table. These packets cannot be identified in any state. Generally, it is a good idea to drop everything in this state. And the last state is called untracked and it's not so often used. Briefly, if a packet is marked within the raw table with the no track target, then that packet will show up as untracked in the state machine. Note that you can use the stateful functionality of IP tables connection tracking with any network protocol even though the protocol itself is stateless, such as UDP or ICMP. To match packets based on their state, use -m state, --, state, and then a comma separated values of packets states written in uppercase letters. In this example, we are accepting incoming packets if they are already part of an existing connection. Another rule or the policy of the input chain could drop the first packet of the connection which is in the new state. This means that the host can connect to any destination using any protocol, but no one is allowed to connect to services running on the host. This was just an introduction to stateful firewalls. In the next lecture, we'll see a real example of how to configure a stateful firewall using IP tables. In the last lecture, we've discussed about stateful firewalls and how do they work. Let's go to the terminal and create a stateful firewall from scratch, which is very good for a desktop operating system. This is the kind of firewall I'm using on my personal laptop, and I can say that I haven't had any problems in years. I'm gonna create a bash script that contains all IP tables rules. At the beginning of the script, I'm flashing the filter table of all chains, IP tables -f. Then I allow loopback traffic. Always allow loopback traffic on input and output chains. IP tables -a input, -i the incoming interface, LO -j accept. And the same for the output chain. Now we have the outgoing interface, which is LO -j accept. The loopback traffic is permitted. The rules until this point could be part of any firewall. I'm starting the stateful firewall part. As I said earlier, it's a good idea to drop invalid packets on input and output chains. These are the packets that cannot be identified in any state. IP tables -a input, -m state, --- state, invalid. -j drop. And the same for the output chain. This kind of firewall is very good for a desktop operating system. This means that there are no services running or no one connects to them from the outside. The host communicates to any destination and uses any protocol, so all outgoing traffic is permitted, but only the return traffic is allowed. This means that I should accept on the input chain only the packets that are in the established or related states. This is the return traffic. And on the output chain, I'll allow packets that are in new, established, and related states. It means all traffic, including packets that initialize new connections. IP tables -a input, -m state, --- state, established, comma related, -j accept. Always write the states in uppercase letters. And the rule for the output chain for outgoing traffic. IP tables -a output, -m state, --- state, and we have new packets that establish new connections, established, and related. -j accept. And finally, I set the policy to drop on input and output chains. All traffic that was not priorly permitted will be dropped. IP tables -p input drop and IP tables -p output drop. That's all. I'm saving the script, and then make it executable and run it. Let's test outgoing traffic. Ping 8.8.8.8. And ping is working. Let's test HTTP or HTTPS. HTTPS is working. And I also test SSH. I'm going to connect to Linux 2. And SSH is working. Perfect. Now, let's test new incoming connections. From Linux 2, I'll ping Linux 1. Ping and the IP address of Linux 1. And ping is not working. Packets are dropped on the input chain. Let's test SSH. SSH is not working. All packets that initialize new connections are dropped on the input chain. No new incoming connections are allowed, and this is secure. Let's list the firewall. And we see packets dropped by the policy on the input chain. There's also an invalid packet that has been dropped. This is very good, but however, there are cases when we want to allow new incoming connections from a specific IP address or protocol. For example, we want to allow incoming SSH connections only from a management station, so from a given IP address. How could we do that? It's very simple. At the beginning of the script, we add a rule that permits incoming TCP packets which are in the new state if the protocol is SSH and the source IP address the given one. In the same script, somewhere at the beginning, I'll add a new rule. In fact, it doesn't matter where I add the rule, but it's better to be at the beginning because I want to permit the packet fast now after many other rules have been checked. So IP tables -a input minus PTCP minus D port 22, and now the new state -m state minus state new minus s the given IP address, the IP address that is allowed, and it's Linux 2. -j accept. I'm saving the script and then test it again. I'm running the script, and from Linux 2, I'll try to connect using SSH to Linux 1. And now SSH is working. Perfect. Let's list the firewall again. And we see there's one packet that has been accepted by the new rule. Welcome back. If you want to match packets based on source MAC address, use the -m MAC match option. Note that you can filter Ethernet or wireless traffic only by source MAC address and not by destination MAC address. This match could be very useful sometimes. Imagine you have a server in your local network and want to allow only a list of trusted machines to access the services that are running on the server. Or you have a NAT router that is running Linux and want only the corporate devices to access the internet. Or in other words, you don't allow devices that are not yours or trusted in your network. Keep in mind that MAC addresses are only valid inside the local area network. The first router towards destination will change the source MAC address of the packet with its own MAC address, the MAC address of its outgoing interface. Also note that you cannot impose a strong security policy based on MAC addresses because MAC addresses can be spoofed easily. When we want to match packets by source MAC address, we use -m MAC match. In this example, we are dropping any incoming packets, it's the input chain, that are coming on WLAN 0 interface and have that given source MAC address. Let's see two more use cases. The first task is to drop incoming packets that are coming with a specified MAC address, and the second task is to configure the net router, which of course is running Linux, to permit the access to the internet only to a list of trusted devices or MAC addresses. Let's do the first task. I'll drop all incoming traffic to Linux 1 if the source MAC address is that of Linux 2. MAC belongs to layer 2, so if you are dropping by MAC address, you are dropping all protocols like IP, ICMP, TCP, UDP, and so on. First, I want to test that the connection between Linux 2 and Linux 1 is up. Perfect, ping is working. Let's see what is the MAC address of Linux 2. This is the MAC address and I'll copy it to the clipboard. And on Linux 2, I'll write the iptables rule. iptables minus a input, x incoming traffic, minus m MAC, minus MAC minus source, and I'll paste the MAC address. Minus j drop. Let's ping this host again. We notice that ping is not working anymore. I am stopping the ping command. Back on Linux 1, let's list the firewall. And we see a lot of matched and dropped packets. All packets that have this source MAC address will be dropped. Let's move on and do the second task. I'm gonna create a script and write there all the necessary iptables rules. As in all other examples, at the beginning of the script, I am flashing the forward chain. Because there could be tens of MAC addresses that I must permit, I'll define a new variable and store those MAC addresses in that variable. So this is the name of my new variable, permitted max equals, and a list of MAC addresses separated by comma. The first MAC address, the second MAC address, the third, and so on. I'll change something at each MAC address to have different addresses. It's good practice to write variables in uppercase letters. Don't use spaces on the left and right side of the equal sign and use white space between addresses. Now, using a for loop, I'll iterate over the list of MAC addresses and run an iptables rule for each MAC in the list. So for MAC, this is a temporary variable in $permitted max. Do and done. Between do and done, we have the for block of code. So iptables minus a forward, remember that we are a router, minus m MAC, minus MAC minus source, $MAC, minus j accept. And I'll print out a message to know what the script is doing. Echo $MAC permitted. And finally, I'll set the policy to drop on the forward chain. So all other packets that were not accepted will be dropped. iptables minus p forward drop. Perfect. I am saving the firewall. Then I'll make it executable and run it. We see how these 4 MAC addresses have been permitted. Only the packets from devices with those MAC addresses can access the internet. This kind of script is useful also for a local server. If you want a LAN server to be accessed only by a list of trusted hosts, you just replace the forward chain by the input chain. When you want to add or to remove a MAC address from the list, you simply remove that address from the list, save the script, and run it again. I have removed 2 addresses. Sorry, I've noticed a small error. Here's the forward chain, not input. Okay, I am saving the script and then run it again. Now, only these 2 MAC addresses are permitted. You see that it's very easy to add or to remove MAC addresses from the list. As a sysadmin, you may be asked to control access to a couple of services based upon day and time. For example, the company intranet server should only be available from Monday to Friday between 8 a.m. and 6 p.m. In this lecture, I'll show you how to filter traffic based on the date and time the packet is received, generated, or routed. There is the -m time match that is very flexible and has many options like date start, date stop, time start, time stop, month days, and week days. You can see all options by running iptables -mtime --help. These are all options of -mtime match. Note that by default, NetFilter uses UTC and not the system time. On my computer, it's East European time, which means UTC +2. So the UTC hour is 14, not 16. The ---- kernel TZ option makes NetFilter use the system time instead of UTC time. But pay attention, I've seen different Linux distributions that used only UTC even though kernel TZ option was given. Let's move to a terminal and take a look at some examples. In the first example, I want to permit SSH traffic only between 10 a.m. and 4 p.m. on weekdays, and in the second example, I want to allow access to a specific website only after working hours. We suppose this machine is the router. I'll create a script and write all iptables rules in that script. First, we flush all chains because we'll execute the script many times and don't want the rules to be added each time we execute the script. We want to permit incoming SSH traffic only between 10 a.m. and 4 p.m. or 16 on weekdays. So iptables -a input -p TCP -d port 22. This is SSH traffic -m time --time start 10:00 and --time stop 16:00 -j accept. Use 24 hours format when writing the time. And another rule that drops packets if time is not between that time interval. This is necessary only if the policy is set to accept. In fact, it's the same rule, but without the -m time match. This is the second rule. And of course the target is drop. The rule on line number 6 will drop packets that haven't been accepted by the rule on line 5. I'm saving the script, then make it executable and run it. From the other Linux host, I'll connect to the firewall using SSH. And SSH is working. Packets are permitted. I'm listing the firewall. And we notice that 13 packets have been accepted by this rule. We are in that time interval. Look how it used UTC and not East European time. So in fact it's 14, not 16. To test it properly, I'll change the time when the rule that accepts the traffic is active. Let's say that the traffic will be permitted only between 3 and 5 a.m. 3 and time stop is 5. This is AM time. I'm saving it and then run it again. From Linux 2, I'll try to connect using SSH to Linux 1. And it's not working. The rule that accepts SSH traffic is not active at this time. It's active only between 3 and 5 UTC. We notice 5 dropped packets by the second rule. Let's move on to the second task. We want to allow access to a specific website, let's say www.ubuntu.com, only after working hours. This machine is the router, and this is routed traffic, and that means the forward chain. In the same script, I'll add a rule to forward chain that matches HTTPS traffic to www.ubuntu.com. IP tables -a forward, -p TCP, -d port 443, this is HTTPS, -d www.ubuntu.com. And now matches related to time, -m time, -time start, 18, this means 6 p.m. UTC, -time stop, 8:00, -j accept. And the rule that drops outgoing HTTPS traffic to www.ubuntu.com. This is the traffic that hasn't been accepted by the first rule. This is the second rule, and it has the drop target. If the destination IP address is that of the domain www.ubuntu.com and time is between 18 and 8, the packet will be accepted. Otherwise, it will be dropped by the rule on line 10. I'm saving the script and running it. We notice the rules that accept packets destined to the IP addresses of www.ubuntu.com between 18 and 8 UTC, and the rules that are dropping the traffic to the same domain name or the same IP addresses if the time is not in that interval. Sometimes I'm asked by my students, how do I restrict the number of connections with the same source IP address to my server on port 80 or 25? NetFilter has the ConLimit module, which allows you to restrict the number of parallel connections to a server per client IP address, or client address block. We can, for example, permit just 10 new connections to our email server from the same IP address, or 5 parallel HTTPS connections from another IP address. This NetFilter option is very useful to protect against denial of service attacks. This example uses con_limit_match to reject incoming TCP connections to port 25, which is SMTP, if the number of connections from the same IP address is above 5. Notice that in this example, I've used another target, which is reject. Instead of silently dropping the packet, the reject target is dropping the packet and then responding back to the source with a TCP reset packet. We'll have a dedicated lecture on reject target, and we'll see what are the differences between drop and reject and when to use each of them. In this lecture, we'll take a look at the limit match, which is, by the way, one of my favorites. The limit match uses a token bucket and restricts the rate of matches. It will only match a given number of times per unit of time. The -m limit match has two options. The first is --limit, followed by a number which specifies the maximum average number of matches to allow per second. It's possible to specify units explicitly using /second or /minute or /hour, like, for example, --limit 10 /minute, which means 10 matches per minute. The second option is --limit burst, followed by a number indicating the maximum burst before the above limit kicks in. By default, limit burst is 5. For every time unit specified using --limit option that passes without a match, one of the bursts will be regained. This limit match can be used in combination with the log target to do rate-limited logging. Let's take a look at two examples. In the first example, the default limit burst is 5, and that means that the first 5 packets will be logged no matter how fast they arrive. After that, we log only 1 packet per minute because the limit is 1 per minute. This match is useful to avoid various denial of service attacks. Let's take a look at the second example. The IP tables rule is accepting 7 new TCP connections because the limit burst is set to 7, no matter how fast they arrive. And after that, it will accept only 2 new connections per second because the limit is 2 per second. If in a second there are not 2 new connections, the burst which has been probably spent will be filled. For every second that passes without matching 2 packets, the burst will be regained with the number of packets not matched in that second. Like if in a second only 1 packet is matched, then 1 burst will be regained, and if in another second no packet is matched, then 2 bursts will be regained. Now I'm going to a terminal and show you a live example. On this Linux machine, I want to limit incoming ping packets to 1 per second with a burst of 7. First, let's see the help of -m limit match. IP tables -m limit --help. And we see those 2 options we've just talked about, --limit and --limit burst. For this example, we need 2 IP tables rules. The first rule will match and accept incoming ping packets, which are in fact ICMP echo request packets, at a rate of 1 per second and a limit burst of 7. IP tables -a input, -p ICMP, minus minus ICMP minus type, echo request. These are ping packets, minus m limit, minus minus limit 1/sec, minus minus limit minus burst 7 minus j accept. Let me explain to you this rule in detail. The rule accepts incoming ICMP echo request packets, and there is like a deposit or burst of 7 packets that will be accepted no matter how fast they arrive. After those 7 packets, only 1 packet per second will be accepted. If there is a second when no packet will arrive, the deposit or the burst will be filled. And we need a second rule to drop packets that haven't been accepted by the first rule. It's in fact the same IP tables rule without minus m limit match and with the drop target. Instead of accept, we have drop, and there is no minus m limit match. And of course minus j. Perfect. Let's list the firewall. And we see those 2 rules we've just written. To test it properly, I want to see all incoming ping packets dropped or accepted. And I'm starting TCP dump, which is a sniffer and packet analyzer like Wireshark, just that it's working in console. It doesn't have a graphical interface. TCP dump, ICMP, I want to see only ICMP traffic, minus n. Minus n comes from numeric, and it's used not to convert addresses and ports to names. It will show them in numeric format. From Linux 2, I'll send to Linux 1 10 echo request packets per second. Ping minus I 0.1 and the IP address of Linux 1. Minus I specifies the sending interval in seconds. It means 10 packets per second. Okay, it's too much. It says I cannot flood. Okay, I'm becoming root and I'm executing the command again. Now it should work. And it's working. Perfect. I'm interrupting the command by pressing Ctrl+C. We noticed how we received 7 replies very fast and then only 1 reply per second. If you look here at this number, you see that the first 7 packets have been accepted and the next 3 have been dropped by the firewall. It skips from 7 to 11. Let's go to server 1 and see the output of TCP dump. Let's go at the beginning. Here. Okay. We notice how these 7 packets have been accepted. 1 echo request, the second echo request, the third, the fourth, and so on till the 7th. These are the first 7 echo request packets. And then only 1 packet per second has been accepted by Linux 1, and for each accepted packet, an echo reply was sent back to Linux 2. Linux 1 has sent 10 packets per second, 9 have been dropped, and 1 accepted. We see how these 3 packets have been dropped. So there is no echo reply for an echo request. This echo request has been accepted and an echo reply sent back to the source. Then Linux 1 has sent 10 packets per second. These are 10 packets, 9 have been dropped, and 1 accepted. I'm interrupting TCP dump by pressing Ctrl plus C. I'm listing the firewall IP tables minus VNL. And we notice both accepted and dropped packets by the IP tables rules. That's all about the limit match. Thank you. Hello guys and welcome back. I'm very excited about this part, and I can say that this is one of my favorite IP tables features. The discussion in this lecture will be about the recent match. The recent match allows us to build a temporary list of denied IP addresses based on whatever criteria we want, and then drop any incoming packets from those IP addresses for a given amount of time. We could, for example, build a dynamic database of IP addresses that have scanned our server and then drop all traffic coming from those IP addresses. Let's take a look at this example, and I'll start with the second IP tables rule, which is dropping routed traffic entering interface called Ethernet 0 if the protocol is TCP and the destination port is 8080. Simultaneously, a list named bad guys is created, and the source IP address of that dropped packet will be added to that list. Later, when a packet arrives and must be routed, it will be inspected by the first rule. The first rule is checking if the source IP address belongs to the bad guy list. This is the name option, and if it's in the list, it will be dropped. The update option updates the last seen time of that particular source IP address, creating a so-called quiet time. Therefore, there must be a quiet time of 60 seconds before another packet from this address will ever be considered. Or in other words, if 60 seconds pass without seeing again that IP address, the subsequent packets from the source IP address will be again permitted. Of course, if they won't be dropped by the second rule, in which case the source IP address is added to the bad guy list again. Okay, let's move on and take a closer look at these match options. The -- name option is creating a list in which the source IP address will be added and checked. -- set is adding the source IP address to the list. And --rcheck is checking if the source IP address is already in the list and doesn't update the last seen time. If the source IP address is in the list, any packet from that source IP address will be dropped for that absolute number of seconds specified. The update option is checking if the source IP address belongs to the list and updates the last seen time. After the last seen time passes without another packet to update it, the source IP address will be allowed to communicate again. This creates a temporary ban or a quiet time. The seconds option is used with update or rcheck and matches the packet only if the source IP address is in the list and the last seen time is valid. Note that the list with blacklisted IP addresses is found in /proc/net/xt_recent/ and the name of the list. Let's go to a terminal and see some live examples. Let's assume that no one is allowed to access port 25 TCP from the outside. And to make it more interesting, I'll say that it's not allowed to access the port between 8 and 10 p.m. UTC time. If someone tries to connect or scan port 25, which is SMTP between 8 and 10 p.m., the source IP address will be added to a list named hackers, and all subsequent packets from that IP address will be dropped for 60 seconds. I'll create a script called recent.sh. I'm creating an IP tables rule that's dropping incoming TCP traffic to port 25 between 8 and 22 or 10 p.m. And besides the rule, it will create a list called hackers and add the source IP address of the packet to the list. IP tables -a input, x incoming traffic, the protocol is TCP, the destination port 25 SMTP, -m time, -time start, and I said 8 a.m., and -time stop 22 or 10 p.m. Use the 24-hour format. And the recent match, -m recent. If I want to continue the rule on the next line, I write a backslash and I press the enter key. And I continue writing the rule. -name hackers, -set, -j drop. Let me explain to you the rule again. When the first TCP packet to port 25 arrives, if the time is between 8 and 10 p.m., the packet is dropped. A list called hacker is created and the source IP address of the dropped packet is added to the list. --name creates the list and --add adds the source IP address to the list. The second step is to add another rule that drops all incoming packets if the source IP address is already in the hackers list. In addition, the last seen time is updated with another 60 seconds. The source IP address will stay in the list for another 60 seconds. This is done by using the update and seconds options. This can be the first rule to drop the packets earlier. So IP tables -a input, -m recent, -name hackers, the list, -update, and -seconds 60, -j drop. If no more packets are coming from that source IP address for at least 60 seconds, new packets from that blacklisted source IP address will be allowed again. Of course, if there is no other rule that's dropping the packets. Let's test it. I'm setting the execution permission on the script and running it. First, I'm checking the time. And we are between 8 and 22 or 10 p.m. Pay attention that IP tables uses UTC time, not local time. From Linux 2, I'll continuously ping Linux 1. Ping is working, and I'm opening a new terminal and scanning port 22 on Linux 1 using nmap. nmap -p25 and the IP address of Linux 1. And ping has stopped. That's because the IP address of Linux 2 has been added to the hackers list and all packets will be denied for 60 seconds if no other packet arrives at Linux 1. The port is filtered. I'm stopping the ping command by pressing Ctrl+C because I want you to notice the quiet time. On Linux 1, I am listing the firewall, IP tables -VNL, an uppercase L. And we see the rules and how many packets were dropped. there's only one packet matched and dropped by this rule, the second rule. That's the first scanning packet. And many other packets dropped by the first rule because the IP address of that packet belongs to the hackers list. When listing the firewall, you notice that we don't see the contents of hackers list. To see its contents, we should display a file from /proc directory. cat /proc net xt_recent and the name of the list, hackers. And we see here the source IP address of Linux 2, which was added to the list and denied, and the updated last seen time in form of a Unix timestamp. There are more last seen times because more packets arrived and each packet has updated this timestamp. Now remember that we have a quiet time of 60 seconds. I think that the time has already passed. Let's check again if ping is working. And ping is working again. 60 seconds have passed without a packet with the source IP address of Linux 2 to be received by Linux 1. But if I send a new SMTP packet to Linux 1, the source IP address will be again banned for another 60 seconds. And I'm scanning port 25 again. The port is filtered and we notice how ping stopped. The IP address of Linux 2 has been added to the list again. In this video, we'll take a look at another interesting match called quota. But what is quota? Generally speaking, quota is a limit set by a network administrator that restricts some aspects of the file system, such as the amount of disk space that can be used by a single user, or the amount of traffic sent or received. In the context of netfilter and IP tables, quota is used to limit the number of packets or bytes matched by an IP tables rule. When the quota is reached, the rule doesn't match anymore. In this example, I'll accept only 1 GB of outgoing HTTP traffic from this Linux machine, which is the web server, to that specific IP address. This means that 80.0.0.1, which is the destination in this case, and our Linux machine, the source, cannot download more than 1 GB of data using HTTP. If more than 1 GB of outgoing traffic is transmitted, the first rule which accepts the packets becomes inactive, and the second rule will drop the subsequent packets. We can create more complex rules, like for example we can set quota per IP or per MAC address, or in combination with the time match, we can set a quota between a starting and an ending time. The requirement could sound like this. Permit no more than 100 megabytes of outgoing HTTP traffic during working hours from a single IP address. As a reminder, 1 kilobyte equals 1025 bytes, 1 megabyte equals 1025 kilobytes, and 1 gigabyte equals 1025 megabytes. This means that a gigabyte is more than 1 billion bytes, but for the simplicity of this example, we consider 1 gigabyte equals 1 billion bytes. Let me show you a live example. I want to permit only 10 megabytes of incoming SSH traffic from Linux 2 to Linux 1. IP tables -a input, -s the source IP address of Linux 2, -p TCP -d port 22, that's incoming SSH traffic, -m quota, - quota, and a value that represents 10 megabytes of traffic. This value will be given in bytes, so 10 million bytes. -J, accept. This rule will be active until the quota is reached, and it means that only 10 megabytes of incoming SSH traffic from Linux 2 will be permitted. And we need one more IP tables rule that drops SSH traffic from Linux 2 to Linux 1 when the quota will be exceeded. IP tables -A input, -S the IP address of Linux 2, -P TCP, -D port 22, -J drop. The second rule will drop any packet that hasn't been accepted by the first one. And that means the traffic over 10 megabytes. If I list the firewall, I'll see no matches. Now, on Linux 2, I'll try to connect using SSH to Linux 1. And SSH is working. I've interrupted the connection by pressing on Ctrl+C. I am listing the firewall again, and we notice 12 matches, 12 packets or 2209 bytes. The quota has not been reached. To test it properly, I'll generate more than 10 megabytes of SSH traffic. There are a lot of packets, so it's difficult to simulate this by simply executing commands in the SSH connection. What I'll do is to use SCP, which comes from Secure Copy, and in fact uses SSH to copy files. And I am creating a file that is bigger than 10 megabytes, and after that I will transfer that file using SCP to Linux 1. file.tar/var. Okay, I'm interrupting the command. I don't want an extremely big file, it's enough. Let's check its size. ls -l, an uppercase S, H, and file.tar. It's big enough, it's 264 megabytes. I'll copy this file to Linux 1. This is incoming SSH traffic to Linux 1. The user that authenticates to Linux 1 using SSH, student, and the IP address of Linux 1. Colon, and the destination. Where will the file be copied on Linux 1? In the home directory of the student user. As you can see, the connection stalled. The quota was reached and the new SSH traffic over the quota will be denied. You don't see exactly 10 megabytes because when SCP is displaying the transferred data, it only approximates it. Back on Linux 1, I am listing the firewall. And we notice almost 10 megabytes of accepted data. Remember that 1 kilobyte is not 1000 bytes, but 1024 bytes. So we'll see a value which is a little bit smaller here. Let's see the size of the file. Home, student, file.tar. And it's 9,5 megabytes. Perfect, it's working as I have expected. Thank you.
Hello and welcome to this episode of T-Tech. This is part 1 of 3 in our 3-part series to set up a network firewall with Linux. So the first part here is I want to introduce the concepts to you. And then in the next part, we're going to actually configure all of this on our new Linux machine. And in the third part, I'm going to walk you through checking to make sure everything is working that we configured. And during that time, I'll also explain why it's working the way it is. So, real quick, anytime we're creating any type of firewall, a custom firewall, what we're trying to do is take an internet connection from our ISP, so our internet service provider. It doesn't matter if it's cable, if it's satellite, if it's fiber, or if it's DSL. Any of the major ones will work just fine. The reason being is a lot of the modems now have an Ethernet port as the customer side of it to connect into your equipment. So we're going to have 2 Ethernet NICs that are going to plug in to our machine. So once we do that, though, and set this up, we're going to essentially have a WAN side and we're going to have a LAN side of our firewall. And the wide area network side is everything we want to keep out, essentially. Yes, we have to use it to get out to things and resources on the internet, but we don't want it talking to us unless we started a conversation, you see? So, it's kind of similar to someone knocks on your door and you check first and then you open the door. You wouldn't want them to just be able to open the door without you telling them they can, see? So, the LAN side, local area network, on the other hand, is everything we have that is trusted. Now, you can control what goes from the LAN to the WAN even further, but normally we allow everything from the LAN to the WAN, but nothing from the WAN to the LAN, unless it has something called state for that. But that is our setup. This is one Ethernet NIC here. This is what this line represents. This is our second Ethernet NIC. This goes into an Ethernet switch. It does not have to be what's called a managed switch. It can just be a normal switch. And then you have these PCs connected. And off of this switch, you would also have potentially a wireless access point. But with that, moving forward, if any of our PCs on the LAN want to talk, PC2, for instance, he's going to use something called ARP. That's Address Resolution Protocol, because Ethernet has to have a MAC address in order to communicate. So essentially, he would just ask for our firewall's machines. The firewall has a MAC address on its NIC. PC2 is going to ask for it, and then it's going to receive a reply from our firewall. But once it gets that, it can send any type of traffic it wants. It has its MAC address now. So, as we see, we send the packet, step 1. Step 2, the switch gets the packet. Remember, switches use the destination MAC address to decide where to switch a frame, so what port it goes out of, and it learns the source MAC address of PC2, so we don't have to repeat the ARP process after the first time. And then, though, the switch is going to forward it up to the Linux machine. Now, the next parts all take place inside our Linux firewall. So, we have something called NAT, and NAT is Network Address Translation. Now, this is only used in IPv4, not in IPv6. There's some use of it, but that is beyond the scope of what we're talking about. Here, though, we are now zooming in on the IP addresses actually assigned to our firewall. The LAN side will have 192.168.1.1, whereas the WAN side will have 192.168.0.25. And these are private because I have a network in place already that this is connected to. So this concept that we're talking about will work the same even once you plug into your ISP equipment. It works the same in a lab as it does in production. This is technically a private address. Yes, it is. but the concept of switching it out will work the same. All right? So, when that packet from PC2 comes in, its source address is 192.168.1.3. It's layer 3 address. Before it is routed out of our Linux firewall, it should be the WAN interface IP address that our Linux firewall has. Otherwise, the ISP will not route it. And as well, you could only have the first PC to send traffic would be the only one that can use your internet connection. All right? So we want to just take that source address at layer 3 in the IP header, and we want to change that to 192.168.0.25. And then after we change that address, that makes an entry, a translation entry. But once this is done, then we can route the packet. So if your computer talks to google.com, once it has the IP of google.com through DNS, it gets its address, it puts that in an IP header as a destination address. And what Linux does is its network stack looks at that destination address, and it has its routing table like as a book, and it compares that destination address value with entries in its routing table. So that allows it to select what's called the outgoing interface or egress interface to route that packet over. In this case, it routes it out of the WAN in this case. So it would route it out of the WAN. All right? And that doesn't create state. That just will route. That's why we have to have a firewall on top of the routing. Because this machine is going to do routing and it's going to do firewalling as well. It's going to do both things, but they are separate functions, even though they're combined in one machine. So, what happens when traffic comes back through? Well, the thing is actually going to happen in reverse. So the first thing that has to happen is it has to come back into the machine. And then that state we discussed, it's going to check that as another of its tables called contract. And that's the state tracking table in Linux. Once it checks that, the traffic from Google, let's say, is going to come back destined at layer 3. The source will be Google's address. The destination will be 192.168.0.25. And what will happen is Linux, if it's in the contract table, if it's part of an existing connection, will change the destination address this time. So it'll be the opposite. And it's going to change that to 192.168.1.3, which is PC2 because he started this connection. It's going to compare that destination address after the NAT reversal takes place. On the way out, we do SNAT. That means source NAT. On the way in, we do DNAT, which means destination NAT. So after the destination NAT takes place, he's going to look at that new destination and send it down. It's going to compare the routing table. The LAN address is what that address falls into. So then he's going to send it, instead of out of the WAN, he'll send it out of the LAN. So in that way, we only let the LAN talk to the WAN, but not the WAN coming in, unless we do something called a port forward, but you don't have to worry about those. And but that's what we're trying to do. That's the big picture, okay? So in the next part, I'm going to set this up on the Linux machine. All right, so I will see you in part 2. Again, this is part 1 of 3 in our Linux Network Firewall series. I hope you enjoyed it this far, and thank you for viewing. And as always, it's Tyler with T-Tech. Alright, hello and welcome to this episode of T-Tech. This is part 2 of 3 in our Linux Network Firewall series. So in this part, we've already found our hardware. We've already done a stock install of Debian Linux in this case. Alright, so the first thing you want to do is make sure you found your hardware that is, of course, compatible and has enough RAM and CPU and everything. In addition, don't forget You gotta find two NICs. You can, if you have a desktop, you can use the built-in NIC, and then you can find a PCI Express or a PCI if it's like a little bit older. And you can plug that in there and then have two interfaces. So as long as we've done that though, we can get started. And what we're going to do is log in as a user, do whatever you created during the installation. And we want to become root with the su command. And now, the first thing to do is back up our interface file. Because in order to make a LAN and WAN interface, we have to assign those addresses. So we want to back up this file here to something ending in .back. And don't be afraid to do this if once you get it running, you're messing around with it. Always make a backup of any config file on your system before you change something and you're not sure. So coming from experience, I've broken a lot of things that way, but that's besides the point. All right, now we have a backup. Let's go into, oh, I'm sorry, I forgot to show you. Type IP space adder here, or ifconfig, but IP adder is a more modern way. And what we want to do is, in my case, ENPS0 number 2 there is my LAN interface. That's where that IP address will be. And number 3 there is ENP0S8. That's my WAN, okay? So that's the interface that's going into your modem. So we're going to go ahead. And now we can go into this file. And if your provider just uses DHCP, that's Dynamic Host Configuration Protocol, you can leave the WAN interface how it is. On the other hand, we used static in our diagram, so we're going to put, after init there, we're going to put static, and then I'm going to put address 192.168.0.25. This next thing after the slash is called the CIDR, the classless interdomain routing. This just means that we have octets in this IPv4 address. What the 24 represents is the bits. So an entire address is 32 bits. And what we're saying with this is 24 bits of this one address can't change. They're part of the network. So that's the subnet. So this means, because each of these sections are 8 bits, that the 192.168.0 is the 20 up to 24. Those are all 24 when you put them together. 8, 16, 24. All right? So when you put all those together, though, those are the ones you cannot change, and that's how the router knows. After that, though, we need a gateway, and it's 192.168.0.2 in my case. Always remember this when you're setting this stuff up. You want to have it must be the case that the gateway is on the same network. So if any of these sections were different, you're not going to be able to route to the gateway because you actually have to use things like ARP or NDP if you're using IPv6. So you have to have that on the same subnet. Your gateway is on the same subnet as your WAN address. Always remember that. So after that, though, let's set up the LAN address. And we need to say allow-hot plug, like this, and then ENP0S3. And now we have to say iface ENP0S3, init, static. We're going to say address 192.168.1.1, use that /24, but on a LAN interface, you don't put a gateway, all right? Don't put a gateway on your LAN. Now we're gonna hit colon and type WQ, and we're gonna write and save the file. Now you want to do if down ENP0S3. Whoops. Make sure it's /sben/if down ENP0S3, and then you want to do sben if up ENP0S3. So now if we do IP adder now, look at number 2, which was our LAN, and now it's got the address and mask we put in there. And if you look at the WAN, which is number 3 still, it has an address, the dynamic address. The reason that is we have to bring that interface down. So just do if down enp0s8, and then we want to say that same if up command. And now if we check, now we have that address. Now on your firewall 2, we have to configure DNS servers. So to do that, you want to go into etc resolve conf. And what we're going to do here is put name server space. I'm going to put external ones on the internet. I'm going to put 4.2.2.2 and 4.2.2.1. Okay, and that will work being external. Again, let's save that file. So now we have our LAN and WAN interfaces configured. At this point, it's a good idea to do a ping. So let's do a ping and make sure you get a reply from the firewall itself. Now, we're going to go into setting up our IP routing. All we have to do is edit this file, etc.sysctl.conf. And in Linux, they've made it very easy. All you have to do is uncomment this one line, and that turns on the forwarding of IPv4 packets. And that just means it will forward a packet that's not destined for itself. From here, we need to configure the firewall. So let's go into etc initd. All right, so we have to make a program that has the rules in it and has them load for us. And we're going to make a shell program for this. So in our boot directory, we're going to make a file called fw, and we're going to start by having an interpreter line, bin bash. And now, if you're familiar with programming, and even if you're not, that's fine, we're going to make some variables, and they're just like an envelope. It holds information. We're going to say LAN, and this will be our LAN interface name, like that. Make sure it's in quotes. And now we're going to say WAN. We're also going to say LAN net. This will be our network for our LAN. So that'll be 10/24. And then our WAN will be 192.168.0.0/24. So after this, let's put in some comments for ourselves. So flush everything on, well, the firewall is called netfilter, so we'll put that in the comment. But essentially, we want to reset ourselves to a default state. We're using the command iptables-F, iptables-tnat-f, and iptables-x, capital X. And that means the chains and tables in netfilter. So we need default policies next. And what we're going to specify is iptables-P input drop, iptables-P forward drop, and iptables-P output accept. Now, the chains here, netfilter has tables and they have chains. A table contains one or more chains. Okay? So the input chain is a part of the filter table. And this input chain processes packets when they're destined for this machine. So if you start Firefox, just for instance, you don't run Firefox on your firewall, but if you start that, this data that goes up and down through the network gets processed through the input chain. So what it means is when a program is listening on a socket to receive data from the network, the data goes through the input chain. So it's for programs on this machine is what that deals with. And what the drop is the policy if it doesn't match a rule in the chain. So it's like a catch-all, okay? Forward is not for applications on this firewall itself. It's actually for routing the packets. These are the rules that decide if a packet can be routed a certain way or can't be routed. So it's not destined for this machine. It's destined for networks this machine is attached to. So our LAN and WAN, that's the example. That's what it's for. So we're going to write rules that control the LAN access to the WAN and vice versa. So everything we don't put in that chain as a rule is just going to be dropped. So it's very secure for us. Now, output, though, is for your applications when they start a connection from your machine. So input is like if data is coming from Firefox into Firefox, but you didn't start a connection. Output is like when you actually go to Google on purpose and it sends the data down first. That is okay, we're assuming. So we're going to say accept, and we actually don't have to write any rules for that chain. All right, so from here, let's go ahead and do firewall destined traffic policy. And we want to add to the end, so append any traffic coming in on the loopback interface. And we want to jump to the target of accept. And also we want to append that any traffic that has a state, so we're using a module with M there, of related, comma, and then established. We want to accept that traffic. We want to also input. We want to accept ICMP traffic to allow pings and stuff to happen. We want that to come in on our LAN interface. And accept. And then IP tables A. We want to accept some traffic for a DHCP server that we're going to set up a little bit later. Alright, that's our input first. And then next, we're going to focus on our forward chain. Alright, so now we need to go ahead and make our forward policy. Now, our forward policy is going to be for our LAN. So this is our LAN to WAN traffic policy, all right? So we're going to say IP tables, and now we're going to append to the forward chain. And then we want to say that the traffic has to be coming in with lowercase I, and we're going to utilize our variable with a $sign to tell our program it's a variable. Do LAN, and then -s for the layer 3 source address in the IP header. Now in this case, we're going to use a $sign LAN net. Now that also has to be routed out of the WAN interface like this. And then once we do that, we want to accept that traffic. Now we also want to go ahead and have it so it matches any existing traffic. So with the module state and then the -- state related, comma, established, like that, and then -j, accept. Now, the last thing we need here is that we need our NAT policy. So this is our LAN to WAN NAT policy. This is not port forwarding. This is the source NAT we spoke about. So this is IP tables. We need to work on a different table this time called the NAT table. The other ones were on the filter table. From there, though, we want to append the rule to the post-routing chain. This is after the routing decision has been made by the networking stack. So if you want to do port forwards for destination NAT, you have to make the decision before you route the packet, so you have to put it in the pre-routing chain for a port forward. So from here, though, we want to make sure that it is coming from the LAN net and that it is going out of the WAN interface. And if it is, we want to jump to the target masquerade. All right? Now, one important thing for any of the rule targets, there's things like log and other stuff, but why I use drop as my policy is because it doesn't send any replies. So it doesn't send ICMP, port unreachable messages, or any timeouts or any indication that the connection failed or was being blocked. You can also set this to reject. I don't recommend it. It's good because it lets the application, like Firefox for instance, time out immediately, but it's bad because it sends back information we can use like with Nmap to gather information about our firewall if someone is in reconnaissance of a cyber attack. So you want to set that to drop, in my opinion. So from there, we should be able to save this file, all right, just like before. We want to say change mod, making it so the owner has an executable permission. Now, let's test the file we made. You want to do iptables-nv capital L, make sure everything loaded, and it did here. And then if we check the NAT table, nv capital L, we're all good on that. Now, we have to create we have to make it so this can boot up. So you want to go into, we're on run level 5, we're going to go in etc rc5.d, and then we're going to make a symlink. So ln-s, we're going to link the file we just made to S01 firewalls. We need to lastly do update rc.d, and then the name of the file we created, fw, the program, and say defaults. This hooks it all into the boot system. So when we're booting up, it goes through that boot directory for all those programs and starts them. So we have our interfaces, our routing, our firewall done. Now we have to install the DHCP server, okay? This is needed because this hands out addressing information and DNS server information. This only works for IPv4 in this configuration. After it finishes, don't panic. It tries to start, but we haven't told it what to do yet. So we want to go to etc default ISC DHCP server, and you want to uncomment the variable DHCPD v4_conf. You want to uncomment the version for PID file, and under interfaces v4 in the quotes, put your LAN interface, so EMP0S3. And then let's save that. And now the config file for DHCP is in etc DHCP dhcpd.conf. We are going to back that up just like before with our interfaces file. Want to back that up just in case. And let's remove the original. And let's make a new version real quick. We're going to say option domain name. This is your local domain name. It can be whatever you want. It doesn't actually have to resolve on the internet unless you've set that up. Now we're going to do option domain name. Domain name servers. And then let's say 4.2.2.1, comma, space 4.2.2.2. And these are external ones that our clients will use. They can be internal as well. We're going to say subnet 192.168.1.0. You want this to be your LAN subnet, and that's what's called the network ID part of it, the beginning of it, in other words. And then we want a net mask. This is a 24-bit subnet mask. That's what we need, because otherwise the clients won't know what network they're on correctly. Then we're going to open a curly brace, enter down, and tab in. So in this subnet, what we want to do is hand out specific addresses. So we want to hand out 100 through 1200, and with a semicolon. And then we want to say what our default gateway is, option routers. So remember, with ARP, this is what it tells the clients to send. It says send to me if the destination isn't on your network. And this is what that option is for. This range, the entire subnet range is 1 through 254 in our case. So just because 100 and 200 are here, you can still use 1 through 99 at the end here, and up to 254. The difference is that range will be dynamically assigned, so a lease will be created for it. All right, let's do DHCPD-T to test everything, and this is why we test. So there's an error, and under domain name servers, make sure that that is a comma and not a period. And there we go. That means it's working for us. All right, so at this point, we're going to reboot, and then we're going to verify that everything is working. So I'll see you there. So just reboot, and I'll see you in a second. All right, so this is now part 3 of 3 where we're going to verify our configurations. So the first thing I did here, we rebooted, and I'm going to do apt-get update because I'm also just going to give you guys quick tips on programs to monitor your firewall with. And what we're going to quick install for you is iftop. We're going to install iptstat, and we're going to install iptrafng. At least to start. There are others, but these are pretty good ones to use. And after that, we'll go ahead and verify connectivity. All right. So now, the first thing I want to do from the firewall is a ping. If you can ping, you know your WAN interface is correctly configured. We're also going to look at the routing table. And our routing table here is correct as well. So what we want to do is actually should have done this before, let's install TCP dump. And while that is installing, I'm going to bring up a client here. And what you're going to want to do with TCP dump is set up a listening instance of it on ENP0S3. And that's your LAN interface, okay? So we're going to fire up our client, and if I ping, because if I do route print, the 000 address is our LAN address as its default gateway. If I ping 192.168.1.1, you can see the echo requests and replies. But if I ping Google instead, you can see that it had to go through and send an ICMP echo request. It already got the IP from DNS, but... All right, now we're going to go to the WAN interface, EMP0S8. And if we ping, you'll see the traffic is different on this side. Because of that NAT rule, it changed it to 25. So if we look at our NAT table, you see it's caught 11 packets, and it's changed the source address of them. But that's how that works and why it works. So again, just to reiterate, check your LAN and WAN when it comes back up. Check your routing table with IPRoute or NetStatRN if you have that. And you also want to do systemctl, status, DHCPD. Whoops. It's actually spelled out, ISC DHCP server with hyphens in there. And you want to make sure that's running as well. One last thing I'm going to leave you with is what happens if you want to have SSH. So SSH is secure shell on here. So if I install SSH, and now if you don't know what SSH is or why you would need it, don't follow these instructions because this is an avenue of attack for breaking into systems, as well as its purpose, which is securely administering those systems over a network. But anything can be used in a malicious way as well. If we install that, I'm just going to show you real quick. If I start this SSHD, and then I run, if I look at SSLN, whoops, too many, SSLNT, it's listening on port 22. And what you have to do is actually open that up in your input chain, but we have to be very careful about doing it. So we're going to say it here, but let's open it up. Only do this how I'm showing you. Please, I mean, do not open this up to your WAN unless you know why you need to do it. So here we're going to use that $ again, LAN, TCP, not just TCP, but let's also have it only be our LAN net source, have it be TCP, have it going to port 22, and accept the traffic. So basically what this means is it's only going to allow, if we look at that table input, it's only going to allow that traffic to the SSH server if it's from our LAN net and coming in on our LAN interface. This is a pretty secure configuration. So why it's important to have this is now I can SSH to that machine like this. And I say accept the fingerprint, and then I can log in. The problem is, it's over the network. I don't have to be in front of the machine to do this. This is why I limited it to the LAN interface and only our trusted computers. See, now if I say W, I'm logged in from an IP address that's remote. And that can be any IP address. Real quick, just to round it all out, if we tail the file verilog auth-log, that's how you can keep track of who is logging in. And if what you want to look for is accepted password, if that comes in for a user from an IP you're not expecting, or from the WAN, you need to look into that. That's why I said do not open this on your WAN. It's impossible for someone on the WAN right now with this configuration to get in. But they could break into your LAN and use it as a pivot point. There's many other ways as well, but regardless, with that, the other programs like IFTOP, you can just use these to monitor your LAN and WAN. You would see connection information. IPTstat is the same way. You can monitor information with your connections and as well. So that's how those work. And IPTraf is another good one. You can monitor interfaces and things like that. So if I ping right now, I can monitor that connection. You see packets down there? So like if I do a continuous ping, I can go through these interfaces here and see all of the packets and their bandwidth and everything, as well as like statistical breakdowns by packet size on my LAN and WAN. See, these are 75 byte packets. And I can monitor my LAN stations. So I can monitor the MAC address and the frames that are coming in from my LAN. So that is how you set up a network firewall with Linux. And these concepts, a lot of them, they all apply to any distro you're using. So I hope this was helpful for you. So with all that, as always, it's Tyler with T-Tech. Alright, so this is now part 3 of 3 where we're going to verify our configurations. So the first thing I did here, we rebooted, and I'm going to do apt-get update because I'm also just going to give you guys quick tips on programs to monitor your firewall with. And what we're going to quick install for you is IFTOP. We're going to install IPTstat, and we're going to install IPTrafNG. At least to start. There are others, but these are pretty good ones to use. And after that, we'll go ahead and verify connectivity. All right. So now, the first thing I want to do from the firewall is a ping. If you can ping, you know your WAN interface is correctly configured. We're also going to look at the routing table. And our routing table here is correct as well. So what we want to do is actually should have done this before, let's install TCP dump. And while that is installing, I'm going to bring up a client here. And what you're going to want to do with TCP dump is set up a listening instance of it on ENP0S3, and that's your LAN interface, okay? So we're going to fire up our client, and if I ping, because if I do route print, the 000 address is our LAN address as its default gateway. If I ping 192.168.1.1, you can see the echo requests and replies. But if I ping Google instead, you can see that it had to go through and send an ICMP echo request. It already got the IP from DNS, but all right. Now we're going to go to the WAN interface, EMP0S8. And if we ping, you'll see the traffic is different on this side. Because of that NAT rule, it changed it to 25. So if we look at our NAT table, you see it's caught 11 packets and it's changed the source address of them. But that's how that works and why it works. So again, just to reiterate, check your LAN and WAN when it comes back up. Check your routing table with IP route or netstat.rn if you have that. And you also want to do systemctl, status, DHCPD. Whoops. It's actually spelled out, ISC DHCP server with hyphens in there. And you want to make sure that's running as well. One last thing I'm going to leave you with is what happens if you want to have SSH. So SSH is secure shell on here. So if I install SSH, and now if you don't know what SSH is or why you would need it, don't follow these instructions because this is an avenue of attack for breaking into systems as well as its purpose, which is securely administering those systems over a network. But anything can be used in a malicious way as well. If we install that, I'm just going to show you real quick. If I start this SSHD, and then I run, if I look at SSLN, whoops, too many, SSLNT, it's listening on port 22. And what you have to do is actually open that up in your input chain, but we have to be very careful about doing it. So we're going to say it here, but let's open it up. Only do this how I'm showing you. Please, do not open this up to your WAN unless you know why you need to do it. So here we're going to use that $ again, LAN, TCP, not just TCP, but let's also have it only be our LAN net source, have it be TCP, have it going to port 22, and accept the traffic. So basically what this means is it's only going to allow, if we look at that table input, it's only going to allow that traffic to the SSH server if it's from our LAN net and coming in on our LAN interface. This is a pretty secure configuration. So why it's important to have this is now I can SSH to that machine like this. Then I say accept the fingerprint, and then I can log in. The problem is, it's over the network. I don't have to be in front of the machine to do this. This is why I limited it to the LAN interface and only our trusted computers. See, now if I say W, I'm logged in from an IP address that's remote. And that can be any IP address. Real quick, just to round it all out, if we tail the file verilog auth-log, that's how you can keep track of who is logging in. And if what you want to look for is accepted password, if that comes in for a user from an IP you're not expecting, or from the WAN, you need to look into that. That's why I said do not open this on your WAN. It's impossible for someone on the WAN right now with this configuration to get in. But they could break into your LAN and use it as a pivot point. There's many other ways as well, but regardless, with that, the other programs like IfTop, you can just use these to monitor your LAN and WAN, you would see connection information. IPT stat is the same way. You can monitor information with your connections and as well. So that's how those work. And IPtraf is another good one. You can monitor interfaces and things like that. So if I ping right now, I can monitor that connection. You see packets down there? So like if I do a continuous ping, I can go through these interfaces here and see all of the packets and their bandwidth and everything, as well as like statistical breakdowns by packet size on my LAN and WAN. See, these are 75 byte packets. And I can monitor my LAN stations. So I can monitor the MAC address and the frames that are coming in from my LAN. So that is how you set up a network firewall with Linux. And these concepts, a lot of them, they all apply to any distro you're using. So I hope this was helpful for you. So with all that, as always, it's Tyler with T-Tech. Alright, hello and welcome to this episode of T-Tech. This is part 2 of 3 in our Linux network firewall series. So in this part, we've already found our hardware. We've already done a stock install of Debian Linux in this case. Alright? So the first thing you want to do is make sure you find your hardware that is, of course, compatible and has enough RAM and CPU and everything. In addition, don't forget, you gotta find 2 NICs. You can, if you have a desktop, you can use the built-in NIC, and then you can find a PCI Express or PCI if it's like a little bit older, and you can plug that in there and then have 2 interfaces. So as long as we've done that, though, we can get started. And what we're going to do is log in as a user, do whatever you created during the installation, and we want to become root with the su command. And now, the first thing to do is back up our interface file, because in order to make a LAN and WAN interface, we have to assign those addresses. So we want to back up this file here to something ending in .back, and don't be afraid to do this if once you get it running you're messing around with it. Always make a backup of any config file on your system before you change something and you're not sure. Coming from experience, I've broken a lot of things that way, but that's besides the point. Alright, now we have a backup. Let's go into... Oh, I'm sorry, I forgot to show you. Type IP space adder here, or ifconfig, but IP adder is a more modern way. And what we want to do is, in my case, ENPS0 number 2 there is my LAN interface. That's where that IP address will be. And number 3 there is ENP0S8. That's my WAN, okay? So that's the interface that's going into your modem. So we're going to go ahead, and now we can go into this file. And if your provider just uses DHCP, that's Dynamic Host Configuration Protocol, you can leave the WAN interface how it is. On the other hand, we used static in our diagram, so we are going to put, after init there, we are going to put static, and then I'm going to put address 192.168.0.25. This next thing after the slash is called the CIDR, the classless interdomain routing. This just means that we have octets in this IPv4 address. What the 24 represents is the bits. So an entire address is 32 bits. And what we're saying with this is 24 bits of this one address can't change. They're part of the network. So that's the subnet. So this means, because each of these sections are 8 bits, that the 192.168.0 is the 20 up to 24. Those are all 24 when you put them together. 8, 16, 24. All right? So when you put all those together, though, those are the ones you cannot change, and that's how the router knows. After that, though, we need a gateway, and it's 192.168.0.2 in my case. Always remember this when you're setting this stuff up. You want to have it must be the case that the gateway is on the same network. So if any of these sections were different, you're not going to be able to route to the gateway because you actually have to use things like ARP or NDP if you're using IPv6. So you have to have that on the same subnet. Your gateway is on the same subnet as your WAN address. Always remember that. So after that, though, let's set up the LAN address. And we need to say allow-hot plug, like this, and then ENP0S3. And now we have to say iface ENP0S3 init static. We're going to say address 192.168.1.1. Use that /24. But on a LAN interface, you don't put a gateway. All right? Don't put a gateway on your LAN. Now we're gonna hit colon and type WQ, and we're gonna write and save the file. Now you want to do if down ENP0S3. Whoops. Make sure it's /sben/if down ENP0S3, and then you want to do sben if up ENP0S3. So now if we do IPadder now, look at number 2, which was our LAN, and now it's got the address and mask we put in there. And if you look at the WAN, which is number 3 still, it has an address, the dynamic address. The reason that is we have to bring that interface down. So just do if down ENP0S8, and then we want to say that same if up command. And now if we check, now we have that address. Now on your firewall 2, we have to configure DNS servers. So to do that, you want to go into etc resolve conf. And what we're going to do here is put name server space. I'm going to put external ones on the internet. I'm going to put 4.2.2.2 and 4.2.2.1. Okay, and that will work being external. Again, let's save that file. So now we have our LAN and WAN interfaces configured. At this point, it's a good idea to do a ping. So let's do a ping and make sure you get a reply from the firewall itself. Now, we're going to go into setting up our IP routing. All we have to do is edit this file, etc.sysctl.conf. And in Linux, they've made it very easy. All you have to do is uncomment this one line, and that turns on the forwarding of IPv4 packets. And that just means it will forward a packet that's not destined for itself. From here, we need to configure the firewall. So let's go into etc init d. All right, so we have to make a program that has the rules in it and has them load for us. And we're going to make a shell program for this. So in our boot directory, we're going to make a file called fw, and we're going to start by having an interpreter line, bin bash. And now, if you're familiar with programming, and even if you're not, that's fine, we're going to make some variables, and they're just like an envelope. It holds information. We're going to say LAN, and this will be our LAN interface name, like that. Make sure it's in quotes. And now we're going to say WAN. We're also going to say LAN net. This will be our network for our LAN. So that'll be 10/24. And then our WAN will be 192.168.0.0/24. So after this, let's put in some comments for ourselves. So flush everything on, well, the firewall is called net filter, so we'll put that in the comment. But essentially, we want to reset ourselves to a default state. We're using the command iptables -F, iptables -tnat-f, and iptables -x, capital X. And that means the chains and tables in net filter. So we need default policies next. And what we're going to specify is iptables -P input drop, iptables P forward drop, and iptables P output accept. Now, the chains here, NetFilter has tables and they have chains. A table contains one or more chains. Okay? So the input chain is a part of the filter table. And this input chain processes packets when they're destined for this machine. So if you start Firefox, just for instance, you don't run Firefox on your firewall, but if you start that, this data that goes up and down through the network gets processed through the input chain. So what it means is when a program is listening on a socket to receive data from the network, the data goes through the input chain. So it's for programs on this machine is what that deals with. And what the drop is the policy if it doesn't match a rule in the chain. So it's like a catch-all, okay? Forward is not for applications on this firewall itself. It's actually for routing the packets. These are the rules that decide if a packet can be routed a certain way or can't be routed. So these, it's not destined for this machine. It's destined for networks this machine is attached to. So our LAN and WAN, that's the example. That's what it's for. So we're going to write rules that control the LAN access to the WAN and vice versa. So everything we don't put in that chain as a rule is just going to be dropped, so it's very secure for us. Now, output, though, is for your applications when they start a connection from your machine. So input is like if data is coming from Firefox into Firefox, but you didn't start a connection. Output is like when you actually go to Google on purpose and it sends the data down first. That is okay, we're assuming. So we're going to say accept, and we actually don't have to write any rules for that chain. All right, so from here, let's go ahead and do firewall destined traffic policy. And we want to add to the end, so append any traffic coming in on the loopback interface. And we want to jump to the target of accept. And also we want to append that any traffic that has a state, so we're using a module with M there, of related, comma, and then established. We want to accept that traffic. We want to also input. We want to accept ICMP traffic to allow pings and stuff to happen. We want that to come in on our LAN interface. And accept. And then iptables A. We want to accept some traffic for a DHCP server that we're going to set up a little bit later. Alright, that's our input first. And then next, we're going to focus on our forward chain. Alright, so now we need to go ahead and make our forward policy. Now, our forward policy is going to be for our LAN. So this is our LAN to WAN traffic policy, alright? So we're going to say iptables, and now we're going to append to the forward chain And then we want to say that the traffic has to be coming in with lowercase I, and we're going to utilize our variable with a $sign to tell our program it's a variable. Do LAN, and then -s for the layer 3 source address in the IP header. Now in this case, we're going to use a $sign LAN net. Now that also has to be routed out of the WAN interface like this, and then once we do that, we want to accept that traffic. Now we also want to go ahead and have it so it matches any existing traffic. So with the module state and then the -- state related, comma, established, like that, and then -j, accept. Now, the last thing we need here is that we need our NAT policy. So this is our LAN to WAN NAT policy. This is not port forwarding. This is the source NAT we spoke about. So this is IP tables. We need to work on a different table this time called the NAT table. The other ones were on the filter table. From there, though, we want to append the rule to the post routing chain. This is after the routing decision has been made by the networking stack. So if you want to do port forwards for destination NAT, you have to make the decision before you route the packet, so you have to put it in the pre-routing chain for a port forward. So from here, though, we want to make sure that it is coming from the LAN net and that it is going out of the WAN interface. And if it is, we want to jump to the target masquerade. All right? Now, one important thing for any of the rule targets, there's things like log and other stuff, but why I use drop as my policy is because it doesn't send any replies. So it doesn't send ICMP port unreachable messages or any timeouts or any indication that the connection failed or was being blocked. You can also set this to reject. I don't recommend it. It's good because it lets the application, like Firefox for instance, time out immediately, but it's bad because it sends back information we can use like with Nmap to gather information about our firewall if someone is in reconnaissance of a cyber attack. So you want to set that to drop, in my opinion. So from there, we should be able to save this file, all right, just like before. We want to say change mod, making it so the owner has an executable permission. Now, let's test the file we made. You want to do IP tables -nv capital L, make sure everything loaded, and it did here. And then if we check the NAT table, NV capital L, we're all good on that. Now we have to create we have to make it so this can boot up. So you want to go into, we're on run level 5, we're going to go in etc rc5.d, and then we're going to make a symlink. So ln-s, we're going to link the file we just made to S01 firewalls. We need to lastly do update rc.d and then the name of the file we created, fw, the program, and say defaults. This hooks it all into the boot system. So when we're booting up, it goes through that boot directory for all those programs and starts them. So we have our interfaces, our routing, our firewall done. Now we have to install the DHCP server, okay? This is needed because this hands out addressing information and DNS server information. This only works for IPv4 in this configuration. After it finishes, don't panic. It tries to start, but we haven't told it what to do yet. So we want to go to etc default ISC DHCP server, and you want to uncomment the variable DHCPD v4_conf. You want to uncomment the version 4 PID file, and under interfaces v4 in the quotes, put your LAN interface, so EMP0S3. And then let's save that. And now the config file for DHCP is in etc dhcp dhcpd.conf. We are going to back that up just like before with our interfaces file. Want to back that up just in case. And let's remove the original. And let's make a new version real quick. We're going to say option domain name. This is your local domain name. It can be whatever you want. It doesn't actually have to resolve on the internet unless you've set that up. Now we're going to do option domain name. Whoops. Domain name servers. And then let's say 4.2.2.1, comma, space 4.2.2.2. And these are external ones that our clients will use. They can be internal as well. We're going to say subnet 192.168.1.0. You want this to be your LAN subnet, and that's what's called the network ID part of it, the beginning of it, in other words. And then we want a net mask. This is a 24-bit subnet mask. That's what we need, because otherwise the clients won't know what network they're on correctly. Then we're going to open a curly brace, enter down, and tab in. So in this subnet, what we want to do is hand out specific addresses. So we want to hand out 100 through 1200, and with a semicolon. And then we want to say what our default gateway is, option routers. So remember, with ARP, this is what it tells the clients to send. It says send to me if the destination isn't on your network. And this is what that option is for. This range, the entire subnet range is 1 through 254 in our case. So just because 100 and 200 are here, you can still use 1 through 99 at the end here, and up to 254. The difference is that range will be dynamically assigned, so a lease will be created for it. All right, let's do DHCPD-T to test everything, and this is why we test. So there's an error, and under domain name servers, make sure that that is a comma and not a period. And there we go. That means it's working for us. All right, so at this point, we're going to reboot, and then we're going to verify that everything is working. So I'll see you there. So just reboot, and I'll see you in a second. Hello and welcome to this episode of T-Tech. This is part 1 of 3 in our 3-part series to set up a network firewall with Linux. So the first part here is I want to introduce the concepts to you. And then in the next part, we're going to actually configure all of this on our new Linux machine. And in the third part, I'm going to walk you through checking to make sure everything is working that we configured. And during that time, I'll also explain why it's working the way it is. So, real quick, anytime we're creating any type of firewall, a custom firewall, what we're trying to do is take an internet connection from our ISP, so our internet service provider. It doesn't matter if it's cable, if it's satellite, if it's fiber, or if it's DSL. Any of the major ones will work just fine. The reason being is a lot of the modems now have an Ethernet port as the customer side of it to connect into your equipment. So we're going to have 2 Ethernet NICs that are going to plug in to our machine. So once we do that, though, and set this up, we're going to essentially have a WAN side, and we're going to have a LAN side of our firewall. And the wide area network side is everything we want to keep out, essentially. Yes, we have to use it to get out to things and resources on the internet, but we don't want it talking to us unless we started a conversation, you see? So, it's kind of similar to someone knocks on your door and you check first and then you open the door. You wouldn't want them to just be able to open the door without you telling them they can, see? So the LAN side local area network, on the other hand, is everything we have that is trusted. Now you can control what goes from the LAN to the WAN even further, but normally we allow everything from the LAN to the WAN, but nothing from the WAN to the LAN, unless it has something called state for that. But that is our setup. This is one Ethernet NIC here. This is what this line represents. This is our second Ethernet NIC. This goes into an Ethernet switch. It does not have to be what's called a managed switch. It can just be a normal switch. And then you have these PCs connected. And off of this switch, you would also have potentially a wireless access point. But with that, moving forward, if any of our PCs on the LAN want to talk, PC2, for instance, he's going to use something called ARP. That's Address Resolution Protocol. Because Ethernet has to have a MAC address in order to communicate. So essentially, he would just ask for our firewall's machines. The firewall has a MAC address on its NIC. PC2 is going to ask for it, and then it's going to receive a reply from our firewall. But once it gets that, it can send any type of traffic it wants. It has its MAC address now. So, as we see, we send the packet, step 1. Step 2, the switch gets the packet. Remember, switches use the destination MAC address to decide where to switch a frame, so what port it goes out of, and it learns the source MAC address of PC2, so we don't have to repeat the ARP process after the first time. And then, though, the switch is going to forward it up to the Linux machine. Now, the next parts all take place inside our Linux firewall. So, we have something called NAT, and NAT is Network Address Translation. Now, this is only used in IPv4, not in IPv6. There's some use of it, but that is beyond the scope of what we're talking about. Here, though, we are now zooming in on the IP addresses actually assigned to our firewall. The LAN side will have 192.168.1.1, whereas the WAN side will have 192.168.0.25. And these are private because I have a network in place already that this is connected to. So this concept that we're talking about will work the same even once you plug into your ISP equipment. It works the same in a lab as it does in production. This is technically a private address. Yes, it is. But the concept of switching it out will work the same. All right? So, when that packet from PC2 comes in, its source address is 192.168.1.3. It's layer 3 address. Before it is routed out of our Linux firewall, it should be the WAN interface IP address that our Linux firewall has. Otherwise, the ISP will not route it. And as well, you could only have the first PC to send traffic would be the only one that can use your internet connection. All right? So we want to just take that source address at layer 3 in the IP header, and we want to change that to 192.168.0.25. And then after we change that address, that makes an entry, a translation entry. But once this is done, then we can route the packet. So if your computer talks to google.com, once it has the IP of google.com through DNS, it gets its address, it puts that in an IP header as a destination address. And what Linux does is its network stack looks at that destination address, and it has its routing table like as a book, and it compares that destination address value with entries in its routing table. So that allows it to select what's called the outgoing interface or egress interface to route that packet over. In this case, it routes it out of the WAN in this case. So it would route it out of the WAN. All right? And that doesn't create state. That just will route. That's why we have to have a firewall on top of the routing. Because this machine is going to do routing and it's going to do firewalling as well. It's going to do both things, but they are separate functions. even though they're combined in one machine. So, what happens when traffic comes back through? Well, the thing is actually going to happen in reverse. So the first thing that has to happen is it has to come back into the machine. And then that state we discussed, it's going to check that as another of its tables called contract. And that's the state tracking table in Linux. Once it checks that, the traffic from Google, let's say, is going to come back destined at layer 3. The source will be Google's address. The destination will be 192.168.0.25. And what will happen is Linux, if it's in the contract table, if it's part of an existing connection, will change the destination address this time. So it'll be the opposite. And it's going to change that to 192.168.1.3, which is PC2 because he started this connection. It's going to compare that destination address after the NAT reversal takes place. On the way out, we do SNAT. That means source NAT. On the way in, we do DNAT, which means destination NAT. So after the destination NAT takes place, he's going to look at that new destination and send it down. It's going to compare the routing table. The LAN address is what that address falls into. So then he's going to send it, instead of out of the WAN, he'll send it out of the LAN. So in that way, we only let the LAN talk to the WAN, but not the WAN coming in, unless we do something called a port forward, but you don't have to worry about those. And but that's what we're trying to do. That's the big picture, okay? So in the next part, I'm going to set this up on the Linux machine. All right, so I will see you in part 2. Again, this is part 1 of 3 in our Linux Network Firewall series. I hope you enjoyed it this far, and thank you for viewing. And as always, it's Tyler with T-Tech.
In this section, we'll dive into IPsec. Let's see first why do we need IPsec. IP tables itself does not support matching multiple separate addresses or networks in one rule. If you want to block 10 different networks, you have to create 10 different IP tables rules. This means that every checked address or network would need their own rule in the rule set. Such complicated and long rule sets bring administration and performance concerns. Just imagine what would happen if you want to block 100,000 networks or IP addresses, or why not an entire country. You have to write 100,000 IP tables rules. Even though you can simplify the configuration by using a bash script that reads the IPs from a file, the performance degradation would be of a real concern. Each packet would traverse all 100,000 rules from top to bottom and would be checked by each rule. I can honestly tell you that I've seen a CPU overhead between 10 and 30% only for IP tables. This is where IPset comes into play. IPset is an extension to IP tables that allow us to create firewall rules that match entire sets of addresses at once. Unlike normal IP tables chains, which are stored and traversed linearly, IPsets are stored in indexed data structures, making lookups very efficient, even when dealing with large sets. It lets you create huge lists of IP addresses and ports with tens of thousands of entries, which are stored in a tiny piece of RAM with extreme efficiency. In your IP tables rules, you can then simply refer to the lists by name, and the entire list is checked with remarkable speed and in a single IP tables rule. These IPsets are a framework inside the Linux kernel and can be administered by the IPset utility. On many Linux distributions, you have to install IPset, which is a very simple operation. If you are using a Debian or Ubuntu-based distribution, you just run apt install IPset. Let's go to a terminal and install IPset. First, I'll try to execute the IPset command to check if it's already installed or not. Don't forget to run all these commands as root. Use sudo before the command name or become root by running sudo su or su. It depends on your distribution and your configuration. I've just run the IPset command and we notice that IPset is not installed, and it also tells us how to install it. So I'm typing apt update and then apt install IPset. If you are using an older version of Ubuntu, use apt-get instead of apt. And if you are running CentOS, execute yum install IPset. Now IPset is installed. Let's check the installation by running IPset help pipeless. Okay, in this lecture, we've seen what is IPset, when do we use IPset, what advantages it brings, and how do we install it. In a nutshell, IPset brings significant performance gain and powerful extra features, like the ability to apply single firewall rules to entire groups of hosts and networks at once. Anytime you want to apply firewall rules to groups of hosts or addresses at once, you should be using IPset. In the next lecture, we'll dive deeper into IPset and see many more examples. In this lecture, we'll see the first examples with IPset. IPset is a mesh extension for IP tables. To use it, you create and populate uniquely named sets using the IPset command line tool and then reference those sets in the mesh specification of one or more IP tables rules. Let's consider the following normal IP tables rules that block incoming packets from these three source IP addresses. Alternatively, the following IP set and IP tables commands achieve the same result. The first step is to create a named set. Remember that a set is simply a list of addresses stored efficiently for extremely fast lookup. IP set -n, let's say my set, #IP. I am creating a new set called my set. -n means create a set. And it's an uppercase letter N. #IP is the method of storing and searching the collection. I'll go into more details in the next lecture. The second step is to add the IP or the network addresses to the new set. So IP set -a from add, it's an uppercase A, the name of the set, my set, and the IP address. The first IP address, the second IP address, and the third, the last IP address. And lastly, we reference the set in a match specification of IP tables. Before writing the IP tables rule, I just want to test that I can communicate with 8.8.8.8. This is the public DNS server of Google. Perfect, it's working. And now the IP tables rule. IP tables -a input, the chain, -m set, -match -set, the name of the set, my set, src from source, -j drop. The IP tables command references the set with the specified name, and it means match packets whose source IP address matches or is contained within the set named myset. The flag src means match on source. There is also the flag dst, which matches on destination. Let's test the connection to 8.8.8.8 again. And ping doesn't work anymore. Let's list the firewall. And we notice there are 6 packets dropped by the rule. Also note that only one IP tables command is required regardless of how many IP addresses are contained within the set. This example uses only 2 IP addresses, but we would just as easily define 10,000 addresses and it would still require only a single IP tables rule. Without IP set, so using the traditional IP tables approach, the setup would require 10,000 IP tables rules. In the next lecture, we'll dive deeper into IP set and we'll see how to use it in depth. Let's move on and dive deeper into IP set. Let's see how to create sets. When working with IP tables and IP set, the first step is to create the named set. It will contain the IP or network addresses. In the last lecture, we've seen that if we want to create a new set, we use -n. Let's try a new example. IP set -n, the name of the set, let's say China, it's a random name, you can choose whatever name you'd like, #net. It's also possible to use the create option instead of -n. IP set, create, Romania, the name of my country, #net. Now if the set already exists, you'll get an error. Sometimes you want to run a script that creates some sets and does other stuff without worrying about the case when the set does already exist. And I'm running the command again. Set cannot be created. Set with the same name already exists. To avoid the error of an existing set with the same name, use the exist option. If exist option is specified, IPset ignores the error otherwise raised when the same set already exists. And if the set already contains some IP or net addresses, they are not flashed. So I am adding -exist. And there is no error. Each set is of a specific type. The type defines what kind of values can be stored in it: IP addresses, networks, ports, and so on. The most common type sets are #net and #IP. #net is the same with net hash. Net hash or #net is used for a collection of networks. And #IP or IP hash, it's the same, is used for a collection of individual IPs. The difference is how efficient the storage of the collection will be and how fast the kernel will search in the collection for matching packets. Besides these two types, IP hash and net hash, additional set types are available to check the port, the IP address and port together, or the MAC and IP address together. Let's move on and see other examples with IPset. If we want to add a given entry to a set, we use the add option. IPset, add, the name of the set, China, and the network, 1.0.0.0/8. Instead of add, you can also use -a, an uppercase A letter. It's the same. If you try to add an entry that already exists in the set, you'll get an error. Element cannot be added to set. It's already added. If the exist option is specified, IPset ignores the entry if it's already added to the set. -exist. And there is no error. Let's list the sets and their entries. We've created some sets with some entries. IPset list or IPset -l brings out all sets with all their contents. We see the name of the set, some parameters, and the entries. Now if you have many sets and want to see only one set, you add the set name, IPset -l China. And it printed out information only about China set. To delete an entry from a set or a collection name, use del or -d option. IPset del China 1.0.0.0/8. Okay, sorry, there is an error. It's an extra dot there. This command has deleted the entry from the set. I can also use -d instead of del. So -d. It's the same. To flush all entries from a set, use flush or -f option. IPset -f China. It flushes all entries from China set. If I write only IPset -F, without specifying the set name, it flushes all entries from all sets. -F or flush. X the same. To delete or destroy a set, use destroy or -X option. ipset destroy China. It has removed the set called China. The set with the given name does not exist. I can also write ipset -X Romania 1. And if I write ipset destroy without specifying the set name or ipset -X, it deletes all the sets. Take a look at this error. Set cannot be destroyed. It is used by a kernel component. Note that a set cannot be destroyed while there is a single reference pointing to it. So if there is an iptables rule that uses the set, you should first delete that iptables rule and only then destroy or delete the set. iptables -VNL. And we see there is a rule that references my set. So iptables -F, I'm flushing all the chains and tables. Now there is no rule in the iptables firewall. And I can simply delete the set or all the sets. So ipset -X will not raise an error. And there is no set. Maybe you wonder how many entries can a single set contain. There is a parameter called maxLM which defines the maximum number of elements which can be stored in a set. By default is 65,535. This parameter is valid for the create command of all hash type sets. Let's create a new set that can store a maximum number of 5,096 elements. ipset create my set #IP, the set type, and now maxLM 4096. Sorry, I've forgotten the parameter. So maxLM and the number. Perfect. ipset list. And we see information about my set, and maxLM is 5096. In this lecture, I'll show you how to automatically block bad hosts. ipset provides a target extension to iptables that provides a mechanism for dynamically adding and removing set entries based on any iptables rule. Instead of adding entries manually with the ipset command, you can have iptables add them for you on the fly. For example, if a remote host tries to connect to port 80, but there is no HTTP or web server running on that machine, you could consider it bad and block it entirely. It's like a proactive measure to avoid something nasty it could do in the future. Let's see how it works. First, I'm destroying all the sets. And I'm creating a new set called autoblocked of type iphash. ipset -n auto _blocked, the name of the set, its type iphash, and also -exist. I don't want an error if the set already exists. The second step is to add an iptables rule that adds IP addresses to the set based on some criteria. So IP tables minus I input minus PTCP minus D port 80. So if the packet comes to port 80, minus J set minus add minus set, the name of the set auto blocked, and SRC. I am adding the source of the packet to the set. If a single packet arrives on port 80, its source IP address is instantly added to auto-blocked set. It's like you'd manually run ipset minus A, auto-blocked, and the IP address, the source IP address, like this. It's the same. Only that IP tables does this automatically for us and does it on the fly. And the last step is to reference the set in an IP tables rule that drops the packets. So IP tables minus I input minus M set minus match set auto blocked SRC minus J drop. Perfect. Now I'll ping continuously from my Windows recording machine. Let's see the IP address of the Linux machine, and I'll ping it continuously. Okay, to ping it continuously, you use -T option. And it's working. Now from a second terminal, I'll send a packet to port 80. And I'm gonna use the telnet command. Telnet, the IP address of the Linux machine, and the port 80. At this moment, ping is still working. Okay? And enter. We see how ping stopped. It stopped because it automatically added the IP address, the source IP address, to that set and dropped all the packets. Perfect. Let's check it. First, let's check the set. I have created a new set without adding an IP address. So IP set -L and the name of the set. And we see the IP address of the Windows machine in the set. Let's list the firewall. IP tables -VNL. And this is the rule. It has dropped 19 packets. This is a very nice and useful feature of IPset and IP tables. You can use it in your network. In this lecture, I'll show you how to clear the running firewall. If you want to completely flush IPset and IP tables rules and reset to an open firewall state, you should set the accept policy, flush all netfilter tables, delete all IP tables user-defined chains, flush all IPset entries, and destroy all sets. This is useful to use at the beginning of any firewall script in order to flush everything and build it from ground up. And I'm creating a script called stopfirewall.sh. Okay, the first step is to set the policy to accept. IP tables -p input accept, and the same for output and forward chains. Next, I'll flash all tables. IP tables -t filter -f. I'm flashing the filter table. IP tables -t ra -f. I'm flashing net and mangle. Next, I'll delete all user-defined chains if there is any. IP tables -x. Okay, we are done with IP tables. Now IP set -f. I'm flashing all the sets. Then IP set -x. I am destroying all the sets. And that's all. I am saving the script, set the execution permission, and run the firewall. Perfect. IP tables and IPsec have been cleared. Keep in mind that secs that are in use and that means referenced by any IP tables rule cannot be destroyed. First flash the IP tables chains and then destroy the secs. Now you should have a good understanding of IPset and IP tables in order to build customized firewalls. In this lecture, I want to show you something really cool and useful. Suppose we run a Linux server with many services like HTTP, FTP, SSH, mail, and many more. Over time, we notice in server's log a lot of authentication attempts, scans, or other kind of malicious traffic. And we want to build a file with all the source IP addresses that tried to attack our server and completely block those addresses. This is the perfect scenario for IPset. For this example, I'll create a new file called badhosts.txt. And I'll write some random IP addresses in the file. And I'm saving the file. Perfect. Now I'm gonna create a bash script that reads the IP addresses from that file, creates a new set, adds the IPs to the set, and then references the set in an IP tables rule that drops the traffic. For example, band.sh. The first line indicates that this script will be executed by bash by default. I'll store the name of the file that contains the IP addresses in a variable. This way, I can rename the file or use another file easily without modifying the entire script. File equals, and between double quotes, the name of the file. bad_hosts.txt. This is a relative path. badhosts.txt and the script called band.sh are in the same directory. Feel free to use an absolute path if you want. I am creating a new set called badhosts of type IP hash. IPset -n badhosts IP hash and -exist. Further, I'll add the bad addresses to the set and do all other required stuff. Finally, I'll run the script. Running the script more than once means that it will add each IP address to the set more than once. To avoid this issue, at the beginning of the script, I flash the set. This means that each time the script is run, the set is flashed and then all the IP addresses are added to the empty set. So here I am flashing the set IPset -f bad hosts. Good. I don't like scripts that are not verbose. I want to see messages to know what the script is doing, so I'm printing a message. Adding IPs from file to bad hosts. Now comes a very important part. Using a for loop, I'll read each IP address from the file and add it to the set. So for IP in a pair of backticks and a command cat $file, the name of the variable. Do and done. These are backticks or back quotes. This is the key just below escape on your keyboard. A backtick is not a quotation sign and it has a very special meaning. Everything you type between backticks is evaluated or executed by the shell, and the output of that execution is used there. It's just as if you'd type that output at that place in the command line. In this case, it's like we copy and paste all the IP addresses in that place. So here. In fact, I am iterating over a list with IP addresses. And inside the for loop, I'm adding the IP addresses to the bad hosts set, and I'm also printing out the IP. IP set -a bad hosts $IP, the temporary variable of the for loop. And echo -n $IP. I'm using -n option because I don't want a \n or a new file after each IP address. All IP addresses will be printed out on a single line. -n prevents echo to add a new line after printing the string. Outside the for loop, I'm printing out another message. Echo -e-n and between double quotes \n, this means a new line, and dropping with IP tables. -e enables interpretation of \escapes like \n, which is a new line. And finally, the last step is to create the IP tables rule that actually drops the packets. IP tables -i input -mset -match set, the name of the set, bad hosts. I'm matching on source IP address, so src -j drop. And echo done. Okay, I have noticed a very small problem. If I try to flush the set before creating it, I'll get an error. You cannot flush a set that doesn't exist. So I am moving the command that flushes the set after the set is created. Perfect. The script is done. I'm saving the script. I'm adding the execution permission and I'm running it. Okay, no such file or directory. The name of the file is bad_host.txt. And inside my script, the name of the file is bad hosts, so there is an extra s at the end. No problem, I'm renaming the file. I'm running the script again. Perfect. It printed out adding IPs from file to bad hosts set, the IP addresses, and the message from IP tables. IP set -l bad hosts. Perfect. the IP addresses are in the set, and IP tables minus VNL, and we see the rule that references the set. That's good. Let's check it. Ping 8.8.8.8, and ping doesn't work. Now I'll remove that IP address from the file. I'm simply erasing that line, saving the file and running the script again. Perfect. That IP address is not in my list anymore, and I'm trying the ping command. And it's working. Now you can simply add or remove IP addresses from the set by simply adding or removing them from the file. This is a very useful firewall script for any sysadmin, and I can say that I have such a script on each Linux I administer. In the next lecture, I'll show you something really cool: how to drop entire countries using IPset and IP tables. See you in a second. Hello and welcome back. In this lecture, I'll show you something really cool. This is one of my favorite use cases of IPset and IP tables. Suppose you have a business localized in a specific country or region, and you don't have any business relations with some parts of the world. Like, say you have an online store that sells shoes and delivers them only in Europe. It would be a great security improvement to drop all traffic originated from America or Asia. You are selling only in Europe. The classical way to do this is to use a service that provides a collection of networks from a specific country. Then, using IP tables, you create a rule for each network address that drops the traffic that's coming from that network. Even though it's working fine, the performance degradation is of concern. You have to add thousands or tens of thousands of IP tables rules, and each packet will traverse from top to bottom and will be checked by each rule. The best practice in this case is to use IPset. It lets you create huge lists of networks with tens of thousands of entries, which are stored in a tiny piece of RAM with extreme efficiency. Then you can simply refer to the set by name, and the entire list is checked with remarkable speed and in a single IP tables rule. In this example, I'll block all the traffic that originates from China. It's just a random country. You can choose any country you'd like. Okay, let's start creating the script. In fact, this is just a variant of the example from the previous lecture where we've banned all IP addresses saved in a file. I'll skip some of the explanations because I've already done it in the last lecture. I am creating a script called blockchina.sh. At the beginning of the script, I'll print out a message. I want to know what the script is doing. And a new line. We start by creating a new set of network addresses. IPset -n China #net x type -exist. This creates a new hash set of network addresses named China. Then I'm flashing the set. We've discussed why this is necessary in the previous lecture. IPset -f China. This bash script will download a file that contains all network addresses from China. Each time we run the script, we check if the file exists, and if it already exists, we remove it and download a brand new file. So I am checking if the file already exists. The name of the file will be cn-aggregated.zone. If the file exists, I remove it. And I'm downloading the file that contains all the networks from China using wget from ipdeny.com. There are many services available out there, but I've used this successfully, and it's also an updated one. I am searching for China, copy the URL and paste it in my script. I'm choosing the aggregated zone file because I want to drop entire networks, not individual IPs. It's more efficient this way. wget and I'll paste the URL. In Linux, each command has a return status, which is 0 if there was no error and not 0 if there was an error. We can get the error status of the last executed command using the question mark predefined variable. I'm checking the return status of the last executed command, and if it was successfully executed, I'm printing out download finished. And another new line. The next step is to add the networks to IPset. Now, using a for loop like in the previous example, the one from the last lecture, I add each network from the file to the China set. This file contains all networks from China. For net in cut and the name of the file between backticks or back quotes, IPset -a China $net, the temporary variable of the for loop. And I'm printing out done. And finally, the last step is to create the iptables rule that actually drops the packets. The rule will reference the set called China. iptables -i input -mset -match set, the name of the set, src, I'm matching on source IP address, -j drop, and echo done. I'm saving the file and set the execution mode. Before running the script, I want to check that I can visit a website hosted in China. And I have this example. It's working great. I'll execute the script. Now it's adding networks to IPset. Perfect. We see how it downloaded a file called cn-aggregated.zone. This is the file that contains the networks from China. After the script has finished executing, I check the site again. And we notice that the site is not loading anymore. All packets that are coming from China are dropped. Let's list the IP tables rules. And we see 200 dropped packets by the rule that references the set called China. Now if you want to see the contents of the set, you simply run ipset -l China. If you already have a firewall script, you just have to execute this script from your main firewall script and it will add this configuration to your existing one. Okay, that's it. Thank you. Hello and welcome back. In this section, we'll dive deeper into IP tables targets. A target is the action that is triggered when a packet meets the matching criteria of a rule. There are two types of targets: terminating targets and non-terminating targets. Terminating targets perform an action which terminates the evaluation within the chain. The packet matched by the rule will not continue traversing the current chain or any other ones in the same table. Depending on the target, the packet might be dropped or accepted. Drop is such a terminating target. For example, if the matching criteria of a rule drop the packet is dropped and no other rule will be evaluated. On the other hand, a non-terminating target performs an action and then the evaluation within the chain continues. The packet continues traversing the rules in the chain. Each chain must eventually pass back a final termination decision, but any number of non-terminating targets can be executed before that. Log is such a non-terminating target. For example, if the matching criteria of a rule log a packet, the packet is logged and then the next rule within the chain will evaluate the packet. Let me show you a first example of a terminating target. In a new shell script, I'll write two IP tables rules. The first rule will accept incoming SSH traffic and the second will drop any TCP traffic. Both accept and drop are terminating targets. I'm writing the rule that accepts SSH traffic. IP tables -a input, -p TCP, -d port 22, -j accept. And the rule that drops all other kind of TCP traffic. IP tables -a input, -p TCP, -j drop. Let's think for a minute what will happen. When an SSH packet arrives, the Linux kernel will accept it and the packet will not be evaluated against the second rule. That's because accept is a terminating target. The second rule will evaluate only TCP packets other than SSH and drop those packets. It doesn't matter if there are other rules that are accepting the packets. Drop is a terminating target, the packet is dropped and will not continue traversing the chain. Let's test it. I'm saving the script, then make it executable and run it. Let's try to connect to Linux 1 using SSH from Linux 2. And we notice that SSH is working. That's because the first rule has accepted the packets and the second one hasn't evaluated them anymore. If I list the firewall, I will see matched packets by the first rule. There are 12 matched packets. and no packet matched by the second rule. Notice that the second rule hasn't matched any packets. Now, let's try to connect to Linux One using a browser. There's a web server running on Linux One. In the address bar, I'll write the IP address of Linux One. And the page is not loading. If I list the firewall again, I'll see that the packets are dropped by the second rule. There are 8 dropped packets. Let's move on and see a second example with a non-terminating target. I want to log and then drop incoming SSH packets. In the same script, I'll log incoming SSH packets. So instead of accept, I will use the log target. This rule will log incoming SSH packets. And the second rule with the same matches will drop SSH traffic. I'm saving the script and running it. From Linux 2, I'll connect using SSH to Linux 1. We notice that SSH is not working. The packets were dropped by the second rule, not by the first one. The first rule has logged information about the packet headers, and then the packet continued traversing the chain and were dropped by the next rule. IP tables -vnl, I am listing the firewall. We notice that both rules have matched packets, and it's the same number. 6 packets have been logged and then dropped. The log target uses the kernel log facility. If we execute the message, like this, we'll see the logged packets. These are the headers of a logged packet. That's another proof that the packets have been logged and only then dropped. In this lecture, we'll see the accept and drop targets again. It's more like a recap because we've already used them in so many examples. Both accept and drop are terminating targets. If a packet is matched against a rule that has the accept or drop target, the packet is accepted or dropped and will not traverse the chain anymore. Let me show you an example. I want to permit incoming ping packets only from a management station or from a single IP address. Before getting started, I want to explain to you what ping means in case you don't know. Ping is a utility command available in any operating system, and it serves two primary purposes: to check if the destination host is available and to measure the round-trip time for messages sent from the originating host to a destination host that are echoed back to the source. According to Wikipedia, the name ping comes from active sonar terminology that sends a pulse of sound and listens for the echo to detect objects underwater. Ping operates by sending Internet Control Message Protocol or ICMP echo request packets to the target host and waiting for ICMP echo reply packets. So allowing ping means in fact allowing incoming ICMP echo request packets and outgoing ICMP echo reply packets. Let's see its help. IP tables -p ICMP, the protocol is ICMP --help. We notice that we specify the type of ICMP packet using --ICMP type, and these are all available ICMP types. Among them, we see echo reply and echo request. In this example, I'll write IP tables rules only for the input chain, so for incoming traffic, but you can write IP tables rules for the output chains as well. So the first rule will allow incoming ICMP packets of type echo request if the source IP address is that of the management host. In this example, I'll consider the management host as being the Windows recording machine, which has the IP address 192.168.0.112. IP tables minus A input minus P ICMP minus ICMP minus type echo minus request minus S 192.168.0.112 minus J accept. And the second rule that will drop all incoming ICMP echo request packets if the source address is another host, not the management station. So IP tables minus A input minus PICMP minus ICMP minus type echo request minus J drop. In fact, it's the same rule without the minus S option, so without the source IP address. Let's test it. If a packet with the source IP address 192.168.0.112 is coming, it will be accepted by the first rule. Being a terminating target, the packet will not be evaluated by the second rule, which of course would drop it if it evaluated the packet. From the management station, I'm gonna ping Linux 1. And ping is working. Perfect. And I'm listing the firewall. And we see matched packets by the first rule. Now, if an echo request packet is coming from another IP address, the first rule will not match and the second one will drop the packet. Let's ping it from Linux 2. And we notice that Linux 2 is not receiving anything back. The second rule is dropping any echo request packets coming from another source IP address. There are 37 dropped packets by the second rule. To become proficient in firewalls and networking in general, you must know in great detail what are the states of UDP and TCP ports and how each type of port behaves when receiving a packet. Let's dive deeper into TCP and UDP port states. Basically, there are three types of ports: open, closed, and filtered. Let's take them one by one. What is an open port? An application is actively accepting TCP connections or UDP datagrams on an open port. Finding these ports is often the primary goal of port scanning. Attackers and pen testers want to exploit the open ports while sysadmins try to close or protect them with firewalls. Open ports are also of interest for non-security scans because they show services available for use on the network. You can see all open ports on your host by running the netstat command, which is available on Linux, Windows, and Mac. In the next lecture, I'll show you a few examples of how to use netstat. Let's see what is a closed port. There is no application listening on a closed port. Even though a port is closed, it's reachable. When sending a packet to a closed port, the port responds back to the source. They can be helpful in showing that a host is up. This is known as host discovery and is part of OS detection. When you send a TCP packet with the SYN flag set to a closed port, the port responds back with a TCP reset packet, and if you send a UDP packet to a closed port, the UDP port responds back with an ICMP packet of type destination unreachable and subtype port unreachable. Sysadmins may want to consider blocking such ports with a firewall, and they will appear in the filtered state. And the last state of a port is filtered, and it means that a firewall is blocking any packet to that port. A port scanner like Nmap cannot determine whether the port is open or closed because packet filtering prevents its probes from reaching the port. As a conclusion, a filtered port can be either open or closed. Filtered ports can be divided further into two categories: open filtered and closed filtered. A filtered port is also known as a stealth port. In this lecture, we've seen what are the states of a TCP or UDP port. In the next lecture, I'll show you how to check for open ports on your host and how to do port scanning on remote hosts. See you in a second. In this lecture and the next one, we'll take a look at two very useful utilities which are used to find information about ports. They are netstat and nmap. Let's get started with netstat. By the way, netstat comes from network statistics and on Linux is part of nettools package. If you don't have the netstat command, you should install the nettool package according to your distribution. For example, on Debian or Ubuntu-based distributions, you run apt update and apt install net-tools. On my machine, it's already installed. And I'll execute netstat -tupan. Sorry, it's netstat. The T option is showing TCP ports and U UDP ports. P comes from protocol, so it displays what protocol there is, TCP or UDP. A means all, and N comes from numeric. It displays ports in numeric format and not the service name. For example, we see 22 and not SSH. The output of netstat is showing both the listening ports on the host and active connections. So if I open a browser and connect to a remote web server, I'll see the connection in the output of netstat as well. There is a lot of output. You can filter it using a pipe and grep. For example, I want to see if SSH is listening or if port 22 is open. And I run netstat -tupan pipe grep 22. And we notice that SSHD is listening on port 22. 0.0.0.0 means that is listening on each IP address of the host. But if I'm searching for port 23, we see that there is no process that's listening on port 23. The netstat command is available in Linux, Windows, and Mac. However, on Windows, there are other options available. Most of the time, you'll simply run netstat -a. and it will display all open ports and active connections on the local host. Let's move ahead and take a look at Nmap, which comes from Network Mapper and is a network discovery and security auditing tool widely used by network administrators for many types of scanning. It's a complex open source application that maybe deserves its own dedicated course, in my opinion. There are a variety of scans that can be performed using Nmap. I want to mention just a few of them. TCP SYN scan is the default and most popular scan option for good reasons. It can be performed quickly, scanning thousands of ports per second on a fast network if there are no firewalls that restrict the scanning. It is also unobstructive and stealthy since it never completes TCP connections. This technique is often referred to as half-open scanning because it doesn't open a full TCP connection. Nmap sends a SYN packet as if it is going to open a real connection and then waits for a response. A SYN and an acknowledgement indicates that the port is listening, so it's open, while a reset indicates that the port is closed. If no response is received, the port is marked as filtered. Keep in mind that you need root privileges to perform this type of scan. If you don't have root privileges, you can still perform another type of TCP scanning called TCP Connect scan. Let's go to the terminal and see some examples. First, let's check if Nmap is installed by executing Nmap without any option. And it says command nmap not found and gives instructions about how to install it. On Debian and Ubuntu based distributions, you can install it by simply running apt install nmap. And it's done. You can also install Nmap for Windows or Mac, and if you want a graphical interface, install ZenMap, which is the official Nmap security scanner GUI. This is ZenMap. Let's try a TCP SYN scan. If you are root, this will be the default scanning type. I'm root. Nmap and the IP address of the other Linux machine. And we see a lot of information about the scan and the destination host. We see how much time the scan took, the MAC address of the destination host, and the open ports. By default, Nmap scans the most common 1000 ports for each protocol, TCP and UDP. We see that 4 ports are open and 996 closed ports. If you are not root, you cannot perform this scan. I open up another terminal where I don't have root privileges and try to scan the host again, this time specifying -SS, which indicates a TCP SYN scan. Nmap, -S, a lowercase s, and an uppercase s, and the IP address of the destination. And it says that I don't have the required privileges. What I can do is to perform another type of TCP scan called Connect scan. This is the default for non-root users. I simply run nmap and the IP address of the destination. Or I can specify -S and an uppercase T. It's the same. Earlier I've said that by default Nmap scans the most common 1000 ports for each protocol. What if a service has been moved to a non-standard port? Like SSH is listening on port 50,005. On the destination, let's change the SSH daemon listening port to 50,005. This is the configuration file of SSH daemon, and I'll write port and the new value, 50,005. That's the new port. I'm saving the file and then restart the service. Now SSH is listening on port 50,005. Nmap will not scan the port by default, and you cannot discover that the service is running. Let's scan the destination again. And we don't see that SSH is running. It didn't display the port as being open. In fact, it didn't scan the port at all. What I can do is specify the port manually using -p option. Let's scan the target again and specify the port manually. Nmap -p and the ports I want to scan. Let's say 20, 22, 80 and 50,005. And the destination, the same IP address. Perfect. Ports 20 and 22 are closed, and 80 and 50,005 are open. We see that the port is open, but it doesn't say who's listening on the port. What I can do now is add another option that does version detection, and that's -sv. So -sv, an uppercase V. And it's much better. It's displaying a lot of information about the services that are running on those ports. And if you want to scan all ports, you use -p- option like this. It's scanning all ports. By the way, this can take a very long time. If you press the Enter key while scanning, it will say what % of the entire scan process has been already performed. And it's done 5%. I'm stopping Nmap by pressing Ctrl+C. This was all about TCP scans. Other types of scans you can perform are UDP and ICMP scans. UDP port scanning is generally slower and more difficult than TCP. UDP port scanning is activated with the -SU option. Nmap -SU localhost. I'm scanning the localhost for UDP ports. And this is the result. And to perform an ICMP ping scan, use -SN or -SP. Nmap -SN. Both letters are lowercase. And I'll scan an entire network. And it has displayed information about all hosts that are up in this network. This is the local area network. Okay, that's all about Nmap for the moment. There's a lot of information about Nmap, but I think there are the most important things you should know. I'll attach to this lecture some resources about Nmap in case you want to dive deeper into it. Thank you. Now that you know in detail what are the port states, how to check what ports are open, on the local machine and how to scan ports on remote machines, I'll move ahead and talk about reject. Reject is another terminating target, and like drop, it denies the packet, but also sends back a reply packet to the source. By default, it replies with an ICMP port unreachable packet, and it's possible to specify the response packet using --reject -with option. Maybe you wonder why it's necessary to use reject when we have drop that silently drops any packet matched by the rule. And the answer is that sometimes it's more efficient to reject than drop packets, because dropping packets will cause TCP to retry the connection until the threshold for the retransmission is reached. The retransmission timeout is generally of tens of seconds. By rejecting packets, TCP aborts the connection, and the application gets to know that the connection has failed after just one round-trip time. Contrary to popular belief, drop does not give better security than reject. In this example, I reject forwarded or routed traffic that is going to port 69 UDP, and I inform the source by sending back an ICMP port unreachable packet. You can see the options of the reject target by running iptables -j reject --help. Let's try some examples. I want to reject SSH traffic from Linux 2 to Linux 1. This is Linux 2 and this is Linux 1. On Linux 1, I will add an iptables rule that rejects SSH traffic from Linux 2. iptables -a input -p TCP -d port 22 -s the IP address of Linux 2. -j reject. I don't specify any reject options because I want you to see the default option. On Linux 1, I'll start TCP dump, and I want to capture all the traffic from Linux 2. TCP dump, host, and the IP address of Linux 2. -n. Perfect. Now, on Linux 2, I'll scan port 22 on Linux 1 using nmap. nmap -p22 and the IP address of Linux 1. And we notice that nmap reports the port as being closed. And on Linux 1, in the TCP dump output, we can see those packets. I'm stopping TCP dump by pressing on Ctrl+C. Let's look for the packets. There are many packets, but let's take a look only at these two packets. Server 2, ending in 20, is sending a TCP packet with the SYN flag set to Linux 1, ending in 10. Here, this is the packet. The packet is dropped, and then Linux 1 is responding back with an ICMP packet to Linux 2. The ICMP packet is the default, which is port unreachable. And if I list the firewall, I'll see dropped packets. There is only one packet dropped by the rule. This packet. Now, I'll add the same iptables rule, but this time I'm using -i instead of -a. This rule will be the first rule in the chain and the rule that will match the packets. The previous rule will be deactivated because no packets will be ever been matched against it. And I want to specify what packet will be sent back to the source after dropping the incoming SSH packet. And I want a TCP reset. So --reject with TCP -reset. I'm starting TCP dump again. And I'm scanning port 22 again. the port is reported again as being closed. Let's take a look at TCP dump output. I'm stopping TCP dump. Let's look for the packets. These are the packets. We see how server 2 has sent a TCP packet with the SYN flag set, and in response, server 1 has sent to server 2 a TCP packet with the reset flag set. This is the response. Okay, one more check. I'll add this rule one more time, but this time I'm using the drop target instead of reject. This rule will be the first rule on the input chain, so it will match the packets. Drop. I'm starting TCP dump again and scanning Linux 1 again. Now the port is being reported as being filtered. That's because nothing is received from Linux 1. Let's take a look at the output of TCP dump. We can see that Linux 2 has sent SSH packets to Linux 1, which silently discarded the packets without responding back to the source. In fact, Linux 2 has sent 2 packets to Linux 1 and after that gave up entirely. Hello guys! In this video, I'll cover the log target. We've seen a lot of terminating targets like accept, drop, or reject. We'll shift our focus to a commonly used non-terminating target named log. If a packet is matched against a rule with the log target, the packet headers are logged, and then the packet continues to traverse the chain rules until it is accepted, dropped, or rejected by a rule or by the default policy. Log target is specially designed for logging detailed information about packet headers. It does this via the kernel logging facility. This information can then be read directly with dmessage or from the syslog daemon logs. Note as well that it could be a really great idea to use the log target instead of drop while you are testing a rule and you are not 100% sure about it on a production firewall. A syntax error in the rule sets could cause severe connectivity problems for your users. The log target takes 2 options that could be of interest: -log-level and -log-prefix. Log level indicates the priority or severity of the logged message, and log prefix tells IP tables to prefix all log messages with a specific prefix or string, which can then be combined with grep to track specific problems and output from different rules. Let's see an example in our testing environment. I want to log and then drop the first packet of any incoming SSH connection, the packet that establishes a new connection, by initializing the TCP three-way handshake. That's the packet that has the SYN flag set. IP tables -a input -p TCP -d port 22 -SYN. That's the first packet of the connection -j log. And -log-prefix equals, between double quotes, incoming SSH traffic. And the other option, -log-level info. Log target is a non-terminating target, and that means that the matched packet continues to traverse the chain. My second rule will drop the packet. IP tables -a input -ptcp -d port 22 -j drop. From Linux 2, I'll try to connect using SSH to Linux 1. The connection is not working because the packet that initializes the connection is locked and then dropped. On the firewall, I'll execute the message to see the kernel logs. These are the kernel logs. Among these logs, we notice the logged packets. We see the log prefix, which is the string incoming SSH traffic. There are a lot of messages, so it could be a good idea to select only the messages we are interested in, and we can do that by using a pipe and the grep command. The message, pipe, grep, and I want to see only the lines that contain incoming SSH traffic. SSH traffic is enough. And we are seeing only those rules. If I want, I can also redirect these lines to a text file for later inspection. I'm using the output redirection. ssh.txt and cut ssh.txt. We see the logs in the file. The message is only displaying a buffer in the RAM memory. If you want to see the logs after the computer restarts or at a later moment, you should read from a specific log file. Based on the Linux distribution you are using, the logs are saved in a specific file on your file system. On Ubuntu, the kernel logs are saved in /var/log/kern.log. Let's see the file using the tail command. Tail -f var log kern.log. -f option means that it will display the tail of the file in real time as data is appended to the file. By the way, tail is displaying the last 10 lines by default. I'm connecting to port 22 on Linux One again. And we notice how the contents of the log file is updated in real time. Note that the log target doesn't save the packet contents, it only saves the packet headers. If you want to save the packet contents, you should use a packet sniffer like tcpdump or Wireshark. The ttarget will clone a packet and then redirect that cloned packet to another machine on the local subnet. It's used for traffic mirroring. In this example, I clone and redirect all routed traffic to destination 80.0.0.1 to my gateway, which has the IP address 10.0.0.10. Let's see a live example. I want to clone and then redirect to Linux 2 all ICMP ping packets from the Windows machine destined to Linux 1. On Linux 1, I write IP tables -a input -p ICMP -ICMP -type echo request. These options will match incoming ping packets -j t --gateway and the IP address of Linux 2. On Linux 2, I'll sniff all ICMP traffic using tcpdump. I want to see the ICMP echo request packets. tcpdump ICMP -n. Okay, I have to be root. I'll prefix the command with sudo. And from Windows, I'll ping Linux 1. Ping and the IP address of Linux 1. Perfect. Ping is working. We notice that packets destined to Linux 1, this is Linux 1, are received also by Linux 2. That's mirrored traffic. If I list the firewall, I notice many matched packets by the rule that uses the t-target. There are 4 matched packets. 4 packets have been cloned and then redirected to Linux 2. In this lecture, we'll see the redirect target, which is used to redirect packets from one port to another on the same machine. The redirect target is extremely useful for setting up a transparent proxy where local area network hosts do not know about the proxy at all and are forced to go through the proxy. The redirect target is valid only within the pre-routing and output chains of the NAT table. Let's see how it works with a live example. On Linux 1, I want to redirect traffic that's coming to port 1234 to 22, where the SSH daemon is listening. IP tables -t NAT. The redirect target is available only on the pre-routing and output chains of the NAT table, -i pre-routing. The rule will be added to the pre-routing chain, and now the matches -ptcp -d port 1234 -j redirect -2 ports 22. Let's check if port 1234 is open on Linux 1. netstat -tupan pipe grep 1234. And it's not open, it's closed. From Linux 2, I'll connect to Linux 1 using SSH and port 1234. SSH -p from port 1234 and the IP address of Linux 1. And we notice that it's connecting to port 1234 even though there is no application listening on that port. What's happening? Packets that arrive on Linux 1 and port 1234 are redirected when hitting the pre-routing chain to port 22, where the SSH server is listening. This was just a simple example to show you how it works, but on port 22 could listen a special application that performs application filtering and inspection like Squid or other proxy does. In this section, we'll dive deeper into NAT or masquerade. What is NAT? NAT comes from network address translation and is the process of rewriting the source or the destination IP addresses of the packets as they pass through a router or firewall. Simply put, NAT enables private IP hosts to connect to the internet. There are two kinds of NAT: SNAT or source network address translation and DNAT or destination network address translation. SNAT replaces the private IP address from the packet with the public IP address of the router external interface. NetFilter framework enables a Linux machine with an appropriate number of network cards or interfaces to become a router capable of SNAT. SNAT always uses the NAT table and the post-routing chain. You'll sometimes hear the term masquerade. What is masquerade? It's a special case of SNAT used when the public IP address of that NAT router is dynamic. It will automatically take and use the IP address of the outgoing network interface for network translation. We use masquerade when there is a DSL, coaxial or fiber internet connection with a dynamic IP address. When configuring the Linux machine for SNAT or masquerade, the NetFilter framework also performs port address translation or PAT. It means that it will translate the source port of the packet as the packet is routed. Let's see how we configure SNet or masquerade. The first step is to enable the routing process on the Linux machine. By default, routing is disabled in Linux, and there are two possibilities. The first possibility is to write the value 1 in a special file. 1 means routing enabled and 0 means routing disabled. It's common to use the echo command and a redirection like this. Echo 1 output redirection /sys/net/IPv4/IP_forward. The second possibility is to edit a file named sysctl.conf from the etc directory. And inside that file, we add net.ipv4.IP_forward equals 1. After editing the file, it is required to restart the network service. It can depend on your Linux distribution, but for example on Ubuntu-based distributions, you execute systemctl restart networking. If you enable the routing process using the first way, which is writing 1 to IP_forward file, it's not required to restart the network service. That was the first step. The second step after enabling routing is to configure SNet or masquerade. Add an IP tables rule to net table and pre-routing chain that matches packets that should be netted. Specify the external interface using -o option and use -jsnet --to source and the public IP address of the router's interface, or -j and masquerade as target. Let's look at an example. First, we enable the routing process and then we add a rule to net table and post-routing chain that translates all packets that have the source IP address from the network 10.0.0.0/24. The source IP of the packets will be translated to source 80.0.0.1, which we'll suppose is the public IP address of the router. Or instead of -jsnet --to source, we could simply use -j masquerade, and netfilter will automatically take and use the public IP address of the given interface. In this case, ETH0. That's all. In the next lecture, we'll configure together a Linux machine to be router and perform net. In this lab, we'll configure net from scratch on a Linux machine using netfilter and IP tables. This is our topology. This is my Windows recording computer that's connected to the net router using an Ethernet connection through a layer 2 switch. The net router runs Ubuntu and is connected directly to the internet using a wireless connection. The name of its external interface is WLO1 and the name of its internal or LAN interface is ENP8S0. You can see the names of the Linux interfaces by running ifconfig command. Yes, I know, these names are difficult to remember, but we don't give them too much importance and take them as they are. The LAN network address is 10.0.0.0/24. The Windows PC has 10.0.0.2 and the Linux router has 10.0.0.1 on the internal interface. The public IP address, which is the IP address of its external interface, is dynamic and it's not important to us. On Windows, on the Ethernet interface, I'll set a static IP. 10.0.0.2, the subnet mask will be 255, 255, 255, and 0, it means /24, and the default gateway will be the IP address of the NAT router, 10.0.0.1. And the DNS server will be the public DNS server from Google. Perfect. Let's get started with the NAT configuration. I'm gonna connect using SSH and PuTTY to the Linux NAT router. There is another wireless connection between Windows and Linux router, connection that will be disabled at the end. I'm using it only for this configuration. This is the NAT router, and I've become root. All iptables commands should be run by root only. The first step is to enable the routing process on the Linux NAT router. Echo 1, the output redirection, /proc sys net IPv4 /IP_forward. Now the Linux machine is a router. The second and the last step is to create an iptables rule that matches traffic that will be netted. Keep in mind that we should always use the NAT table and the post routing chain, and the target will be SNet or masquerade. We use SNet when we know the public IP address of the router, that's a static address, and masquerade when the public IP address is dynamic and it changes frequently. That's a dynamic IP address. iptables -tnet -a post routing -s the entire subnet 10.0.0.0/24 -o the outgoing interface, the external interface of the router, WLO1 -j masquerade. By the way, it's not mandatory that all LAN traffic, like in this example, to be netted. It's possible, for example, to net only DNS, email, HTTP, and HTTPS traffic. We use the required matches. Okay, that's all. Let's check if it's working. On the Windows machine, I'm going to disable the wireless interface. I should be able to access the internet using the Ethernet connection and the NAT router I've just configured. So, disable. Good, it's disabled. I'm opening the command prompt cmd.exe and then test the layer 3 connection to an external IP address like, for example, 8.8.4.4. By the way, this is another public DNS server from Google. And it's working. The packets have reached the Linux router, which has translated the source IP address with the IP address of its external interface and sent them to the destination on the internet. I'm opening a new connection to the NAT router, and then I list the NAT table. By the way, the first SSH connection froze. So 10.0.0.1, and here I have a custom port 2299. And it's working. I'm authenticating. And I'm becoming root. iptables -tnet -vnl. We notice that 31 packets have been matched and translated by the rule. Also keep in mind that the configuration is not saved after the system is restarted. If you want to activate NAT at boot time, you should write the configuration inside the script and set the script to execute it at boot time automatically. In this video, we'll talk about DNet, which comes from Destination Network Address Translation, aka port forwarding. Destination Network Address Translation, or port forwarding, is a technique that allows connections from the internet to servers with private IP addresses inside LANs. The internet client connects to the public IP address of the DNet router, which in turn redirects the traffic to the private server. The private server, which has a private IP address, stays invisible all the time. The clients from the internet do not know that they are not connecting to the server with the public IP address, which is the router, and that are connecting to another server in a LAN. DNet uses net table and pre-routing chain and the IP tables rule target DNet. Let's go to the terminal and configure DNet or port forwarding on the net router. In this example, there is a web server running on a private IP address which is 10.0.0.2 and the net router has the private IP address 10.0.0.1 and the public IP address 80.0.0.1. Port forwarding means that users from the internet can communicate with the web server that has the private IP address. As I've already explained, they will connect to the public IP address of the router, which in turn will change the destination IP from 80.0.0.1 to 10.0.0.2 and then forward the traffic to the private web server. SNet is assumed already configured and it's working properly, meaning that traffic from the web server to the internet clients goes through the net router. You can take a look at the previous lecture to see exactly how it's done. Enough talking, I'm writing the IP tables rule. IP tables minus tnet, I must use the net table and the pre-routing chain, minus a pre-routing. And the HTTP traffic, so p TCP minus d port 80, minus j dnet. And minus to minus destination and the IP address of the web server 10.0.0.2. That's all. Now, traffic that is coming to 80.0.0.1 with the destination port 80 and protocol TCP will be translated and forwarded to destination 10.0.0.2. Another possibility is to specify another port as a match, let's say 8080, and :80 here after the private IP address. How will it work? Traffic that's coming to 80.0.0.0.1 and port 8080, so the client is connecting to port 8080, will be forwarded to 10.0.0.2 and port 80. Also keep in mind that the configuration is not saved after a system restart. If you want to activate port forwarding at boot time, you'll write the configuration inside the script and set the script to execute it at boot time automatically. Now that you know how to configure NET on a Linux router, let's do a small project that can be very useful. Suppose your LAN is connected to the internet using two different service providers. The NET router is running Linux. Your task is to create a script that configures the NET router to load balance outgoing routed traffic in the following way. SSH, email, and web traffic will use the first connection, so the first ISP, and all other traffic will use the second service provider, ISP2. One important remark is that internet traffic is asymmetric. That means that we cannot force a router to select a specific route. What does it mean? It means that even though we send traffic using the first connection, traffic could return back through the second service provider. Okay, these are the project requirements. In the next video, I'll show you how I would do it in case you get stuck. Good luck! This lecture is the answer to the assignment given to you in the lecture prior to this one. This is just a recording of me thinking loud and walking through the assignment. Maybe you took another approach and that's fine as long as you get the end result. I'm gonna create a script called loadbalancenet.sh. The first line is the shebang. Let's define what services I'm gonna configure for net using the first ISP connection. And there are the following services and their ports. So there is web, and that means 80 and 443, these two ports. Another service, email, and there are more ports, 25 for SMTP, 465 for SNTPS, 143 for IMAP, 993 for IMAP-S, 110 for Post Office Protocol, POP, and 995 for POP-S, so POP over SSL. And there is also SSH that uses port 22. Perfect. I want to remain flexible, so I'm creating a variable that contains the ports. It's easier to add or remove a port in the future this way. And the name of the variable will be ISP1 equals, and the ports between double quotes and spaces between them. So 22, 25, 80, 110, 143, 465, 993, and the last port 995 for POP-S. This is the traffic that will use ISP1. The next step is to flush the net table of post-routing chain. When I run the script, it will start each time from scratch. So IP tables minus tnet minus f post-routing. Good. The first step is to enable the routing process on the Linux machine. Echo 1, and I'll redirect the value 1 to a specific file. And the file is /proc sys net IPv4 and IP forward. Now the Linux machine is a router. Okay. Using a for loop, I'll iterate over the previous declared variable and write a rule for each port in that variable. So for port is a temporary variable. I can use any name I like in $ and the name of the variable, ISP1. Do and done. And between do and done, I write the IP tables rule that performs snet. Let's check what will be the outgoing interface. In this case, it's ETH1, Ethernet 1. You should change it according to your own topology. You see the name of the interface by running ifconfig. And the IP tables rule, IP tables minus tnet minus a post routing minus ptcp minus d port $port, the temporary variable of the for loop, minus o, and the outgoing interface, ETH1 minus j masquerade. I'm using masquerade and not snet because I don't know the public IP address of the router. Maybe it's a dynamic one. This is enough for the first connection, for ISP1. Another rule is required that will masquerade all other types of traffic through the second connection. So if a packet was not translated until this point, and this means using ETH1 and the first ISP, it will be source translated and sent over the second connection. So using the interface called ETH2. So IP tables minus tnet minus A post routing minus O ETH2 minus J masquerade. Okay, that's all. I am saving the script, then make it executable and run it. I'm listing the net table, IP tables minus tnet minus VNL. Okay, and we see here all the rules. This was my solution to the assignment given to you in the last lecture. Hello guys and welcome back. In this lecture, we'll talk about a more advanced topic called user-defined chains or custom chains. By default, the IP tables filter table consists of 3 chains. There are input for incoming traffic, output for outgoing traffic, and forward for routed traffic. Besides these 3 built-in chains, you can add as many other custom chains as you like in order to simplify managing large rule sets. We can create a very good firewall without user-defined chains, just that user-defined chains are useful in optimizing the rule set. They allow the rules to be organized in categories, and this way the firewall becomes scalable. Custom chains behave just as built-in chains, introducing logic that must be passed before the ultimate fate of a packet is determined. From a built-in chain like input, output, or forward, using -J and then the name of the custom chain, you can jump into any number of user-defined chains and even jump between them. The matched packet traverses the user-defined chain, and after that the control is returned to the calling built-in chain, and matching continues from the next rule in the calling chain. This was the logic of user-defined chains or custom chains. Let's talk about the return target. If there is a match in a custom chain and the target of the rule is return, the processing of the packet resumes back immediately in the main built-in chain that called the custom chain. The return target can be used also inside the built-in chains like input or output, and in that case no other rule will be inspected and the packet executes the default policy of the chain, which is either accept or drop. Custom chains introduce many ways of optimizing things. Like say you want to stop using the rules of a custom chain temporarily without deleting the chain. You simply delete the jump from the main built-in chain to the custom chain. Let's take a look at available options. -N creates a new user-defined chain and -X deletes a user-defined chain. To list the rules of a user-defined chain, you use -L as usual. Note that before deleting a user-defined chain, the rules of the chain must be flushed or you get an error. To flush the rules of a user-defined chain, you use IP tables -F and the name of the chain. This was just an introduction to custom chains. In the next lecture, I'll show you how to implement and use custom chains. See you in a second. Let's go to the terminal and take a look at some examples. IP tables -VNL lists the default built-in chains of the filter table. There is input, output, and forward chains. Now let's create a new chain called myChain. IP tables -N, an uppercase N, and the name of the chain, myChain. Now, if I list the filter table, I see all the built-in chains plus the user-defined chain called mychain. Let's add an iptables rule to mychain. iptables minus a mychain and the matches minus p ICMP minus minus ICMP minus type echo request minus j drop. This rule will drop all incoming echo request or ping packets. At the moment, the rule exists, but it's disabled because there is no jump to my chain from a built-in chain. I'm gonna test this by sending ping packets from Linux 2 to Linux 1, ping and the IP address of Linux 1. And we notice that ping is working. Echo request packets are still accepted by Linux 1. Back on Linux 1, I will enable mychain. How will I do this? From the input built-in chain, I'll jump to mychain. iptables minus a input minus j mychain. And we notice how ping has stopped. That's because the rule from mychain has been activated and packets are matched and dropped by the rule. Let's dive deeper into how it works. The packets traverse the input chain, and if they are not dropped or accepted by a rule, they jump into mychain. In this case, there are no other rules on the input chain that could drop or accept them, so they start traversing the custom chain, which has only one rule that drops the packets. If the packets hadn't been dropped, they would have returned to the input chain and would have continued traversing the input chain until a rule drops or accepts them or the default policy is executed. If I'm listing the firewall again on Linux 1, we notice 121 matched packets by the rule of mychain. These are dropped ping echo request packets. But if we take a look at the rule of the input chain, we see a larger number. 145 packets have traversed the user-defined chain. The number is larger because not only ping packets traversed the user-defined chain, but all incoming packets. Or simpler said, 145 packets traversed the input chain and then my chain, and 121 of them were of type echo request and dropped by the rule of my chain. If I want to delete my chain, I use iptables minus x and the name of the chain, my chain. Let's try it. And I've got an error. I cannot delete a chain that has rules. So first I must flush the rules of the chain. iptables minus f my chain. And by the way, ping has started again. Now there is no rule that drops the incoming ping packets. If I list the firewall, I notice that there is no rule in the chain. Let's try to delete the chain again. iptables minus x and the name of the chain. And I still have an error. Why is that? That's because there is a reference to this chain from the input chain. As a conclusion, we cannot delete a user-defined chain if the chain has rules or if another built-in chain is referencing the user-defined chain. So in order to delete the custom chain, I must first delete the rule from the input chain that references the custom chain. iptables minus f. I am flashing all the chains. There is no reference to my chain and I can delete it. IP tables -x, my chain. By the way, if I execute IP tables -x, so without the name of the chain, it will delete all user-defined chains. Let's see an example where a user-defined chain is created and used in order to have a more organized and scalable IP tables firewall. To save time, I've already created this firewall script and will refactor it together using user-defined chains. This is the script. For the beginning, let me explain to you what this firewall script does. After flashing all chains of the filter table, I allow outgoing or generated packets that are in new, established or related states. These are in fact all packets except invalid ones. Then there are two rules. One rule that allows incoming SSH traffic from any source to our Linux machine, and another rule that allows the return generated traffic. This means that anyone is allowed to connect to this Linux machine using SSH if the user has the right credentials. And I also permit 4 MAC addresses, so 4 hosts from the same LAN, to initiate connections to the Linux host. And finally, I set the drop policy on both input and output chains. Any packet that was not matched and accepted by a previous rule will be dropped. Now, let's see how we can refactor this firewall script to scale well in case that instead of 4 MAC addresses, there will be 50 MAC addresses. I also want the possibility to switch on and off all rules related to MAC addresses. Let's get started. I will create a user-defined chain. I could create the chain accepted MAC, and instead of adding these 4 rules to the input chain, I can add these rules to my new user-defined chain, and then I will jump from the input chain to my user-defined chain. If the packets will not be accepted by a rule of the new chain, they will continue traversing the input chain for further processing. Okay, let's do it. I'm creating a user-defined chain called accepted MAC. IP tables -n accepted _MAC. Alright. And I add these rules to my new chain accepted MAC. The first rule, the second rule, and the last 2 rules. Okay. Now I must jump from the input chain to my newly created chain called accepted MAC. IP tables -a input -j accepted MAC. And one last thing, at the beginning I want to delete any user-defined chain. IP tables -x. So each time I'm starting from scratch. Okay, that's all. Let me explain to you in detail what will happen with the packets. I think everything is clear for outgoing traffic. I'm accepting all outgoing traffic except invalid packets. Then, if an incoming packet is of type SSH, it will be accepted. If a packet was not accepted nor dropped, it will further traverse the accepted MAC chain. And if the source MAC address is one of these 4, the packet will be accepted. If not, it will continue traversing the input chain. In this case, there is no other rule in the output chain, and the packet will be dropped. I am saving the file, making it executable, and running it. We can see the user-defined chain. There is one reference to it. Here on the input chain, there are already 4 packets that have traversed the chain, but no packet was matched against a rule of the chain. Now, if I want to disable all the rules related to the MAC addresses, I simply comment out the rule where the jump is made. So this rule. Instead of deleting these 4 rules, I have just commented out this single rule. This is one of the advantages of using user-defined chains. This lecture is a very important one, and maybe it's a good idea to bookmark it for future reference. In order to write efficient firewall rules, you must deeply understand how a packet traverses the net filter tables and chains. A packet can be found in one of the following scenarios. It comes from the network and is destined for our host, which is the final destination of the packet. In this case, the packet traverses the pre-routing and then the input chains. The second scenario is when it comes from the network, but it's not destined for our host. In this case, our host is not the final destination of the packet. The packet must be routed or forwarded by the Linux machine, which is the router in this case. The packet traverses the pre-routing, forward, and then the post-routing chains. And the last scenario is when the packet is generated by an application on the host. The local Linux machine is generating the packet. In this case, the packet traverses the output and the post-routing chains. Let's move on and have a closer look at a packet that is destined for our own local Linux machine. It would pass orderly through the following steps before actually being delivered to the application, client or server, that should receive it. When a packet first enters the firewall, it hits the hardware and then gets passed on to the proper device driver in the kernel. The bits of the physical layer are transformed into a data frame and then into a packet. After that, the packet starts to go through a series of steps in the Linux kernel before it's either sent to the correct local application, client or server, or dropped. The packet starts traversing the rules from the route table of pre-routing chain. This is where connection tracking takes place, and in this table and chain we add rules that match packets that should skip the connection tracking system. Then the packet traverses the mangle table of pre-routing chain. At this point, we can change values from packet headers like type of service bigs or time to leave. The net table of pre-routing chain is used for destination network address translation or port forwarding. Any traffic filtering should be avoided here. After the net table of pre-routing chain is traversed, it comes the routing decision. The Linux kernel should decide if this host is the final destination of the packet or it should be routed to another host. If this host is not the final destination, the packet will be routed and it gets to mangle table and forward chain. We'll dive deeper into this in another lecture. But if this host is the final destination, the packet starts traversing the mangle table of input chain. Here we can change values from the packet headers if we haven't already done that on the mangle table of pre-routing chain. After this step, the packet starts traversing a very important table and chain, which is the filter table of input chain. This is where we perform filtering for all incoming traffic destined for the local Linux machine. All incoming packets destined for the local host will pass through this chain, no matter via which interface or direction they came from. Filtering means accepting or dropping the packet. If the packet is not dropped, it goes to the local process, the client or the server application. This could be, for example, a web browser like Firefox or a server application like Postfix, Nginx, or SSH daemon. That's all. This is how all incoming packets are inspected against the rules of IP tables, tables, and chains. In this lecture, we'll take a deeper look at how outgoing or generated packets traverse the netfilter tables and chains. First, the packet is created by the local process, the client or the server application. Then, it starts traversing the rules of the route table of the output chain. Here, there are rules used to skip the connection tracking system of netfilter. After that point, the packet traverses the rules from the mangle table of the output chain. At this point, we can change values from the packet's header, like time to leave or type of service. At the next step, the packet starts traversing the NAT table of the output chain. Here we can write rules that translate or change the source IP address of the packet. NAT takes place also on post-routing chain, but through post-routing chain goes also routed or forwarded traffic. So maybe we want to have different NAT rules for generated packets than for routed packets. After that point, at number 5 on the scheme we are looking at, comes a very important table, the filter table of the output chain. Here we perform filtering, which means dropping or accepting outgoing traffic. It's very important to filter also outgoing traffic, not only incoming traffic, because we don't want possible malware or rootkits to communicate outside our network. After the packet traverses the filter table of the output chain, the Linux kernel checks if the packet is routable, or if the IP destination is in the routing table. If it's not routable, the firewall drops the packet. But if the packet is routable, it starts then traversing the mangle table of post-routing chain. Here we can change other values of the packet's headers, and then the packet starts traversing the NAT table of the post-routing chain. Also here we define rules for source network translation or masquerade. If the packet has reached this point, the driver of the network interface, which is wireless or wired, transforms the packet into a data frame, and then the physical layer packs the frame into bits and sends the bits on the physical medium. Okay, that's step by step how outgoing or generated traffic traverses the tables and chains of netfilter. In this lecture, we'll see in great detail how routed traffic traverses the tables and chains of netfilter framework. We are assuming that the packet is coming from the network and is destined for another host on another network. First, the information is on the medium, wireless or wired, in form of bits. Then, the interface driver transforms the bits into a data frame and then into a packet. The packet starts traversing the route table of pre-routing chain. This is where connection tracking takes place, and in this table and chain we add rules that match packets that should skip the connection tracking system. Then the packet traverses the mangle table of pre-routing chain. At this point, we can change values from the packet headers like type of service or time to leave. The NAT table of pre-routing chain is used for destination network address translation or port forwarding. Any traffic filtering should be avoided here. After the NAT table of pre-routing chain is traversed, it comes the routing decision. The Linux kernel should decide if this host is the final destination of the packet or if the packet should be routed to another host. Okay, if this host is the final destination, then this is an incoming packet and it goes to the mangle table of the input chain. In a previous lecture, we've already seen what happens in this case. But if the Linux machine is not the final destination, the packet must be routed, and it starts traversing the mangle table of the forward chain. After that, the packet starts traversing the filter table of the forward chain. This is a very important place where we add rules for filtering routed traffic. Here we decide what kind of traffic is allowed from the LAN to the internet and back. The next step, if the packet is not dropped, is to start traversing the mangle table of the pre-routing chain. We can change here values of the packet's headers, and then the packet starts traversing the NAT table of post-routing chain. Here we define rules for source network address translation or masquerade. If everything is okay and the packet hasn't been dropped until this point, the packet leaves our Linux machine. The driver of the network interface transforms the packet into a frame, and the physical layer transforms the data frame into bits and sends these bits on the medium. Okay, that's how routed or forwarded traffic traverses the tables and chains of NetFilter step by step. Thank you.
Now I will explain some basics about Bash shell scripting. First, a shell script is a text file that contains commands and other programming structures like variables, loops, and so on, and can be run. A shell script is created using the preferred text editor like VI, Nano, Pico, and so on. For example, I use VI or VI improved. Let's create a script. Script 1.sh. The first line of a shell script starts with a hash sign, then comes an exclamation mark, and then the absolute path to the program that executes the script. In our case, it's the bash shell, so bin bash. This is the absolute path on Ubuntu server. We can define variables only by specifying their names, for example IPs, and now between double quotes I can have a value, a string value. For example 129.66.3.4, 10.0.0.1, 5.5.5.5, and so on. Okay. We can get the value of the variable by putting the $sign in front of the variable name. For example, the value of variable IPs is $IPS. If we want to run the script, first we must save it, then we make it executable by specifying at least 700 as a permission. And now we can run the script specifying its relative path. This means dot the current directory slash and the name of the script. As you can see, the line number 5 brings the value of the variable IPS is, and then it replaces the name of the variable with its value. Pay attention that you can't execute the script simply by its name, like script1.sh. The bash shell doesn't look for the script inside the current directory, so it doesn't find the script. We get the command not found error. So we execute the script using / and the name of the script. Okay, we can execute the script also using its absolute path.
like this, but it's easier to use the relative path. Inside the script, we have some predefined, some built-in variables. These are $1, $2. Let's see what they contain. For example, I write $1 is $1. If I want to cancel the special meaning of the $sign, I put a backslash in front of the $sign. Now, the $sign is not a special character, it's the literal. So line number 7 will print $1 is, and then the value of $1. I copy paste this line and I replace $1 with $2 with $3. Another built-in variable is $hash. We'll see what it contains in a minute when we'll run the script. Backslash $hash is $hash. There are more variables, but for this moment, these are enough for us. If we want to program a for loop, for example, we want to iterate through this variable, through IP's variable, we can simply run for IP in $IPs, do, done. And between do and done, I have a block code with instructions. For every iteration, the variable IP has a value from the IPS list of variables, where the space is the separator. So if I write echo IP has or is $IP, what is the script going to print? It will print the first value till space, the second value, the third value, and so on. And if we want to test the value of a variable, we simply use the if construction. So if square bracket, and now, for example, $1 minus EQ equals, for example, 55. This means if the value of the built-in variable named $1 equals 55, then execute the following lines. I have just one line. $1 is 55. Else echo backslash $1 is not 55. Fi closes the if. We can talk more about bash scripting, but for our following examples, this is enough. Okay, I save the script. Now I run the script. 1, 2, 3, 4, 4, 4, XX. Okay, what do we see? First let's display the value of the script. So the value of variable IPs is, and I printed the value of the variable, then $1 is the first argument of the script. The first argument is the script, is the string that comes after the script name. So 1, 2, 3 is the first argument. Then 444 is the second script argument, and XXX is the third script argument. $hash contains the number of arguments. We have 1, 2, 3 arguments. $dash is 3. We don't have a fourth argument because we have only 3 arguments. That's why $4 is empty. Okay, and after that, this is my for loop. I iterated through that variable, through IP's variable, and I printed each time a value from that list. And my if test, it verifies if the first argument equals 55. My first argument is 1, 2, 3, so it doesn't equal 55. So it prints $1 is not 55. If I run the script one more time, 55, something like that, it prints $1 is 55. The last thing I show you in this lesson is how to read a variable from the standard input or from the keyboard. Let's take another example. Echo -n makes the cursor to remain on the same line. and now enter something. Read my variable, echo, you entered my variable. What happens? The third line brings at the terminal enter something, then on the fourth line a variable named my variable is created, and the value the user enters at the terminal will be allocated to that variable. So the variable will have the value that the user entered at the terminal. And on the line number 5, the script brings you entered and the value you have just entered. Let's test it. Read variable, the script stopped and waits for the user to enter something. This is just an example. You entered, this is just an example. Or, one more time, 6.5.3.56. You entered 6.5.3.56. In this lecture, I'm going to show you how to automate some IP tables tasks using shell scripts. Let's suppose we noticed some strange activities in our server logs, or maybe we seen some IPs that try to scan our server, or we received many spam emails from an IP or from a network address, and we want to block all incoming packets from that IP address. What is interesting is that we can automate this task. More interesting and useful is that a user that doesn't know much about IP tables and Linux firewalls can simply run the script blocking packets from that IP address. The user doesn't need to know about commands, rules, about ports and so on. He just runs the script and packets from that IP address will be blocked. Let's see an example. On server 1, I'll create a script that blocks incoming traffic from the IP address that is specified as the first argument of the script. I create a script named block IP, block_IP.sh. The first line indicates that this script will be run by bash. Using echo, I write at the terminal dropping traffic from $1. As we've seen in the previous lesson, $1 means the first argument of our shell script. And now the IP tables rule. It is very important to add this rule using -i, not -a. Maybe our firewall already has many rules, and maybe there is a rule that permits traffic from that IP address or from the protocol that IP address is using. So it's important to add a rule that will be the first rule in the chain. So IP tables -i input -s, and now I write $1. $1 means the first argument of the script. The script will be called using the IP address, the offending IP address, as the first argument, -j drop. I save the script, I make it executable, and now on server 2, let's suppose we want to block the connection, the packets from server 2. Let's check that the connection between server 2 and server 1 is up. I will ping server 1 from server 2, so ping and the IP address of server 1. Ping works. And now back on server 1, first I check the firewall. Maybe I have some rules. Okay, I have some rules. It doesn't matter what they do. I'm not interested because my rule will be the first, so the packets will be dropped. Block IP, and now the IP address of server 2. Ping stopped. Packets from server 2, no matter of protocol, will be dropped. Let's see the firewall. The line that was added by the shell script is the first line on the input chain and already dropped 14 packets. One interesting thing is that we have another rule. This is the first, second, third, the fourth. We have the fourth rule that accepts any packets from any IP address inside my local area network, also from server 2. But because my line is the first, will drop the packets. Now I want to optimize the script. What if the user calls the script without an argument? So he calls the script like that, block IP, and presses enter. We get an error because you ran the IP tables command without the -s match. So inside the script here, we must specify the value of the source IP address. And if we run the script without an argument, $1 is empty. What can we do? There is another built-in variable named $hash that contains the number of arguments. I must verify that the script was called using one argument. So if $hash equals 1, then I run these 3 lines, this block of code. Else, echo, this script must be run with an argument, or better, with the blocked IP address as argument. Okay, I close the if using fi, I save the script, and now run it one more time without an argument. And we can see we got no error because the line number 10 was executed. So the else branch was executed because $hash is not 1. If I run the script using an argument, for example 3.0.0.0/8, I blocked the entire network address space. Let's see another example. Let's suppose we want to block access to a specific service that runs on our server. For example, we want to block connections to port 22 or to port 25 or to port 80 or whatever port we want. I create a script, block service.sh, echo blocking $1 port $2. $1 is the first argument of the script, $2 is the second argument of the script. The first argument of the script will be the protocol, for example TCP or UDP, and the second argument of the shell script will be the port, because we can block a TCP or an UDP port. IP tables -i, it's very important to specify -i. My rule must be the first, otherwise other rules could permit that traffic. -i input -p $1 -d port. The packet is coming to my service $2 -j drop. Echo done. And because we already know how to check that the script was run with the correct number of arguments, we write here we have 2 arguments then, and we have this code block. It's easier to follow what happens if we indent the code. Okay, else echo the script was run with the wrong number of arguments. Okay, we make the script executable. I want to permit again the traffic from server 2 just to test my second script. So IP tables -i input -s and the IP address of server 2. Okay, ping started. And now from server 2, I want to check if port 22 is open. So nmap -p22 and the IP address of server 1. Port 22 is open. And now I want to drop connections from any IP address to port 22. So block service TCP 22. Blocking TCP port 22. Now back on server 2, I scan one more time the port 22 and I notice that port 22 is filtered. Yeah, because my script blocks connections to port 22 TCP. Okay, my SSH connection from my Windows recording box already dropped, but that's fine. In this lecture, I'm going to show you how to create a custom firewall for a web hosting server. On our server, run the following services. We have a web server like Nginx or Apache, a MySQL database server, postfix or an email server, a POP IMAP server, a FTP server like ProFTP, a DNS server like Bind, and the OpenSSH server for management SSH connections. Our firewall has the following requirements. We want to allow incoming connections to all running services from any IP address. Management SSH connections are allowed only from 5 management IP addresses. Then no more than 50 concurrent connections from the same IP address are allowed to the Nginx web server, and all traffic from some hosts inside the same LAN with our server is allowed. We identify those hosts by MAC address. Let's see how it's done. There are some things we must do even if they are not specified. For example, I must flush the firewall. Flush the filter table from input and from output. It's a good idea to comment lines because when we'll return to this script, it will be easier to know what we have done. Or if somebody else reads our script, he will understand easier. IP tables -F. It doesn't matter what happens with the forward chain because we are not using the forward chain. Our host is not a router. We must permit loopback interface traffic on input and on output. So, permit loopback interface traffic. IP tables -A input -I lowercase I incoming interface LO -J accept. IP tables -A output -O LO -J accept. Okay. Then the first requirement, incoming connections to all running services are allowed. Because there are many services, it's easier to create a variable and then iterate through that variable, allowing port by port. I create a variable permit TCP, and this variable contains a list of allowed ports, allowed TCP ports. For SSH, I have a special requirement. I don't write the 22 port here. The first ports are 20 and 21 for FTP, 25 for SMTP. SMTP also uses 465 SMTPS, SMTP over SSL. Then we have 80 and 443 for HTTPS, 110 and 143, 110 is POP, 143 is IMAP, 993 is for IMAP over SSL. Okay, what other services we have? Nginx, web server, this means 80 and 443, database server. Usually the database server uses local connections. We don't allow incoming connections from the internet because the client, the database client, which is PHP or Python or another scripting language, runs on the same computer, on the same host. It's not necessary to have a special line for my database server. Of course, if it must allow incoming connections from the outside, we must specify some IP tables rules. Postfix email server. I wrote 25 and 465. DAFCOT POP IMAP x110, 143, and 993. Okay, DNS server uses UDP. We'll have another rule for that. And for OpenSSH server, I'll have another rule. Anyway, it's very easy to add some ports or to remove some ports from this list. This is the advantage of automation using shell scripts. Now, using a for loop, I will iterate through this variable and I will permit port by port. For port in $permit TCP, do and done. Between do and done, I'll have a rule that allows incoming traffic to my TCP port. IP tables minus a input minus ptcp minus d port $port, because my variable port will have a value from my list, value after value. First, my port variable is 20, then is 21, then 25, and so on. Minus j, accept. As I said, it's a good idea to comment the lines. So here, allowed TCP ports. I must also permit DNS traffic. This means IP tables minus a input minus p UDP. DNS uses UDP minus d port 53 minus j accept. And here I comment the line allow DNS traffic. Then the second requirement is to allow SSH connections from 5 management IPs. I'll have another variable, permit SSH, and now some IPs. First, my Windows recording IP, because otherwise my SSH connection will drop. Let's see what IP I have. I have 192.168.0.145. Okay, and then I'll write some random IP addresses. I don't have specific IP addresses at this time. Okay, that's enough. It doesn't matter how many IP addresses I have, because I'll iterate through this list and I'll permit IP after IP. For IP in $permit SSH, do, done. And here IP tables minus a input minus ptcp minus d port 22 minus s, the packet is coming from that IP address $IP, the value of my variable that is created and that iterates through that list. Minus j, accept. I also comment this line, IP addresses to connect using SSH. What other tasks we have? No more than 50 concurrent connections from the same IP address are allowed to the Nginx web server. So permit no more than 50 concurrent connections from the same IP address to our web server. For this task, we'll use the -m conlimit match. If we don't remember the options, we could open another terminal and there we write IP tables -m conlimit --help and we see the options of this match. I'll use --conlimit above 50 with drop. So I'll drop if there are more than 50 concurrent connections from the same IP address. Back on my terminal, IP tables -a input minus p TCP minus d port. Okay, I have to drop if there are more than 50 concurrent connections from the same IP address for 2 ports, for port 80 and 443, HTTP and HTTPS. I can write 2 IP tables rules, or I can use the -m multi-port match with --d ports and now 80,443. This line matches packets to port 80 or port 443. -m conlimit let's see one more time, conlimit above. Conlimit above 50 minus j drop. That's all. Now the fourth task. All traffic from some hosts inside the same LAN is allowed. For this task, I'll use the -m mac match. First, I write a comment. So permit all traffic from the following MAC addresses. For this task, I create another variable with those MAC addresses and I will iterate through that variable. Allowed MAC. And now I need some MAC addresses. I just take some random MAC addresses at this moment. So I'll take my interface MAC address with copy paste, and I paste it some more times. And I'll modify the last two characters just to have different MAC addresses. For MAC in $allowed MAC do and done. And here my IP tables rule that allows incoming traffic from those MAC addresses. IP tables -a input, -a MAC, -- MAC source, and now $MAC -j accept. This IP tables rule will accept traffic that has the source MAC address that is specified here. Perfect. Till now I have rules that only accept traffic on the input chain. What should we do with traffic that is generated by our server, with the output traffic? For example, I could use the connection tracking feature of the NetFilter firewall and I allow new packets on the output chain. IP tables -a output, -m state, -- state, and now on the output chain I allow new packets. This is the first packet of the connection. Established packets, these are the second, the third, and so on. Established and related. -j accept. If I use connection tracking, it's a good idea to drop invalid packets on input and on output chain. So here at the beginning of my script, I write IP tables -a input, -m state, --- state invalid, -j drop, and IP tables -a output, -m state, --- state invalid, -j drop. I'll use the drop policy on input and on output chain, and that means that these invalid packets will be anyway dropped, but I prefer to drop them faster at the beginning of the firewall and not after all those rules have been checked. And I think I solved all the tasks. IP tables. It was a spelling error here. What should we do? We must set the default policy to drop. Set default policy drop. IP tables -p input drop. IP tables -p output drop. Any packet that hasn't been accepted by an IP tables rule will be dropped. I save the script, make it executable, and run it. Okay, I list the filter table from input and output chain, and I can see I have 28 accepted packets. These are packets generated by my server. Yeah, they are new, related, or established. I didn't specify what happens with ICMP traffic. If there is no special reason, it's a good idea to allow ICMP packets. So I open the script one more time, and I want to allow ICMP packets on input and on output chain. I comment what the following lines do. Allow ICMP traffic. IP tables -p ICMP -j accept, and IP tables -a output -p ICMP -j accept. If I want this firewall to run automatically at boot time, I must use iptables safe and iptables persistent, because here it's Ubuntu server. Okay, this is the output. I redirect the output to etc iptables rules v4. Now, when the server starts, it will automatically load iptables rules from this file. It's very interesting that anyone can use this script. A user doesn't have to know much about iptables or about targets, matches, and so on. If we want, for example, to allow some other ports, I just write them here and they are allowed. If I don't want to allow port 25, I just remove the port 25 from my list. I save the script and run it. And the script updates the firewall. If I list the firewall, we can see there is no more port 25, and my new ports like 1111 and so on are there. Now that you had some chances to play with shell scripts, I want to give you an assignment. I want you to create a shell script that requests an IP address and then asks if the traffic from that IP address should be accepted or dropped. Of course, instead of an IP address, you could write a network address. When running the script, after entering the IP or network address and drop or accept string, it should add some iptables rules that drop or accept traffic from that IP or network address. Now, I want to give you a hint. You can use the read shell command in order to read a variable, and then using an if testing condition, you check if the traffic should be dropped or accepted. Based on the user answer, the appropriate iptables rules should be inserted into the filter table and input chain. In the next video, I'll show you how would I do it in case you get stuck. Good luck and see you in the next lecture. This lecture is the answer to the assignment lecture right before this one. This is just a recording of me thinking loud and walking through the assignment. Maybe you took another approach and run other commands, but that's okay as long as you get the end result. So I create a script, filter traffic.sh. This script will be run by bash, and now echo -n, enter the IP or network address. Okay, read IP. This is my variable. And now another message that I display, enter, drop, or accept. So the user should enter, drop, or accept. And read another variable I create, let's say answer. Okay, here I have a single quote. You can have single or double quotes. Okay, and now if I want to test the content of the answer variable, so if $answer equals to drop, so here in bash scripting we have a single equal sign. We don't have equal equal, so we don't have something like this. This is not okay. This is the testing condition for a string. Drop, then echo traffic from $IP has been dropped. First, I want to test my if testing conditions, and after that I'll add the iptables rules. So I only write echo and that message. Elif $answer equals to accept, so the user wrote accept, then echo traffic from $IP has been accepted. Okay, else echo invalid option, enter, drop, or accept. And fee, the fee closes the if. Okay, Here it's better if I put a -n. -n means that it writes or it displays the message on the same line. I save the script. I'll add the execute permission. So 700 filter traffic. So enter the IP address or network address. 6666. Enter drop or accept. Drop. Traffic from 666 has been dropped. Okay, we also need a new line there, but that's no problem. I'll add a new line. One more time. Okay. Accept. Accepted. Okay. And one more time. I want to write neither drop nor accept. So, okay, something like this. Invalid option. Enter, drop, or accept. Okay, perfect. So we need some new lines. So here we don't need -n. Okay, and here we need a colon. Okay, that's better. And now the IP tables rules. So here I'll drop the traffic. That means IP tables -i. I want this rule to be the first rule because maybe there are many rules. -s $IP. So the traffic is coming from that IP -j drop. And if the user answered accept, here I'll have the same line, so I can copy and paste it there. Okay, and paste. And instead of drop, I have here accept. That's all. I save the script and run it one more time. So filter traffic. Enter IP or network address. Let's say 3333. This is just an example. Drop. Has been dropped. IP tables -VNL. So the line is there. One more time. Let's try ping 8888. Ping works. And now filter traffic 8888 drop. Okay, the traffic has been dropped. Ping doesn't work. It seems everything is just perfect. Okay, everything works, and that's my assignment.